Okay. Hello, everyone. Welcome. I am Jundu from University of Science and Technology of China. And on behalf of the organization committee, thanks for all your participation to the third DIHARD Speech Diarization Challenge workshop. And especially thanks to the all presenters of keynote and oral sessions to help us to make this workshop possible. And due to the coronavirus pandemic, we went through a tough time for the past year. So we hope all of you are now managing to stay safe and well. The length of today's workshop is more than 6 hours, consisting of 2 keynotes and 3 oral sessions. And each presentation will be conducted by playing a pre-recorded video, followed by a live Q&A session. Okay, this is our organization committee, including Professor Mark Liebman from UPenn as the director of LDC, Dr. Kenneth Church from Baidu Research, Dr. Neville Ryan and Christopher Siri from LDC, Professor Shyam Gamprasi from India Institute of Science, and me. Later, Neville will give an overview talk and chair the 3 oral sessions, while Shyam will chair the 2 keynote sessions. The focus of the DIHARD 3 workshop is mainly to report the outcomes of DIHARD 3 challenge and bring together researchers to discuss the robust speaker diarization problem in challenging realistic scenarios. This year, 11 teams from 9 countries submit their extended abstract of systems. And overall, we have 61 authors from 19 institutes among these 11 teams. And we plot the country distributions of institute and authors in the left and the right figure, respectively. And we can see that the top 2 countries are China and the United States. Finally, we have 10 teams to present today. We also did a statistic on the country distribution of all the 151 registrants before the workshop. And we can see that the country distributions are very diversified. Okay, today we will have 2 keynotes. Dr. Mireia Diez from BUT will give the first one, and Dr. Paola Garcia from JHU will give the second one. We have 3 oral sessions, and Neville will be the chair. And in the oral session 1, we have 1 overview talk and 3 team presentations. In oral session 2, we have 4 team presentations. And in oral session 3, we have 3 team presentations. Okay, finally, as a reminder for all audiences, in the Zoom webinar, we have 2 ways to ask questions. The first one is a text mode. Also, is a preferred option. You can click the Q&A button at the bottom of your Zoom webinar, and then you can type your question into the Q&A panel. The second one is a live mode. You can click the raise hand button and wait the host to enable your microphone. Okay, and in case we cannot answer all the questions in the Q&A panel of the current presentation, the presenters can answer the remaining questions after the presentation later by typing the text. Okay, one last thing to remember, during the video playback of each presentation, please mute your microphone and close your camera. Okay, that's all for my part. Enjoying the workshop. And now I will invite NAVER to chair the first oral session.
Right, thanks, John. So the first talk of the first session will be an overview of the third DIHARD speech diarization challenge that I recorded this past week. So if you could start that video, I will mute myself.
Okay, I will play the video. Sorry, wait a moment.
All right, welcome. All right, welcome to the first talk of the first session of the third DIHARD Speaker Diarization Challenge workshop. It would have been nice to see everybody in person, but given the year we just had, I guess this will have to do. In terms of structure of this talk, I'll start briefly with a little bit of background on what led to DIHARD and what happened in the first two DIHARD challenges. Then proceed to talk for a little bit about the DIHARD 3 tasks and data set, the baseline system that was released for DIHARD 3, as well as its results on that data set, and then finish up with a discussion from a high-level perspective of the final leaderboards this year and some of the future plans for DIHARD. So first, a little history of DIHARD. Let's go back here actually to 2002. 2002 to 2009, NIST ran an evaluation series, the Rich Transcription Evaluation Series, that among other things had a task focusing on speaker diarization, or who spoke when in a recording. Early evaluations in this series focused on diarization of conversational telephone speech and broadcast news, though later evaluations focused on a meeting room scenario similar to that in AMI. There are two main contributions from the RT series. First, it led to substantial improvements for diarization and of meeting speech in particular. And it introduced the diarization error rate metric, which remains the principal evaluation metric within this field. Following the end of the RT series in 2009, there was a nearly 10-year period, 2009 to 2017, which for want of a better term, I've deemed the wilderness years, where work on diarization continued in many groups in industry and academia. And there were many, many clear advances, often happening in tandem with speaker recognition, but there were no major evaluations of a diarization component, which led to, unfortunately, a fragmentation of the research community where different groups would focus on different domains or data sets, sometimes with inconsistent evaluation procedures, which made it very difficult to gauge progress that was happening during this 8-year stretch. This is the backdrop for the 2017 JSON workshop, and emerging from that workshop, DIHARD 1. DIHARD 1 ran spring of 2018 with results reported at Interspeech that fall. It looked at diarization from the perspective of single channel speaker diarization from 10 fairly diverse domains. Systems were evaluated on 2 tracks. There was track 1, which looked into diarization starting from a reference speech segmentation, and track 2, where systems just get the audio and have to do their own segmentation, diarization from scratch. The primary evaluation metric was diarization error rate, and 13 teams submitted systems, with track 1 run by Johns Hopkins and the best performing system for track 2 coming from Brunel University of Technology. This was followed 1 year later by DIHARD 2, which ran spring and summer 2019. Results presented at an Interspeech special session that fall. DIHARD 2 maintained the single channel tracks from DIHARD 1, with the addition of vastly improved annotation and some additional data for certain domains. It added 2 tracks evaluating multi-channel far-field diarization using the Chime 5 dinner party corpus. And for the first time, we supplied a baseline system and results for all tracks. 21 teams submitted systems, with all 4 tracks being won by Brno University of Technology. If you look in the bottom left-hand corner of this slide, there is a table that presents for each track the diarization error rate from the baseline system and the diarization error rate from Brno's system. In all cases, Brno's system is a massive improvement, but particularly for tracks 2 and 4, which are also testing speech activity detection. I'd also be remiss if I didn't at this point mention that while DIHARD was the first of the modern challenges with diarization components, there are 4 other recent challenges that include diarization. Chime 6 included diarization in track 2. Fearless Steps 1 and 2 looked at massively multi-channel diarization from Apollo 11 mission recordings. The most recent Vox SRC looked at diarization of multi-speaker YouTube videos. And Iberspeech has looked at diarization of television broadcasts and of diarization across a lifetime. Moving on to this year's evaluation, there are a few key changes from going from DIHARD 2 to DIHARD 3. One, we dropped the multi-channel diarization condition. Instead, you see Chime 6 for results on that data. We also dropped the child language domain. This is the seedlings data. This was done due to licensing restrictions in that data that made it difficult to distribute. We did add additional data for the clinical interview domain, and we did add a new domain to make up for the loss of the child language data. This is the conversational telephone speech domain, which consists of recordings of phone calls that were originally collected during Fisher English, but were never previously exposed. We also, for the first time, collaborated with NIST via their Open SAT evaluation series and use their platform, their evaluation platform, for all activities. And in the future, we hope for even closer integration. The task, as always, is for each recording to determine how many speakers are present, and for each speaker, identify all the corresponding speech segments. There are 2 tracks: diarization from a reference set, where the systems provided with the reference speech segmentation, and track 2, diarization from scratch, where the system is responsible for producing its own segmentation from the raw audio. These are identical to tracks 1 and 2 in the previous DIHARDs. We evaluate systems using 2 metrics: diarization error rate and DIHARD error rate. Diarization error rate is the sum of 3 sources of error: misspeech, false alarm speech, and speaker attribution errors, and it's computing using no forgiveness collars and explicit scoring of overlap speech. This is the primary metric. It's the metric that's used in all the rankings, and it's the metric I'm going to focus on throughout the rest of this talk, simply due to the lack of space and time. We also did look at a secondary metric, DIHARD error rate, which was introduced originally in DIHARD 2. For this metric, reference speaker and system speakers are optimally paired, and then DIHARD index for each pairing is computed, and DIHARD error rate is simply 1 minus the average of these indices. Typically, it's higher than DER. Sometimes it can be much, much higher. No training data was distributed. However, participants are free to use any public and or proprietary data. In the case where proprietary data is, they are required to adequately document this in the system description they submit. In practice, most teams have used some combination of Voxlib 1 and 2 and or Mozilla Common Voice. The development, we do distribute a development set that closely mirrors the evaluation set. For development and evaluation sets, you're looking at 5 to 10 minute duration recordings from 11 different conversational domains with at least 2 hours of audio in each domain. And the majority of that data was segmented manually and quite painfully, in some cases up to 35 times real-time annotation rates for DIHARD 2. Annotations for data that's new this year were obtained by forced alignment of turn-level transcripts. And these domains range from the trivial audiobooks, where you have a single speaker, to 2-party interactions, such as these clinical interviews, broadcast interviews, or map tasks, and social linguistic interviews, to massively multi-party interactions as emerge in courtroom proceedings, goal-directed meetings, speech in restaurants, and web videos. For the first time this year, we have a data set which is not balanced across each domain. 2 domains, conversational telephone speech and clinical interviews, have rather more data than the others. Due to this and concern over those domains dominating the evaluation metrics, we define two separate partitions for the evaluation set: a core evaluation set, which is balanced so that each domain has roughly the same duration of audio, and a full evaluation set that uses all the available audio as really being distributed just as a service to participants. The table at the bottom of the slide gives a breakdown of the duration, percentage speech, and percentage overlap speech for each partition of each set. As you can see, the distributions are roughly equal between the core and full partitions within each set. This next slide gives the same breakdown, but on a per domain basis for the core development set. This is mainly to give yet another indicator of how much variation there is across domains. So the number of speakers, the mean number of speakers per recording ranges from 1 in the case of the monologues, the audiobooks, upwards of 7 for restaurant speech. And the percentage overlap speech ranges from 0% or single digits all the way up to 20% for restaurant speech, meeting speech, and web videos. And if not depicted here is the same breakdown for the full partition, development set, and core full partitions and evaluation set, but they're roughly the same. As with last year, we released a baseline system this year. It was based on Leap Lab's submission to DIHARD 2. This is a very conventional architecture. There, for instance, there's nothing end-to-end about it. Recordings are divided into short overlapping segments. X factors are extracted for each segment. PLDA scoring is applied to the X factors, and then the output of PLDA scoring is input to a agglomerative hierarchical clustering to do a first pass segmentation. This first pass segmentation is then refined using a HMM segmentation step. All baseline components, as well as the recipes for producing the official results, are distributed via GitHub. And I really want to just acknowledge here most profusely all the contributions from Prachi, Venkat, and Rajat for all their hard work training and testing these systems. The speech activity detection module is based on Kali Aspire recipe. It's a TDN SAD model with 5 TDN layers and 2 statistics pooling layers. And the output of that neural network is smoothed using an HMM with constraints on minimum speech and minimum non-speech durations. It was trained using the entirety of the DIHARD 2 development data. The X factor extraction recipe is fairly generic. 512 dimensional X factors extracted from overlapping 1.5 second segments, centered and whitened using the DIHARD 3 development and evaluation set statistics, then link normalized. And this was trained using Voxelet 1 and 2 with data augmentation. There's nothing particularly unusual about the PLDA scoring approach either. X factors were scored with a Gaussian PLDA model, and then subjected to cluster of agglomerative hierarchical clustering. The stopping criterion for HC was tuned using the development set, and the PLDA model was trained using Voxelet 1 and 2. And then the output of this initial segmentation set, the 8 agglomerative hierarchical clustering, was then used to initialize VB-HMM using operating on 24-dimensional MCCs extracted every 10 milliseconds. The UBM and total variability matrix for VB-HMM were trained using the same data as the X factor extractor, and posterior scaling was applied to discourage some frequent speaker transitions. VB-HMMs run for 1 iteration. Results of that baseline system for track 1 and for track 2 evaluation set are depicted in these 2 tables. You should really focus on the rows where VB-HMM is yes, particularly for the core partitions, as the core partitions most closely match the evaluation conditions in DIHARDs 1 and 2. For the core evaluation set, the baseline achieves 20.65% diarization error rate, and for the on track 1, and for track 2, 27.34% DER. So that was the baseline system. I'm going to move on to give a discussion of the results from this year's challenge. 23 teams submitted systems, 23 to track 1 and 14 to track 2. Participation spanned 10 countries and 3 continents. And actually, despite everything that happened this year, despite COVID, despite our own delays, this is a slight improvement over DIHARD 2, where we had 21 teams submit. Final leaderboards are available online right now at the OpenSAT website, and these will be updated in early February with links to the system descriptions and full team names. Team names are currently anonymized for some teams. In this next slide, I am presenting a statistical summary of the final leaderboards, as you would see on that website. So these are box plots of diarization error rate and DIHARD error rate for each partition of the evaluation set for each track. As I said, I'm going to focus for a reason of time on diarization error rate. If we look at track 1, the median diarization error rate for the core evaluation set is 18.66%, and the median for the full set is 17.26%. The best performing system achieved 13.45% for the core partition and 11.3% for the full partition. Both of these are improvements over the baseline of 20.65% for core and 19.25% for full. And there's a similar pattern of results, basically identical pattern of results for track 2. All the numbers are just shifted upwards by about 6 or 7% due to the additional difficulty of having to also produce a speech segmentation. This next slide goes into rather more detail. This is a breakdown of diarization error rate by domain on the core evaluation set. The leftmost item on this box plot is just reproducing the overall diarization error rate that you saw on the previous slide for sake of comparison. And then for each of the domains, these have been ordered in ascending order of median DER. So there are 3 domains out here that are clear outliers in terms of difficulty: meeting speech, web video, and conversations in restaurants. And then audiobooks is clearly extremely easy. There's a single speaker. It's fairly trivial unless something really goes wrong. I don't know what happened with this entry, for instance. And then in between, you have this continuum of difficulties. There's a large number of domains where median diarization error rate is somewhere between 5 and 15%. And it's the exact same plot for the core eval set for track 2. It's pretty much the same pattern, just everything's shifted upwards, maybe 6 or 7%. There's a slight change in the ordering of which domain is hardest, and there's some slight changes here in terms of this middle set of domains. But it's very much a similar pattern overall. I'm also going to take a slide to present the change in best diarization error rate for each track over time on the core evaluation set. The reason for this is that we've been using some of the same data in DIHARD since DIHARD 1, and DIHARD 2 and DIHARD 3 not only share a large amount of data, but a large amount of the annotation. So there was some worry at the end of the last challenge that this data set might be on its last legs, and we have to start worrying about people tuning to error. So it was comforting to see steady improvements over the course of the challenge. Pretty clearly, this data set maybe only has a couple more years of life left, but it is nice to know there is still some headroom there. So I'm actually a little bit ahead of where I was planning to be this time to talk, but I'll just move on to final remarks. So I really want to just focus on some of our plans for the next few months and then longer term. So in terms of media plans, next week, we intend to release the evaluation key to participants. Hopefully this is next week. LDC asked for me to update the JRTech with a couple pieces of information. If I can get that done Sunday, then hopefully that means everybody submitted a system description will be able to download the updated evaluation release at that point. Early February, we're hoping to publish system descriptions to the leaderboards. This is pending everybody getting their description into us at the end of January. But if that happens and we can sort through them the first couple weeks of February, we're going to have NIST post links from each leaderboard entry to the corresponding system description. We also will be releasing full challenge results as Nodo. So this is all submissions as well as metadata and the output of D-score on a per file and per domain basis. The intent is for this data to support work on system combination methods, such as overlap, and on alternative metrics or evaluation methodologies, because it's pretty clear diarization error rate is not the end-all be-all. It is a convenient metric that has been useful, but it has some glaring problems. And we very much want to encourage people to work on alternative metrics or approaches to applying diarization error rate. Slightly longer term, hopefully by May, publication of the development evaluation sets in the LDC catalog, and also to finally finish publication of DIHARD 2. This was derailed initially by some licensing issues, then COVID, and then just so much time had lapsed that we didn't really have time to take away from other activities to finish the publication. But that is on my to-do list and at the very top. Somewhat longer term, future diehards will be occurring every 2 years. The yearly schedule has just been too grueling and has left insufficient time for proper post-challenge activities, summarization of what happened in each challenge, getting results published in a timely manner, and just doing our own research. So we will be moving to an every 2 year schedule with the next diehard currently scheduled for 2022. And if you want any additional details about the challenge design, the baselines, or the leaderboards, just go to the official website. It's all there. If you have questions that aren't answered there, or if you just want to be added to the mailing list, you're not currently on it, just please send an email to diehardchallenge@gmail.com. Also, if you are interested in being a co-organizer, contributing to future challenges, send us an email. We're happy to bring more people on. And that concludes the introduction. I look forward to spending the next 6.5 or so hours with all of you. Thank you. Okay, I believe we have between 3 and 4 minutes to take questions. Let me just bring up these slides here. All right. One second. Sorry, for some reason my screen share is paused, but indeed. And I've lost my presenter view. 1 second. Okay. First person, Jay Wayne, allow you to talk. Please unmute yourself. Could you ask your question? Hello? Okay. Well, seem to have lost that person. So moving to the question and answer panel, can we get access to the slides? If so, yes, all the slides will be posted after the workshop on the website, along with the videos for each presentation. Second question is on the same topic. Child-centered speech, that issue. Yes, so part of the reason Seedlings was dropped was licensing. It had that data, that specific child language acquisition data had very specialized and specific licensing provisions that made it difficult to distribute with the usual LDC license. One consequence of this, for instance, was that in the general catalog, we had to split the dev and eval releases up to have separate seedlings and non-seedlings partitions. We are interested in perhaps doing a child speech technology challenge at some point that would include diarization as a subcomponent, but we do not have a current plan to add back in child directed speech like that. Technical summaries of the overall challenge systems. So system descriptions are due to be submitted by all teams by the end of January. The hope is that then in the first week of February, I can get NIST to send us a dump of all the system descriptions with metadata about the submitting team, date submitted, etc. And we can maybe by mid-February or late February have the leaderboards linked directly to the system descriptions. All right. My timer informs me we are now ready for the second talk. So just a quick overview on the Q&A, on the scheduling for talks. We are going to try to stick to the schedule as much as possible with each session starting at the designated time. We may slip a little bit within sessions. So our next presenter is Hee-Soo Ha of NAVER Corporation, who's going to be presenting the NAVER Clova submission to the third DIHARD challenge. And if we could get those slides up. All right.
Hello, I'm Hee-Soo Ha from NAVER Corporation. I will present submission of Team NAVER Clova to the third DIHARD challenge. Our system is built on top of the common stepwise pipeline of speaker diarization. This system is composed of three components: an endpoint detection module, which is only for track 2, a speaker embedding extractor, and a clustering method. We use this system as the baseline. Our submission to the DIHARD 3 challenge include two main contributions of the existing baseline. First, we built an overlapped speech detection system and put it between the EPD and speaker embedding extraction modules. Second, we designed a feature enhancement technique for speaker diarization. This technique includes session-level dimensionality reduction and attention-based aggregation. The feature enhancement technique is applied after extracting embedding vectors. Let's start with the overlapped speech detection system. This system finds onset and offset of segments that contain more than one speaker's speech. Our overlapped speech detection system has three features. First, we train the DNN as a three-class classifier, namely non-speech, single speaker speech, and overlapped speech. In the test phase, we use the output layers node that indicates overlapped speech. Second, we augmented the training dataset by adding another speaker segment in the middle of a single speaker segment. This augmentation was performed and increased the ratio of the overlapped speech. Last, we use our CRNN architecture instead of the existing system based on RNN. For the DIHARD submission, we use a school-level ensemble of three model variants: 2D CRNN model with SE, 2D CRNN model without SE, and 1D CRNN module without SE. To incorporate the development overlapped speech detection model, we modified our process pipeline to minimize clustering error caused by overlapped speech. We aim to minimize the effect of overlapped speech in the clustering phase. To do so, we extract speaker embedding only from single speaker segments and perform the first speaker clustering. Then for each overlapped segment, we predict two labels based on centroids of clusters. For example, we find top two centroids with high similarity and assign the corresponding labels for each embedding of overlapped speech. Our second main contribution is adding the feature enhancement module to the process pipeline. Feature enhancement is common in machine learning field. However, if we were right, it has been explored for speaker diarization. Compared to speaker identification or verification, the speaker diarization task consider less number of speakers at once. The speaker diarization task requires discriminative power between only 5 or 6 speakers at most scenarios, while the common speaker verification task requires discriminative power of the thousands of speakers. Thus, we assume that speaker embedding should be projected to a new representation space that shows discrimination of small number of within-session speakers. To achieve this goal, we first reduce the dimensionality of speaker embedding using an autoencoder that is trained for each session. The autoencoder is composed of 2 layers, one for the encoder and the other for the decoder. For the encoder layer, we apply max feature map activation. Using the trained autoencoder, the 256-dimensional embedding vectors are replaced with 20-dimensional enhanced representation, or code. Note that in dimensionality reduction, the autoencoder is designed to run reconstruction of only one session after random initialization. And detailed architecture of the autoencoder is as follows. The input to the autoencoder is 256-dimensional embedding vector. The output of the first hidden layer is a 40-dimensional representation. The representation is compressed into 20-dimensional code by element-wise max operation. To build an output of the autoencoder, 256-dimensional vector is reconstructed from this code. And this whole architecture is trained to minimize MSE error between the input and the output. The role of MFM operation implemented by element-wise max operation is to extract and effectively compress information of speakers included in one session. Finally, the code from the autoencoder replaced the existing embedding vector after training the autoencoder. Then we aggregate embedding vector using a self-attention mechanism. We have prepared a short PyTorch code to introduce this concept. We calculate attention map for each embedding using support map function and iteratively update embeddings based on these maps. There are 2 hyperparameters in this technique. The first one is number with repetition, and the other one is temperature value before support max function. We fixed these 2 values as 5 and 15 respectively. We expected that the attention-based aggregation technique would make speaker embedding robust to outliers and refine the affinity matrix. These 2 figures show the effect of attention-based aggregation technique on the affinity matrices. We could find that most of noises in the affinity matrix were removed by this technique. Such an effect would be useful for most of clustering methods which are performed using the affinity matrix. Now, let's move on to experiments. First, the overlapped speech detection system. We used AMI corpus, box converse, and DIHARD 1 and 2 development set to train the model. The submitted model were tuned using DIHARD 3 development set. We tuned the threshold of each model to get a precision of 0.8. This graph shows the result of our 3 individual models and their score level ensemble. The ensembled model demonstrates the score of 0.55 on the DIHARD 3 development set. In order to build the embedding extractor, the public readiness structure was visualized along with several modifications. We used bursts of box Voxel 1 and 2 development set to train the model. The 64-dimensional features were used as frame-level feature. The number of filters in the first convolutional layer was configured to 64. After the last convolutional operation, average pooling was performed for aggregation. The dimension of embedding was set to 256 dimensions. For the spectral clustering, we calculate affinity matrix using cosine similarity and do not apply any additional refinement process on this matrix. To determine the number of clusters, eigenvalues greater than 20 are counted. We perform k-mean clustering on the spectral embedding to estimate the final cluster labels. This graph shows the performances of various diarization systems in DER. First, we found that the proposed picture enhancement technique increased the performance with a very large margin compared to the baseline. An additional performance improvement was achieved using the output of the overlapped speech detection model. And we also found that the proposed overlapped speech detection model and picture enhancement technique can be effectively applied to other clustering methods, such as AHC. Finally, we submitted the system that achieved 40.97% DER on the development set as the primary system. These results are from the leaderboard of track 1. Our primary system achieved 50.40% DER on core set, while achieved 13.95% DER on full set, and ranked 3rd and 5th place on core and full set respectively. This is summary of our presentation. There are 2 contributions on stepwise pipeline. The first one is overlapped speech detection using an ensemble of CRNN-based models. The other one is a series of feature enhancement for speaker diarization, dimensionality reduction, and attention-based aggregation. Our system achieved 15.40% DER on core evaluation set and 13.95% DER on full set. Thank you for your attention.
Right, so we have several minutes for questions. If I could ask the presenter to turn the video on, good, and share their slides in case anybody has questions about that. I do see we already have one question in the queue. Is clustering on non-overlap segments effective? Since overlap detection will bring more short segments, the X vector extraction from those segments will affect the final cluster performance in my experiments. You could please answer that live.
Yep. Yeah. As you mentioned, the clustering on non. As you mentioned, the overlap detection system will bring more short segment to the embedding structure, but we could find that the clustering is still effective on non-overlap segment with overlap speech detection, and excluding the overlap speech using overlap speech detection model was really effective in our case.
right, does that answer the question? So, okay, I'll mark that as done. Do you have any other questions from the audience? You can either, as John mentioned, ask questions in Q&A. I think that might be the most efficient based upon our limited experience, or you can raise your hand, in which case I will see that you've raised your hand in the attendees panel, and I can ask you to unmute and ask your question live. If we don't have any more questions, I will proceed to the next talk. As I said, we're going to stick strictly to the start times for all the sessions, but we will allow some slippage within the sessions. For some talks, naturally, there will be, I think, more questions asked than for others. So if we could bring up the next video, our next presenter is Sun Yat Leon, Phano Labs, presenting their talk, end-to-end speaker diarization system for the third DIHARD challenge.
Hello everyone. I'm going to present our work, end-to-end speaker diarization system for the third DIHARD challenge. I'm the presenter, Jun Yet Leung. Another author is Nahiro Samara Kong. We are from Phano Labs, Hong Kong. First, we will give an introduction of our work. Secondly, we will talk about our proposed system. Then we will talk about our data set we used. Finally, we will share the experimental result. First, our model is based on the recent self-attentive end-to-end diarization model with encoder-decoder-based attractor. The model architecture is illustrated in this figure, which is from the original paper. And in this challenge, we focus on thread 2 because the end-to-end model is capable of handling speech activity detection internally. We proposed 5 modifications on the original end-to-end system. First, we use conformer encoder instead of transformer encoder. Secondly, we use a convolutional upsampling module to upsample the result resolution. Then, we incorporate the attention into attractor calculation. Next, we also introduce the additive margin penalty into the speaker diarization result calculation. Finally, we try to shuffle different chunks in order to increase the combination of audio samples. Conformer is proposed in the recent Conformer Convolution Augmented Transformer for Speech Recognition paper. The main component is the conformer box, which combines the transformer and convolutional network. The transformer is good at handling the global feature, but it is bad at handling the local features. So we want to use the conformer box to replace the transformer encoder in order to handle the local feature. Next, we observe that each frame in the original end-to-end model is about 0.1 second because it subsampled the input feature by a factor of 10. But in the DIHARD evaluation, no caller is used. We find that when the result comes with a low resolution, it will increase the DER. So first, we paste a convolutional upsampling module to increase the resolution of embedding. Then, instead of manually subsampling the input feature, we use a convolution subsampling module here to subsample the audio feature by a factor of 10. Next, in the dial challenge, we can observe the sequence of embedding is very long. And in the original end-to-end model, the information of the etcher is passed by the last timestamp of the encoder output and the cell state. So we suspect that some important information could be lost when the sequence is very long. So instead of using the last timestamp of the encoder to initialize X0 and C0, we use two separate multi-head attention as a pooling mechanism to initialize X0 and C0, which is illustrated in the left-hand side of the figure. The main component is the multi-head attention. We use the multi-head attention to aggregate the embedding to produce the X0 or C0. And also, we also use a common global attention loop mechanism on the decoder side. It allows the model to retrieve the information from the embedding at each decoder timestamp. Next, inspired by the angular softmax, we try to put the additive margin penalty into speaker diarization result calculation to increase the difficulty of the task and make the model more robust. So basically, we first normalize all the etcher. Then we use the permutation event training to obtain the correct permutation of the speaker label, similar to the original paper. So after that, we will know whom the etcher represent. So in the real optimization step, the posterior probability of YTS hat or speaker S at time t is calculated by this equation. Basically, the embedding at time t and the etcher of speaker S, we do the dot product, and with the speaker S at time t is 1, that means the speaker S speed at time t will give a minus m. Otherwise, we'll add plus m there in order to increase the difficulty of the task. So finally, actually in the training procedure, each training sample is a 50-second audio from the original recording. So in order to increase the combination of different audio samples, we divide the original recording into smaller pieces. It's about 10 seconds. Then we shuffle those pieces with a probability of 0.5. Here is the data set we used. First, we will create some simulated recording on the Libre speech dataset. Then we'll pre-train our model on those simulated recording. Then we'll fine-tune our dataset on the in-domain data. Here is our fine-tuning training set. In detail, we split our DIHARD 3 development set into a training set and validation set. Now I will share the experimental result on the conformer and the resolution. First, when we look at the DER, we can see when we use the conformer encoder, it gives significant improvement on the validation set and the evaluation set. Also, it also improves the JER. And in addition, we also tune the number of layers and the dimension of T10 unit. So the second column indicates the encoder has 7 layers and T10 unit dimension is 128 instead. When we use a deeper level, we saw some improvement on the validation set in DER. But the DER on the evaluation set does not give a big difference. But the model with three modification, it gives the best result on the evaluation set in DER. As it gives the best result on the DER, on the evaluation set and validation set in DER, so we continue our development with these three modifications. And now we're going to share the result of the attention mechanism and the additive margin penalty. So basically, if we incorporate the attention mechanism into the attractor, it gives significant improvement against the model without attention mechanism. And when we also incorporate the additive margin penalty, it gives further improvement on our validation set in DER, as well as the JER on the validation set and evaluation set. Despite that, it does not give a big difference on the evaluation set DER. So we'll incorporate these two modifications in our system and continue to development our system based on these two modifications. Finally, we try to incorporate the chunk shuffling during the fine-tuning process. We can see that on the evaluation set DER, on the full set, we can achieve 20.7 DER on the full set. And compared to the previous best system, it only achieved 21.7. That means the chunk shuffling gives 1% DER improvement on the full set. And that means it proves the chunk shuffling gives significant improvement. For the second column, larger input indicate that the pre-trained model is trained with a longer time. And when the pre-trained model is trained with a longer time, it also gives significant improvement here. And on the full set, on the evaluation set, we achieve 20.05. And this system is our final system. So in the future, we will give more detailed comparison of different modifications, and also we will try to train the pre-trained model with a longer time for comparison. Thank you.
Right, so if our presenter could unmute themselves and share their view and open up a copy of the slides. I see we already have a few questions lined up. So first from Shinzi Watanabe, what is Bayesian in the Libre speech simulation?
Yeah. Okay. Yeah. So the beta. So I guess he's referring to the beta in the data session. So the beta actually control how much overlap speech is created in the simulated recording. And actually we are using the script provided in the original end-to-end paper. From the original paper, end-to-end speaker diarization for an unknown number of speakers with encoder, decoder, based, etc. from this paper. This paper share the code on the GitHub, and we use the script, the provided script to create the simulated data. And there's a parameter called beta to control how much overlap speech is created. And then the next question is.
Yeah, so the next question, this is actually a question I had. So one of your tables mentions that I'm not sure what the reason was, but it mentions that you were using the clinical domain from DIHARD-2.
Yeah, I should verify that. It seems that the DIHARD-2, other audio in the DIHARD-2 development set actually, when the DIHARD-3 development and the DIHARD-2 development shared, most of the audio are the same in both development sets. So, but only the clinical are different. Only the clinical data are not provided in the DIHARD-3 development set. So we just add the long overlap part of the DIHARD-2 development set data. Yeah.
I'm surprised it makes a difference since that the clinical data in the DIHARD-3 development set should be a superset of DIHARD-2, but that's interesting that it does.
Yeah. I just find that it's mentioned in the evaluation. The description is that in DIHARD-3 they release a new set of clinical data here. So I just add.
Okay, yeah. So I probably should have clarified. It's new in that we expanded by adding additional recordings, but it should be that the DIHARD-3 clinical data is a superset of the DIHARD-2.
Okay. I see.
So it might be the case that the numbers will be pretty similar if you omit that step.
Okay. So
question.
So next question is, could you explain a bit more to conformal box? Oh yeah. I have incorporated the relative position encoding. Number of head, the attention head should be 4, and the feed-forward layer dimension. I have 2 systems. One is just for using. It should be 124, if I remember correctly. I did check about it. But yeah. The feed-forward layer dimension should be 124, and should be same macron feed-forward layer. Yeah. And yes. Next question should be X0 and C0 are computed by 2 multi-head attention. Yeah. Which do not share the weight. Could you explain why? Okay. Because I expect that the X0 and C0 contain different information. So I use 2 different multi-head attention module. I'm not sharing the parameter. Yeah. And in my limited experience, end-to-end struggle with many speakers, and modify those help a lot. Yeah, actually, in this experiment, I limited I set limit of the maximum number of speaker. I only using four maximum number of speaker equal to 4. Yeah. So I haven't do experiment with more speaker. Yeah.
So one thing I would say that you could do within just DIHARD is the meeting speech domain, the web video domains, and the restaurant speech domain, and the courtroom domain. Those all have recordings with that might be a useful test case.
Yeah, that in the restaurant there more than 4 speaker. Yeah.
And then we have one more question. Could you give more details about how you make the simulated Libre speech data? For instance, number of recording, overlap percentage, etc.
You can find out the information from the original end-to-end paper from the InterSpeech 2020. There are multiple papers. It describes the procedure how to create the simulated data. Yeah, you can find out the original paper. And there are lots of detail about it. Yeah.
All right, Shinji just also.
Yeah. Thank you. Is that all?
Okay, so it looks like I'm just checking. I don't see anybody has their hand raised in the queue. So I think in that case, we will proceed to the next talk.
Thank you.
So, thank you very much. So the final talk that we have lined up for this first session is going to be presented by Shota Horaguchi of Hitachi. This is the Hitachi-JHU system for the 3rd DIHARD Speech Diarization Challenge. I see you have the video up, so if you could please play that.
Thank you for coming to our presentation. I'm Shota Horiguchi from Hitachi, Japan. In this presentation, I introduced Hitachi and Johns Hopkins University's joint efforts on the 3rd DIHARD challenge. This is the overview of our system. It consists of 2 expector-based systems, 2 end-to-end neural diarization (EN) based systems, and 1 hybrid system. The final results are based on the ensemble of 5 subsystems. We use almost the same systems for both track 1 and track 2. Only the difference between them are the VAD-related part, which is used for pre-processing of the expector-based systems and post-processing of the EN-based systems. So I start from VAD part. To obtain VAD results, we used posterior average of the estimation from 2 models. One is a SyncNet-based VAD, which is implemented in Keynote library. The model consists of SyncNet, followed by stacked LSTM layers and 1 fully connected layer. We trained it on DIHARD 3 dataset for 300 epochs. The other one is TDNN-based VAD, which consists of 5-layer TDNN with statistics pooling. It also trained on DIHARD 3 dataset for 10 epochs, but with data augmentation using Musan corpus and simulated room impulse responses. Our method achieved 2.58% of false alarms and 2.55% of missed regions. From here, I will introduce each subsystem in our solution. The first one is RedSUNet-based system, which consists of expected extraction from each speech segment, clustering, overlap assignment, and modified overlap. For expector extractors, we employed 4 kinds of models, each of which trained on Box7 dataset. They have different number of layers, normalization method, compression for feature extractions, and augmentation. For the extracted expectors from each extractor, we applied VBX clustering following DUT system for DIHARD 2 challenge. We first applied agglomerative hierarchical clustering with the interpolation of Box7 PLDA and DIHARD 3 PLDA. After that, Bayesian HMMs clustering with the LDA is applied. Once clustering is completed, we applied overlap assignment. Overlapped regions are detected by SyncNet-based model used for VAD, but trained to detect overlap using DIHARD dataset. And we assign the closest other speaker in the time axis as a second speaker for each detected frame. Finally, results from 4 models are combined using modified overlap. I will explain later how the overlap was modified. This is the results of track 1 on DevSet. VBX improved DAR in 3 out of 4 models, and overlap assignment improved DAR by over 2%. Model combination using overlap further improved the performance, and we obtained DAR of 14.04% of Jacquard error rate of 34.29%. Next, I will introduce TDNN-based subsystem. This system uses TDNN-based model implemented in the Caudy voxel recipe, which takes 40-dimensional filter banks as input and outputs 512-dimensional speaker embeddings. Following VBX and overlap assignment parts are the same as ones used in the ResNet-based system, so I omit that explanation. As shown in the table at the bottom, this subsystem results in 13.87% DER and 32.73% Jacquard error rate. From here, we introduce 2 EN-based systems, each of which takes their reverberated audio as inputs in inference space. The first one is EN-EDA-based system. From here, I introduce 2 EN-based systems, each of which takes their reverberated audio as inputs in inference space. The first one is EN-EDA-based system. EN-EDA first convert log-mail filter bank-based features into frame-wise embeddings using stacked transformer encoders. From the embeddings, a flexible number of attractors for each speaker are calculated using encoder-decoder-based attractor calculation module named EDA. Diarization results are calculated based on dot products of attractors and embeddings, followed by sigmoid activation. We train the model using simulated 2-speaker mixtures for 100 epochs, and then fine-tune the model using 1 to 5 speaker mixtures for 75 epochs, and then adapted the model using DIHARD dataset. But we have some issues to fit to DIHARD tasks. The first one is that the EN-EDA is a model that performs VAD and diarization at the same time. So we have to incorporate it with Oracle VAD or more accurate external VAD module. Therefore, we applied post-processing using external VAD. We removed false alarms and recovered missed speech by assigning the speaker with the highest posterior probabilities using the results of external VAD. The second issue is that EN-based model cannot handle the case when the number of speakers is large, especially more than 5 speakers. This is because the model was trained on simulated mixtures that contains at most 5 speakers. To solve this issue, we propose iterative inference method for transformer-based EN models. We first decode at most 5 speakers as usual. If the number of decoded speakers is less than 5, we stop decoding. But if the number of speakers is 5, the recording may contain more than 5 speakers. So we select silence frames and conduct the decoding only for the selected frames again to extract 6th to 10th speakers. This procedure continues on until the stopping condition is satisfied. But this inference method has one problem, that for example, 6 speakers' speech activities cannot overlap with 1st to 5th speakers' speech activities. To ease this problem, we used iterative inference and overlap together. At first iteration, we recorded at most k speakers. And from the second iteration, we recorded at most 5 speakers as explained in the previous slide. We use 5 values, 1, 2, 3, 4, and 5 for k. So we obtain 5 different decoding results. They are combined using overlap. Results. Increasing the number of speakers in simulated mixtures, VAD post-processing and iterative inference with overlap successfully improved the DERs and JERs. And finally, the best results were 12.92% DER and 33.85% JER. Next, I introduce another EN-based system, SCEN. SCEN, speaker-wise conditional EN, is a model to estimate each speaker's speech activities one by one, conditioned on previously estimated other speakers' speech activities. The original paper used a transformer encoder, but we use conformer encoder instead. VAD post-processing was also applied as an EN EDA-based system, but iterative inference cannot be used for this model. This is because the conformer encoder depends on the order of input features. So we cannot use this model with selected frames. We trained the model using mixtures, each of which contains at most 4 speakers for 200 epochs, and then adapted on DIHARD 3 dataset for another 100 epochs. We obtained 13.13% DER and 35.35% JER from this SCEN-based system. The final subsystem is X-vector-based system incorporated with EN as post-processing. The clustering results from TDNN-based X-vector system is used as input for EN as post-processing. I first explain why this procedure is effective. X-vector-based system depends on unsupervised embedding clustering, so it can deal with large number of speakers. But it has difficulty on overlap processing because it depends on an external overlap detector. On the other hand, EN-based system can handle overlapping speech, but it has a disadvantage that it cannot deal with large number of speakers because the model depends on the training dataset, and it is difficult to use mixture of large number of speakers because EN employs permutation invariant training. To compensate for each other's weakness, we used EN as post-processing, in which select 2 speakers iteratively and update the results of the selected 2 speakers. I graphically explain how EN as post-processing works. Given initial results calculated using X-vector clustering, we first decide the processing order of speaker pairs. This is determined by the number of frames that are selected to exclude speakers rather than the selected 2 speakers. In this case, we first process speaker 2 and 3, and then speaker 1 and 3, and finally 1 and 2. To process speakers 2 and 3, we first select frames to contain only the selected speakers and silence. The corresponding acoustic features are input to EN EDA model to estimate diarization results of 2 speakers. Speaker labels are assigned by solving speaker permutation between the initial results and the newly estimated results. And then the results are overwritten by the new results with overlap. We iteratively execute the same process for each speaker pair. In the second iteration, we do the same for speakers 1 and 3 and update the results accordingly. In the third iteration, speakers 1 and 2 are processed to obtain the final results. Results after 3 iterations of processing is considered as a final result on EN post-processing in this case. Results in the right table show that the EN as post-processing improves the results of X-vector clustering. And this is better than the overlap assignment using heuristics as in System 2. Finally, we combine the results from 5 subsystems using modified overlap. Overlap is a recently proposed method to combine overlap-aware diarization results based on voting. We found that the processing when multiple speakers have the same rank can be modified from the original one. The original overlap assigns uniformly divided regions for each tied speakers, but we instead assign the regions for all the tiled speakers without any division. We also introduced a weighting mechanism to change the importance of each system included in DOVALAP. The results showed that the modification and manual weighting further improved the performance of the original of DOVALAP. This is the DRs of the subsystem and DOVALAP so far in track 1 and track 2 on both hull and core conditions. We can observe that each subsystem is significantly better than the baseline system, and DOVALAP system performed best in every condition. Additionally, we use this system 6 to create suit labels for the DIHARD 3 evaluation set and re-adapted E&EDA model. This self-supervised adaptation further improved the performance of the final results. Note that self-supervised adaptation of SCEN also improved the performance of SCEN performance. But the final DOVALAP results was degraded, so we didn't use it. This is the results. Replacing the E&EDA model with that with self-supervised adaptation improved DER on evaluation in both E&EDA-based system and E&D as post-processing system. The final DOVALAP results was slightly improved by using self-supervised adaptation, and this system 9 was used for our final submission. I summarize the presentation. Our system consists of posterior average of 2 VLA models, modified DOVALAP of 5 systems, which includes 2 XPIFT-based systems and 2 EN-based systems with VLA post-processing and iterative inference, and 1 hybrid system using EN as post-processing. We also employed self-supervised adaptation of the EN-EDA model. Our system got the 2nd place in track 1 hull, core, and track 2 hull, and got the 3rd place on track 2 core. Thank you.
Right. Thank you for that talk. Now, we do have a decent amount of time for questions. If there are any questions from the audience for that talk, please either ask in the Q&A panel or write. One question: was the overlap detector trained on the DIHARD data only, and did you encounter any problems with overfitting? Also, if you could bring your slides up and share them.
Wait a moment.
Sure.
You see my screen?
Yes. All right. And so again, the question was the overlap detector trained on the DIHARD data only? And did you encounter any problems with overfitting?
Yeah, I don't know the detail of our overlap detector, but our overlap detector was only trained on the DIHARD 3, and the performance itself of the overlap detector was not so good, which has about 13% of false alarms and 13% of missed speech. So maybe it's not so good.
Yes. So how long does it take to get the final RTTM from the audio? So I guess the question here is, what is the real-time factor on your system, sort of approximately?
Real-time factor. Sorry, I don't have the answer about the real-time factor on the system, but maybe you mean the overall system?
Yeah, the overall system, just sort of like ballpark how much
maybe
computation is.
Yeah, the most time-consuming part is, I guess, the expector part, and so yes.
Okay, so the end-to-end system is not.
Yeah, end-to-end system have a can have a very fast inference speed, so it's not so time consuming. For example, ENDDA can decode all the development set within 5 minutes. So it's not so takes so long time. Yes.
Okay, yeah, that's about Tor set's like 23 hours and full set's like 34 or something. So that's not bad at all. So what is the manual weighting in Doverlap based on?
Yeah, a manual weighting. Yeah, we introduced the parameters to change the importance of the each subsystem for the input to the Doverlap, and to change the rank of the each system manually. For example, in our method, the system 5, which is use the ENDA's post-processing, has the best performance. So we weight this system more than the other ones. For example, SE and expect-based system.
Okay.
When calculate the rank of them.
Okay, so I did have one question. Unfortunately, I didn't manage to catch all of your slides since I was trying to clean all my microphones. But I know you did reporting results here, but what kind of results does this system get on any other data sets, for instance, AMI or Call Home? If you have those numbers sort of handy.
You mean the result on the others data set?
I'm just wondering if this system, if you've tried this on any other data sets, this exact architecture.
Yeah, in this DIHARD period, we only see the performance on DIHARD dataset, so I'm not sure. But only I know is END based model, and it has about 3% better than the DRI reported in the interspeech papers. So,
okay.
Yes.
Okay, thanks. And one other question. So how long is the input for the end-to-end model? If your segment recording session, how do you deal with permutation consistency across the different segments?
In the inference phase, we didn't use chunking, so all the recording for each. Yeah, when I input the recording for the end-to-end model, I didn't split them into chunk. So for the recording was input to the model to calculate all the Diarization results.
Okay, and I see Sanjeev just answered my question as well. So unless we have any more questions, I think we can adjourn this session. We have a short break before the first keynote. The first keynote will start in about 12 minutes at 1340 UTC. So if some of us, I think, need quite a bit of caffeine at this point. So I will join you hopefully in obtaining that, and see everybody back shortly.
Okay, so good afternoon, good morning, or good evening, wherever you are, depending on where you are watching this from. So myself, I'm Sriram Kanapati. I'm here from India in Bangalore, the Indian Institute of Science. So welcome back to this second session, so as to speak, on this online workshop. So we had a very exciting set of talks in the morning session from multiple teams. So now we are heading towards our first keynote. We have two keynote sessions, as you might have seen in the program. This is the first of the two keynote sessions. And I'm happy and glad to introduce the speaker for this session. The speaker is Dr. Mireia Diez Sánchez. She's a researcher in the speech group at the Brno University of Technology. Dr. Mireia received her electronic engineering degree in 2009 and her PhD in 2015, both from University of Basque County in Spain. Her thesis has focused on aspects of features for speaker and language recognition. In 2016, she obtained an individual Madame Marie Curie Fellowship for Speaker Dias project dealing with diarization tasks. She has also been actively attending several workshops and conferences, participated in several speaker and diarization challenges, and actually, she has been active in the DIHARD challenges, both the current challenges as well as in the past challenges. Her research interests are mainly in speaker diarization, speaker and language recognition, and as well as in Bayesian inference. And today's talk is also on the very interesting topic of variational Bayesian models for speaker verification. As we have seen in almost all the talks leading up to this keynote session, most of them use a refinement method based on variational Bayes. So we are all excited and looking forward to hearing this methods from Dr. Mireia Diez.
Hello, everyone. My name is Mireia Diez. I'm from Brno University of Technology, and we were asked to prepare one of the keynotes for today's workshop. And I've titled ours Bayesian HMM Clustering in Speaker Diarization. So it may come as no surprise that I'm going to be talking about what has been our main diarization system in the last few years, which is this speaker diarization based on Bayesian HMMs, which you might have heard as VB diarization, BHMM diarization, or even VBX. And I will first give some historical perspective on how this algorithm came into life, and then I will talk about how the algorithm evolved through time. I will cover the two flavors of this diarization method, which are first the Bayesian HMM with eigenvoice priors operating in a frame-by-frame basis, which was part of the winning system in the first DIHARD challenge in 2018 in a submission made by the JHU team. And next, the Bayesian HMM-based expector clustering, which was the core of the winning system in the second DIHARD challenge in 2019. And this time we were successful, and it was in a submission made by our team, VUT. And next, I'm drafting here already what I would like to be the message that I want to convey with this talk. And it is that this Bayesian HMM diarization has been establishing diarization baselines in standard tasks in the last years. And we have been always providing our code as open source code, so anyone could be using this recipe and running it for any purpose. And as an example, in this year's third DIHARD challenge, the baseline provided by the organizers achieved 20.65 diarization error rate in the core condition on the track 1 of the evaluation set, and 19.25 in the full condition. But anyone who would have downloaded our recipe from the GitHub repository from this BBX code, which was the core of the winning system in the second DIHARD challenge, just by downloading it, running it, slightly tuning it, and submit it to the leaderboard, could have achieved a 17.25 diarization error rate in the core condition and around 16.01 in the full condition, which is a significant gain as compared to the official baseline. And this system actually would have ranked this year in 8th position for the core condition and in 11th in the full one. So also in this line of establishing baselines, I will, at the end of the talk, talk about the contributions of our last journal paper, also related to this diarization method. which has been just recently submitted, and the title of the paper is Bayesian HMM Clustering of X Vector Sequences, or BBX, in Speaker Diarization, Theory, Implementation, and Analysis on Standard Tasks. And the main thing is that with this paper, we established new baseline results for Colholm, AMI, and the second DIHARD dataset. So let me start with it, and let me talk about first the diarization methods that inspired or eventually led into this BHMM diarization. So in around 2008, there started coming some of the diarization methods which would be doing some sort of clustering of I vectors. And what these methods would do, they would take the input audio utterance and they would cut it into short equal length segments. Here I'm representing these 1 second segments. And then for each of these short segments, they would extract I vectors or even speaker factors from the GFA model in the very early approaches, as I vectors didn't even exist yet. And then what these methods would do is to cluster these low dimensional representations according to some clustering method or criteria. And in this graph, I'm representing what would be the agglomerative clustering. So according to some similarity criteria, pairs of I vectors would be consecutively clustered until some stopping threshold or criteria would be achieved. And the assumption here is that the I vectors belonging to the same speakers could be clustered together, and therefore this clustering solution would be giving the solution to the clustering problem. And next, I'm going to mention the diarization using factor analysis. This was a work by Patrick Kenny. And the method is similar somehow to the I vector clustering approach, as it also uses a pre-trained I vector extractor. But rather than extracting I vectors for these short segments, what it does is it estimates some I vector-like speaker models, and then it makes a probabilistic assignment of the frames to the different speakers. So let me go a little bit more slowly through it. So like I said, this model operates on a frame-by-frame basis with MFCC features. Although to avoid very frequent speaker turns, it allows speaker changes only every second, which results in effectively the same segmentation as the one that I've shown for the I vector clustering approach. And then it models these speaker-specific distributions using an I vector-like model, where the speaker-specific distributions are Gaussian mixture models, which share the weights and the covariances that are taken from the universal background model. And then for each of the speakers, the supervector of concatenated component means is constrained to live in a linear subspace as defined by this familiar formula to all of us already, where the low dimensional vectors Y are treated as latent random variables with standard normal prior, and imposing this prior is what makes this model Bayesian. So like I've said, these two models are somehow similar as they use the same informative prior on the speaker distributions, and they both need pre-trained I vector extractor model, but there are some relevant differences between both of them, and this is what I'm going to highlight next. So the I vector clustering approach extracts I vectors from short segments, which results in noisy estimates, whereas the diarization using factor analysis estimates speaker models on all the frames coming from a given speaker. And I will illustrate this again with the graph. So here we have now on the upper part of the slide, the same schema that I have used earlier to represent this clustering of I vectors. And below I'm showing what would be the diarization using factor analysis. So like I've said before, we would have in this clustering of I vectors the input audio utterance, which would be cut into 1 second short segments. And for each of these segments, we would extract one point map estimate, one I vector. That would be a noisy estimate of this segment. Whereas for the diarization using factor analysis, what we would have is some I vector-like speaker models. In this example, I'm showing 4 different I vector-like speaker models. And the assignment of the frames to the different speaker models would be done probabilistically. And this would be estimated on all the frames that are coming or assigned to it. So it's a more robust estimate than for the clustering of I vectors. And also the I vector clustering makes hard decisions. The I-vectors represent these point map estimates of the speaker models, and also the clustering of I-vectors is making hard decisions that it cannot recover from. It has some errors that it cannot undo. So instead, the diarization using factor analysis, it has no hard decisions as it uses an iterative variational-based inference, where it re-estimates the speaker models, keeping the uncertainty of the models or the posterior distributions, and re-estimates the sub-assignments of frames to the speaker models. So what I mean here is in the clustering of I-vectors, we are extracting these I-vectors for each of the segments, and then the clustering that is performed later on. And here I'm actually showing the agglomerative clustering, which is maybe the clustering method that suffers more from this hard decision that I'm mentioning, as every time it clusters two I-vectors, this decision is made and it just can go forward. It's not going to undo any of those decisions. There are other methods to cluster these I-vectors. It could be done by k-means or by using Bayesian and Gaussian mixture models. I'm even going to comment on some of that later on. And those somehow soften this hard assignment of a hard clustering or decisions. And instead, the diarization using factor analysis, what it does is it initializes, like I said, these different speaker models, and it can be then done randomly with some random assignment of the frames to the different speaker models. Then the speaker models are estimated using those frames. And next, there is a probabilistic assignment of the different segments to the speaker models. And this process is repeated iteratively until convergence. So this is not a hard decision, it's a probabilistic assignment, and it can be it is repeated several times until the model reaches the final decision and solution to the diarization problem. In the next slide, I'm showing the same idea, but with more mathematical formalism. So in the clustering of I-vectors approach, we would extract the I-vectors for each of these n segments using the formula shown here. So this would be the I-vector that is estimated for each of these n segments. But in the diarization using factor analysis, what we have is I-vector-like update formulas. And this resembles a lot the I-vector estimation. So we would have to keep track of the full posterior distribution of these speaker models. And the means of these posterior distributions are the ones that resemble the I-vector model, the I-vector extraction. The difference is that we have this gamma term over here, which are the probabilistic sub-assignments of the frames to the speakers. So in this case, the I-vector is estimated on the full segment, that is just single estimate. But in the diarization using factor analysis, what we have to do is for each of the speakers, we have to take into account only the frames that are assigned to them and use those for the updates of the models. So that is why we require this term in these updates. And I'm not going to give the expression to estimate these gammas because it's a non-trivial estimation and I don't want to get that deep into the math today. I just wouldn't have time to cover it all. I will just mention this later again for another example. So this is it for these two approaches, which were the inspiration, let's say, for the Bayesian HMM with eigenvoice priors, because this diarization method of ours was introduced as a mere extension of the diarization using factor analysis. The difference was that it was built into an HMM to model the speaker turns and to avoid this pre-clustering into the fixed length segments that I've mentioned that it was doing. And this method was implemented by Lucas Burgett in 2010, but it was not officially released or linked to any publication, so it got popular much later on. Let me describe the model more formally. So, like I've said, our model is a Bayesian hidden Markov model, where states represent speaker-specific distributions, the transitions between states represent the speaker turns, and the speaker distributions are modeled by Gaussian mixture models with parameters constrained by eigenvoice priors, as in the I-vector or GA5 models, or this diarization using factor analysis. So I am showing here to the right one HMM model, which is an example of how this model could look like for our diarization system. And in this specific case, I'm showing the HMM with only 3 speakers. Our model will eventually estimate also the number of speakers, and I will even comment on that already in the next slide, but let's assume for now that we have only 3 speakers. And this HMM is ergodic, so transitions between all states or speaker models are possible. And then for each of the speaker-specific distributions, we would have the same formula or that I've shown before. So they are represented by Gaussian mixture models, where the speaker means are constrained to live in this lower subspace, and we are imposing the same normal standard prior on the speaker models. Next, I have here the exact same HMM as I was showing right now, and also this other HMM, but they both represent exactly the same. The only thing that I have done here is introduce some dummy non-emitting initial state. And I've done that. I've done it just because it is much easier to introduce the different parameters and variables in this format of the HMM. But you can see that they actually correspond to the same HMM model. So, like I said, we're assuming that we are starting from this dummy non-emitting state, and then we have these pi values, which are actually the speaker priors, and what they represent is the probability to transition into each of the speakers or HMM states. So at the beginning, the assumed generative process is that we would start from this initial state, and then with probability pi, we would transition into some of these speaker models. Then the observation would be generated using the corresponding Gaussian mixture model. And next, we could either stay in the same speaker or HMM state with this p-loop probability, or transition back to the initial state and then transition to any of the other speakers, or even re-enter the same speaker model. We allow this re-enter into the same speaker model just for mathematical convenience, but it doesn't affect the model in any other way. And this p-loop probability is a parameter that we set by hand, or we usually tune it on the development set. And what it does is it is used to model the natural length of the speaker terms. And I've said already that our model is going to be able to estimate the number of speakers. So what we do for that is we initialize the model with an upper bound on the number of speakers. So instead of having these 3 speakers, let's say that we would initialize it with 10 speakers, because we are not going to assume that the utterance has more than these 10 speakers. And then on the updates of the model, these speaker priors are also going to be re-estimated. And eventually, what the model will do is it will drop some of these pi values to 0, which effectively removes the speaker models from the speakers from the model. Because if the pi value is 0, we just cannot transition into that speaker, and it's just not going to be present in the output of this Diarization system. So I'm summarizing here the different variables that we are considering in our model. So we would have X, which is the observed set of vectors, in our case, the MFCC features, set, which is the alignment of frames to the HMM states, and Y, what is the set of all the speaker-specific latent variables. And the complete probabilistic model can be defined in terms of this joint probability, where we have the speaker-specific distributions for the individual frames, the transitions probabilities emerging from the HMM model, and the different speaker priors. Then to address the speaker diarization task, the speaker distributions and the latent variables set are jointly estimated given the input sequence X. But the solution to the speaker diarization task is given by the most likely sequence set. So this is the only thing that we really need to infer to solve the diarization problem. So what we need is this posterior probability, which can be estimated using this integral. And this term could be derived using the standard rules of probability from the joint probability that I've shown here. But the problem is that this integral is intractable. So what we do with our model is approximate it with some approximate distribution. And in our case, we use the mean field approximation, and we use the variational inference to estimate all these speaker models and the assignment of frames to the HMM states. And so I'm drafting only here what is our model. I'm not going to get deeper into the math, mainly because I don't have time to cover it all. I will, at the end of the talk, give some references on where all these things can be found and even related talks to it in case anyone would be interested in learning more about the inference in the model. So as a summary, this is what we need to do with our model. We have to first pre-estimate an I-vector extractor model, which is the total variability matrix and the universal background model. And we also will have to initialize the assignment of frames to speakers, this set. This, as I mentioned in some example earlier, it can be done just randomly, but actually initializing it with another good system, it's better, and it's actually key to get best performance with the method. Then the variational inference iteratively updates the speaker models, these Y variables, and these are done in the same way as in the diarization using factor analysis. These are the exact same formulas that I've shown in one of the slides earlier. The difference here is that this probabilistic assignment of frames to the speaker models is done differently. So now we have the HMM model, and these gammas are estimated using the forward-backward algorithm from the HMM model. Once again, I'm not going to give the full formula for it because it's non-trivial. And then also the speaker priors are re-estimated, like I said, which effectively gives us the number of speakers that are in the utterance. And this is done by the dropping the redundant speakers by the automatic relevance determination principle that emerges from our operational-based inference. And this is it about the main idea of how the model works. What I'm showing here is the convergence of the model, or an example on how it behaves. So what I have here are different iterations of the algorithm. The first line would be only the initialization and the consecutive first, second, and third iterations of these update formulas. And in each line, what I show is a full utterance, and the background colors represent the reference speakers. So this white color would be representing one speaker, and the pink one would be representing another speaker. And what you see here as a very thin line in the first iteration are this assignment of frame to speaker, so the speaker responsibilities. And like I mentioned, we usually initialize the model with 10 different speakers. So that is why all these responsibilities are roughly in this 0.1 value. Then in the first iteration, we can already see that there's some deviation from this initialization. And in the second iteration already, there's some speakers that are starting to cover some of the speech. We could see that the blue one is starting to cover the speech for the white speaker. And then we have these two yellowish and orange speakers that are fighting to cover the rest of the speech. And already in the third iteration, there's some more defined solution, let's say. So the blue one is definitely covering the speech from the white speaker, and the orange one is trying to cover the pink one, although there are still some other speakers present, but eventually those are also gone. So you can see here how it behaves, that it's really dropping some of the speakers, and already in the fourth iteration, we only have 2 relevant speakers as the output of the algorithm. And in this consecutive iteration, what the model does is basically refine somehow the boundaries of the speech between speakers, and also try to cover the shorter segments. Not in all cases. We can see, for example, that this speech is still not recovered, but this is how it mainly behaves. And this is, again, a summary. So what we have been using as a standard statement for this Bayesian HMM with eigenvoice priors is that this approach addresses the complete speaker diarization problem by means of a straightforward and efficient variational-based inference in a single probabilistic model, because a single model is used to infer the assignment of frame to speakers, the number of speakers, and the speaker-specific models. And until not so recently, this really felt like we were addressing the complete speaker diarization problem, but lately there are emerging new techniques and new methods, like the end-to-end approaches specifically, which are doing even more than what our model does, because our model still requires input after voice activity detection, so it doesn't deal with this problem of detecting where speech and silence is. And also, unlike the newer end-to-end approaches, it does not deal with the overlap speech. So this would be 2 of the drawbacks of our system as compared to the newer technologies that are emerging right now. But in any case, I'm going to give a historical perspective still on how things connect and evolve through time. So I am first highlighting here 3 different systems, which are all 3 clustering of I-vector systems. The first one in 2008 is the clustering of speaker factors from GFA. Like I mentioned, this here still I-vectors did not exist. So the first work by Castaldo et al. In this line was using the speaker factors. Next, I'm highlighting here a system by Stevensham, which is Bayesian HMM clustering of I-vectors. And once again, here it would be estimating the I-vectors as a point math estimate of these short segments. But unlike the examples that I was mentioning before, the Bayesian HMM already wouldn't be making hard decisions for the clustering of I-vectors. It would already use some probabilistic assignment of I-vectors to the Gaussian mixture models. And next, I'm also highlighting here the system by Gregory Sell and Daniel Garcia Romero, this PLDA agglomerative clustering of I-vectors, which has been definitely set as one of the most standard baselines in the recent years. Next, and this might come as a little surprise to some of you, because I somehow introduced the diarization using factor analysis as a more advanced technique as compared to this clustering of I-vectors, but it was actually also introduced in 2008. The thing with this approach is that it was presented only working on some telephone data from NIST. So it was not tested on, let's say, a more standard diarization setup. And maybe it somehow people didn't notice it that much, and it was not that extended. So next, we have the Bayesian HMM software, which already was ready in 2010. But like I already mentioned, also, it was not linked to publication or officially released. So it had to wait quite a few years until it eventually came to light. And that was actually done for the first time by people from JHU again. Gregory Sell and Daniel Garcia Romero used it combined with their PLD agglomerative hierarchical clustering of I-vectors. So this is the first time that the algorithm was officially used. And actually, it was not properly described until several years later, in 2018, when we had our first publication describing properly the model, which was definitely done after quite some push from JHU people, because they were insisting that they wanted us to publish something so that they could finally cite properly in one paper. And this is how the full history of this algorithm somehow worked. But I also want to highlight here that in 2016 already some X-vector models started emerging, and this is going to be relevant for the slides that are coming next. So, like I said at the beginning, this Bayesian HMM diarization system was important for the first DIHARD challenge, and it was the main part or the main element of our system in the first DIHARD challenge. And what I'm showing here is how the pipeline of this system was for us. So what I have here is the different modules, and starting this would be the input utterance. I would go first through some pre-processing, some WPE in our case, then would have to use the Oracle VAD to remove the silence regions and stay only with the speech frames. Next, we would have the feature extraction. We would extract the MFCC features. And next, like I said, we need some initialization for our Bayesian HMM model. So we would already extract X vectors, and these X vectors would be clustered with agglomerative clustering, and the output of that system would be the initialization for the Bayesian HMM model. And next, we will have 2 extra modules, which did not give that much gain, but they were still part of our system, which are the overlap detection and the overlap labeling, and also some domain identification that was mainly used to detect the LibriVox files and to make sure that they were labeled with a single speaker. So this was our whole pipeline, with which we achieved this 25.06 diarization error rate. And the winners of the first DIHARD system were actually DKU. So I'm also drafting here what was the main system. And you can see that the pipeline is very similar to the one we had. The main difference between their system and ours was that they did not use overlap detection or domain identification modules. They actually tried some domain identification, but it didn't make to their final system. But otherwise, they also had this pre-processing of the input utterance, then they would use the Oracle VDET to discard the silent regions, the feature extraction, and then, as we did, they would also have the extraction of the X vectors, which they would cluster with this agglomerative hierarchical clustering, and that would be their diarization labels, and then they would refine those labels using BB resegmentation. So maybe some of you already felt there is some inconsistency also, that I said that our systems are different, but I'm calling here things different, these two modules. And the thing is that I guess we will never come into an agreement. We always say that we have to produce some system initialization for a Bayesian HMM. We consider that this is the main, the essence of our diarization system. Like I said, it can be even be initialized randomly, and it addresses the full diarization problem. So for us, this is the main component of the diarization system. But instead, for them, the main part is still the agglomerative clustering of the X vectors. And then what they do is use the VB just as a refinement. And to be honest, they do use less iterations than us in this refinement. And also, what made them much more successful than our system is that they definitely had much better X vector extractor system than ours. And this initialization is really relevant. So you need this to make the final system work to the top of the performance. In any case, they would achieve this around 26 points for diarization error rate with the agglomerative clustering of their X vectors, and the refinement would give them the 23.73 diarization error rate, which is another more than 2 absolute more points for the diarization error rate, which made them the winners of the challenge. So this is it for the Bayesian HMM model working on frame-by-frame basis. And the thing is that after DIHARD 1, we saw that the vectors could just not compete with the discriminatively trained X vectors. And it was important to use them at least to initialize the system. So we therefore look for a way of combining the discriminative power of the X vectors combined with the benefits of our Bayesian HMM model, which resulted in using this Bayesian HMM model to directly cluster the X vectors. So in this case, instead of using the I-vector-like model that I mentioned for the former model, we take the PLDA model and we build it into the Bayesian HMM to model the speaker distributions. And we decided to do this because the PLDA was very effective, was found to be very effective for the clustering of X vectors and also to discriminate between speakers. And in this case, the speaker-specific distributions are no longer Gaussian mixture models. They are single Gaussians with speaker-specific means and shared covariance matrices. And the speaker-specific means are again Gaussian with some global mean and the across covariance matrix. And this is merely this PLDA-like model, which actually corresponds to the PLDA model that is normally referred to as the two covariance model. So we have the same model and inference as in the original Bayesian HMM, but with a single Gaussian pair state, and now with the total variety matrix, the speaker means and the covariances initialized from the PLDA model pre-trained on a large amount of X vectors. And I should also mention something about the parameters of the model. So at the beginning, I talked about this P loop, the probability of to model the speaker terms, to just stay in the same HMM state or speaker model. But there are two more parameters of the model that are quite relevant to achieve the best performance. One of them is the acoustic scaling factor, or FA, which was introduced to counteract the assumption of statistical independence between observations. But we also have the speaker regularization coefficient FB, which is a regularization term penalizing the complexity of the speaker models, where a high value of FB results in the BB inference dropping more speakers. And for BB experts, these two latter parameters are introduced as a modification of the evidence lower bound. And what we do with them is to scale the likelihood of the observed feature sequences, or the Kullback-Leibler divergence, regularizing the approximate posterior distributions of the speaker towards the priors. Once again, I'm leaving here this only as a reference. I don't want to get much more deeper into the math. And the thing is that these parameters, what we do with them is usually tune them on the development set and use them like that for the diarization system. But actually, this speaker regularization coefficient is quite crucial to achieve best performance with the VBX method. And like I said, this second flavor of the diarization method was the core of the winning system in the second diarization DIHARD challenge. And I'm drafting again here what are the different models for this system. So we have some pre-processing of the audio, the Oracle VAD, followed by X-vector extraction, and then we would use the agglomerative hierarchical clustering as initial clustering. Once again, having these labels as initialization for the system proved to be crucial to obtain best performance. And then we'll have the Bayesian HMM working on X-vector level, this VBX clustering. And this year, we still use the HMM VB resegmentation on top of it, so just single iteration to refine these outputs. And we will have the overlap detector and the overlap labeling, which once again didn't give us much gain, but they were part of the system. And what we achieved with this system was with this 18.42 diarization error rate, which means about 5 absolute diarization error rate gain points as compared to the system winning the previous DIHARD challenge, which is quite a big gain considering that the first and second DIHARD datasets were compares about approximately the same files. There were not such a big difference between both evaluation sets. And next, I'm going to talk about this latest BHMM-related publication. So, like I said, it's called Bayesian HMM Clustering of X-vector Sequences in Speaker Diarization, Theory, Implementation, and Analysis on Standard Tasks. And here, what we did is to provide the derivation and update formulas for the inference of this simpler VBX model. So I said that the model, this model is just a simplification of the bigger brother working on the frame-by-frame basis. And actually the same model and inference and equations can be used just by modifying that. Instead of having this Gaussian mixture model, we would have a single Gaussian for the speaker-specific distributions, and it can be used like that. But the thing is that this simpler model is much more efficient, and all this inference can be done in a much more efficient way if you know how. So what we do in this paper is provide all these update formulas and the tricks to make the inference much more efficient. And also, we established new baselines in all Call-Home AMI and the DIHARD datasets with this VBX. And let me now talk about evaluation protocols. So when we came into preparing these results with the new VBX method, we encountered some problems on how to compare to the literature. So if I would ask here into the audience, how do people evaluate diarization systems? The thing that would come to mind to most of you, I guess it would be diarization error rate. Nowadays, there's also this Jaccard error rate, which was introduced by the DIHARD challenge, and with this, I would say, gaining strength. But still, the diarization error rate is the main metric to evaluate diarization systems. And I'm not going to get into much detail on how it is defined. I'm assuming that people here today know roughly what diarization error rate is. But I will just mention that is sum of the speaker error, the false alarm error, and the misfit error. But even if it's a quite standardized measure for evaluation, the thing is, do we use it with a collar? Yes or no? And do we evaluate overlap speech with it? Yes or no? And in the context of DIHARD challenges, the answers to these questions are easy. It's yes, we do evaluate the overlap speech, and no, we are not going to use any collar. So this is the most challenging setup. But when we come to evaluate on other data sets, things change. For example, when we look into the Call-Home results, You can see here that I'm showing results on different evaluation setups with color or without color, and with or without the overlap speeds. And you can see that most of the systems in the literature are grouped in this 0.25 color and no overlap, not evaluating the overlap region. And the reason for having most of the systems here, I would say, is twofold. First of all, Colholm was released as a dataset for diarization purposes on 2001. And in those times, the diarization systems were just not as good as the ones that we have nowadays. So it makes sense to ignore the more challenging regions of the overlap speeds and to consider even some colors around the speaker change points, just to focus on the core of the speeds and the main, to try to tackle the easier problem with them. Also, the usage of this 0.25 color, I'm assuming that it comes inherited by the assumption that the human labeling cannot be perfect. And I don't know if any one of you has tried to label files for diarization purposes. I have, and it is really not an easy task. To be able to define precisely where the speech starts or ends for some speakers is quite tricky, and trying to label overlap speeds is pretty much crazy. It's very complicated for human annotators to be able to do that. So in some sense, this color also could be trying to cover these human errors that the references could already contain. In any case, even though most of the works are already here, these new emerging technologies like the end-to-end approaches are already considering the overlap speeds. So there are some works which are already considering these overlap speeds and still inheriting this 0.25 color when evaluating the systems. In any case, in our modest opinion, we believe that the best way to evaluate the systems is the setup which is also used in DIHARD evaluations. That is no color and considering the overlap speeds. And the truth is that diarization systems nowadays are achieving performances that allows to move and even pushes to move into these more challenging scenarios. And even though the labeling will always contain errors, like I said, it's not going to be ever perfect. This just means that we will have some lower bound on these errors. We will never achieve zero error on diarization error systems, but that doesn't mean that we have to, by default, discard speeds that we could be evaluating. So that is our modest opinion once again, but let me just briefly comment on the results in the table. So I'm showing here different works in the literature, and I'm highlighting that the VBX method is simply outperforming all of these different approaches for the Colholm dataset in all the different configurations. So this is about evaluation protocols in general, but it actually can still get more complicated. So in the case of AMI dataset, this how do people evaluate does not reduce only to do people use a color, yes or no, or do they use overlap speech or not. For the AMI dataset, there's much more chaos than that. There's different types of audio. The AMI came with beamformed audios, mixed headset, or single microphones. And there's people working with AMI dataset use different partitions. They use different files for the train, def, and evaluation sets. And also they use different references. So the official AMI dataset came with transcription files for ASR purposes, and there's no official references for evaluating systems for diarization. So what people do is derive their own RTTNs from these transcription files, but there's no standardized way of doing it. So when we try to make a comparison, a fair comparison between our system and all the different works that we found relevant in the literature, we eventually came to this. So I'm not going to comment on all the numbers in this table. I just want to highlight a few things. So when we tried to compare with everybody, we eventually had to use 3 different partitions into train, development, and test audios to be able to do the comparison, use 4 different sets of references, these RTTN files derived from the ASR transcriptions, and use also different audio types. And of course, all these had to be combined with using different colors and considering or not overlap speeds to compare to the different works. And maybe what I would like to highlight the most from this table is this column that I'm marking right now, and is that all these works differ in the amount of scored speeds on the evaluation set a lot. So they can evaluate as little as 13,000 seconds to as much as 52,000 seconds. And this comes given by the fact that they are using different audios for this evaluation set. They are using different references, and they are considering or not collars and overlap speeds. And the thing is that you can actually find cross-references of this work. So people are not always aware that there's this mismatch on evaluation setups on AMI. So what we try to do in this work is come with a protocol that could be used for AMI. And we do highlight in the paper what are the differences with the ones that are found in the literature and why we chose to make something different to what was already published. And let me just summarize very briefly what we are using here. So we consider the AMI full corpus ASR partition for the trained eval and evaluation sets. And we direct our references as follows. So we consider all words as speeds, and we include them in the references. We take a well-defined, consistent, and conservative approach in which all vocal sounds are discarded. The reason for this is that very different sounds were labeled as vocal sounds in AMI, and maybe more importantly, not all vocal sounds were time labeled. So it was not possible to include them all in the references. So we just thought it would be better defined and more clean to just discard them all and consider only the words in the references. And this is also more consistent with the task of speaker attributed ASR. And next, another small processing that we did also of the transcriptions, it was that we precisely respected the timings given in the transcriptions, but the adjacent speaker segments or words of the same speaker were merged not to create false breakpoints. And let me illustrate what I mean here with this example. So I have here the phrase, I like apples but not bananas, and the transcription that would come from it, where it marks where each of the words starts and ends. And you can see here that I like and apples are just consecutive words with no pause in between. So we merged this into a single speaker segment. And the reason to do this is the way we evaluate the diarization systems. When we use diarization error rate, if a collar is considered, these breakpoints are considered as stopping points, and the collar is applied around them, which results in removing quite a lot of speeds, maybe unnecessarily. So that's why we decided to remove them. And in the case of using this zero collar that we, like I said, still believe would be the best choice, this processing has no effect at all. But still, we believe it's better to do the processing in case anyone wants to use the 0.25 collar. So this is it for the protocol. I want to also officially say again, thanks here to Leibny Paola Garcia and Herbredin for their feedback on this protocol, and also for being willingly adapting the new protocol into their latest recipes in Caldi and the Keynote Diarization tools. And these are our results with this VDX method with this protocol. So I will just comment briefly maybe that for the beamformed audios, when considering collar and overlap speeds, we have this around 4% diarization error rate in the evaluation set. If we consider the overlap, the error jumps to more than 3 times higher. And if we suppress the collar, there's still around 30% increment in the error. And if we consider instead of the beamformed audios, the mixed headset, as expected, these are easier for diarization, and results are consistently around 2% diarization error rate better for each of the evaluation setups. And next, I'm going to talk about our results with these techniques on the second DIHARD challenge. And as far as we know, there's no published results which are still outperforming the system by BUT that was sent to the presented in the challenge. So nobody still, as far as we know, we did this 18.21 diarization error rate. And actually, the system that we use in this publication is still 18.55, so it's even slightly worse than that. And the reason for it is that in this publication, we used a single system for all Clova, AMI, and DIHARD datasets with no adaptation at all. So the only thing we do is tune the parameters likely on the development set of its dataset, but we do not perform any adaptation to the development set like we did on the challenge to really boost performance to the best. So that's the reason why these two are is still a little behind this performance. And that is it for the second DIHARD. And let me just now briefly comment on the third DIHARD results. There's one line missing here that I just realized. And like I mentioned at the beginning of the talk, our VBX baseline for this second DIHARD system would have achieved in this evaluation 17.25 Diarization error rate in the core condition. And our submission this year by the BOT team achieved 15.46, which means 2 absolute points in the gain in the Diarization error rate. The VBX was actually one of the components of this submission of ours this year, but the gains mainly come from other tricks that we did during the evaluation, but I'm not going to make any spoilers. Anyone who wants to learn about what we did for this challenge, please listen to the talk that Federico has to give later on. But still, the winning system of this DIHARD challenge is another 2 points ahead of us, achieving this 13.45. And I know that by the time this talk is released, most likely all of us will know what this system is. As for now, I'm just really eager to learn what the winning system is about, what do they do, and really eager to learn from them. And also let me mention maybe that we know that some of the systems that still perform better than ours are using VBX as a component of their system. So we are happy to see that the VBX is still useful for their teams and that they find it useful to even maybe use it better than ourselves. And this is it. So showing here a summary. The Bayesian HMM systems have been consistently the best or among the best performing systems in the last years from Diarization tasks. And despite their weaknesses, because this system does not do any overlap handling, which I believe is going to be one of the main areas of research for the future Diarization systems. Also, our system requires an external VAD. And the VBX has, for example, no frame precision, and unluckily we didn't win the third DIHARD challenge with it. But we believe that the method is still competitive. It is a strong baseline and or an important component that can be used for fusions. And we recently, like I said, established new baseline results in Clova, AMI, and DIHARD datasets with this VBX method. We provide a new evaluation protocol for AMI dataset, which we hope can become a new standard. And I just really, I thought I could use this platform to reach all of you because I thought there couldn't be a better way of mentioning this between all the Diarization community. Please, if anyone has any feedback actually about this, we are happy to hear from others if they think the things could have been done differently or improved. We are really happy to hear from all of you. And also, all the code from this VBX recipe is made publicly available once more. So the recipe for training the vector extractors for 8 kilohertz and 16 kilohertz is available. We also released the already trained vector extractors used to achieve these numbers that I have been showing. And we provide the full pipeline for applying the BB-HMM Diarization. And as future trends, so from now on, we will still seek of ways of combining this VBX with other embeddings. We know that there are other embeddings more powerful than the ones that we have been using. And like I said, the initialization of X vectors is crucial to make the VBX system work as well as it can. So this could be a way to boost performance. We also will seek a way of combining the benefits of the frame-by-frame BHMM and the VBX, because there's still something that we are missing with this later VBX approach. We are not having the full frame precision with it. And maybe in a more abstract way of thinking, we would like to still seek of ways of dealing with overlap speeds also with this method or combine it so that with something else, so that we could also deal with overlap stitch with it, and also maybe combine it with some end-to-end approaches to also get the benefit of these new emerging technologies, which we believe that eventually will be really crucial for diarization systems. And that is it. I'm leaving here some resources in case anyone wants to learn more about the things that I've been mentioning before. So the math related to the full Bayesian HMM with eigenvalue priors, a related talk, the derivation of the method with the introduction of the fetch factors, and the different open source codes corresponding to the two models. I'm guessing that the slides will be shared with everyone. So here you have all the extra information that you could need, and the rest of the slides are just references of all the different works that I have been mentioning. So thank you very much. I will be now ready here for answering any questions, and I guess that also my colleagues Federico Landini and Lucas Burguet would be available to give even more insights than the ones I could provide in case of needed. So thank you very much.
Thank you again. We thank Dr. Mireia for an excellent talk on all the latest and greatest in the VBX technique and perspective results on various data sets. That was really exciting to know all the results and the research happening in that domain. So we have about 3 to 4 minutes. So many of the questions I see that Dr. Diez has already been answering them in the chat. So she's also here with us. So any other extra questions that we may have, we could directly ask her. And yeah, here she is. We can also talk to her to take the questions directly. So I see a couple of, in fact, only one question on the open questions that you haven't answered thus far. So the question is about the real-time factor of VB versus VBX, and the additional comment that can this be used for online diarization?
So it is not straightforward to use it for online diarization. Like I said, we have to initialize the model of with an upper bound on the number of speakers. So if we would also use it in a online fashion, we would still have the first stream of it. And if we have there set the number of speakers, there's no straightforward way of adding new speakers into the HMM model. So we still haven't considered this kind of extension, for example. And
okay, yeah. So there's no additional questions that I see. So I had a couple of questions. Being the host, I can take the honors. Now, thanks, Mireia, again for the nice talk. So one question was that some of the gains that we were seeing on the diarization error rate were not translating on the Jacquard error rate for the VBX over, let us say, the prior VB approach, or even over the AHC sometimes. So is there any comment that you have on why that was happening? Or
actually, we are eager to learn why is this happening. So we saw this effect for the first time in the box convert challenge. That the errors in the diarization error rate and Jacquard error rate would not correlate between also development and evaluation, so they would be diverging. And we saw it again here in DIHARD, and we haven't been able to analyze much on it because we basically are still lacking the evaluation references. So this would usually, we would see it mainly on the evaluation set, and we haven't been able to analyze it, but we are very curious on why is this happening.
Okay, yeah, because I think the Jacquard error rate, I guess, also cares about non-uniform speaker, distribution. Essentially, every speaker is considered equally. So that may also play a role, kind of, in whether all the speakers are equally, getting improved.
Yeah. So just jumping in here quickly, I imagine in both Vox Converse and DIHARD, maybe some of this might be. I imagine if we did a breakdown by domain in DIHARD, for instance, we might see the divergence is greatest for meeting speech, web video, and restaurant speech, where you have the highest average number of speakers, but a small number of those are actually dominating the conversation.
Okay. Yeah. So one more question I had, again, this is not to put you on the spot. You certainly, I saw a short answer from you on the chat. This is on regarding how to handle overlaps inside the VBX itself. what are your thoughts? And if even the results are not successful, what could one think of in moving, and what has been your experience with it?
Well, we basically have been like thinking of how to implement it. It's not that we have done that much with it. We try some post-processing, like considering different, like first make one run of the diarization to get the different speaker models, and then considering how to use these like 2 speaker models to make one for the overlap speech and try to use it as a post-processing or next run of the VDX, but we were not successful with that. We could eventually think also on introducing some HMM states that would be directly modeling the overlap. But the tricky thing here would be we need to have X vectors that are also representing this overlap speech. And it's not clear if we can also extract X vectors that are representing this overlap speech, and that would be transferred into the model. So we have, let's say, ideas on it, but nothing that we will be able to already plug into the pipeline.
Maybe some of these end-to-end embeddings, which might also incorporate some information about the overlaps, because they're trained with kind of activity-based, loss functions.
Definitely, like I said, also as in the conclusions, we could eventually combine it with other kinds of embeddings that would be maybe more affordable, like useful for this kind of processing of the overlap.
Yes. So I see a very huge comment from Sanjeev. I'm not even trying to read it in the interest of time. But what we could do is, can we have Sanjeev speak the comment? Sanjeev, do you want to raise your comment as an audio question so that we could get the response faster? So can one of our organizers help to unmute Sanjeev? Certainly, we can't go into the break without answering Sanjeev.
Hey, no, that's can you guys hear me okay now?
Absolutely. Please come in.
I actually wrote earlier back to Mireia's answer to my earlier question, and I think she just repeated something that I was going to say, or she said something I was going to say. There are 2 issues with making this whole thing a unified good model. One is that if you want to fold in VAD, the X vector extractor is not trained to distinguish speech and non-speech. So we should throw in non-speech as a special speaker, speaker 0, and see if that helps. And the other one is that the basic HMM formulation with 1 speaker per state, I think Mireia, what's the name? We were all thinking about having states to represent overlaps. Another way, because that unfortunately has the problem that you have to choose all possible overlaps, otherwise make some assumption that at most 2 people overlap and so on. Another way around it might be to use tied mixtures, where speaker states have private Gaussians for that speaker plus share Gaussians with other speakers for overlaps. It'll make a mess of the VB approximation, but I don't know, maybe there's a hack. So I was just suggesting that somebody could look at it. I'm not saying we are looking at it right now. We have some ideas, Mireia has ideas. So I think we'll figure this out in the next few weeks, months, years.
Hopefully.
So excellent. So thanks everyone. Thanks Mireia for an excellent talk. So what we'll do right now, as per the schedule, is to have another break, a coffee break, a lunch break if you are in that time zone, or even a beer break if you are in some other time zone. So let us try to catch up in 10 minutes roughly for the next set of open oral talks, and followed by the second keynote that we'll have. So see you in about 8 minutes or so.
Okay. So I hope everybody had a nice, relaxing break after Mireia's excellent talk and is ready for our second oral session of the day. In my case, this is our second oral session in the morning. Some of you, this is going to get in a bit late in the evening, but we're almost to the halfway point, so just hang in there. The first presenter of this session will be Wei-Qin Wang of Duke University, who will be presenting their talk entitled System Description for Team DKU-Duke-Lenovo. And if we could play that video.
Hi, this is Wei-Qin. Today I'm going to talk about our system for the DIHARD third challenge for Team DKU-Duke-Lenovo. So this is the content. We will introduce the dataset first, then we will talk about each model in our system, including VAD model, speak embedding model, the attention-based model, and the target speaker VAD model. Finally, we will present our experimental result for evaluation set. So here is the statistics on the dataset for this DIHARD third challenge. As you can see, there are 11 domains in the dataset, and some of these domains contains a very high ratio of overlapping speech. But the most important difference between DIHARD second and DIHARD third is that we have the conversation telephone speech, the CTS data, this year. So this data contains only 2 speakers and is originally at the sample rate of 8 kilohertz, but it was upsampled to 16 kilohertz. So we break up this data into 2 small data sets. One is CTS and the remaining is non-CTS, which is at the sample rate of 16 kilohertz. It's quite easy to find the CTS data in the development set and the evaluation set, since the energies of 8 kilohertz data at high frequency are extremely low, so that we can find the CTS data, and we then downsample all CTS data to 8 kilohertz. So for our VAD model, it consists of a ResNet 18, a global average pooling layer, and a 2-layer by STM. Finally, a linear layer with sigmoid predicts the frame level speech likelihood. Our model is directly trained on the development set, and we use 90% of the data as the training set and the remaining as the validation set. So due to the limitation of the training data, we also use Musen and IRS corpora as the augmentation method. The result on the training set and the validation set doesn't show a big gap, so that we can believe that the model is not overfitted. And here comes the speaking embedding model. So the architecture of our speaking embedding instructor is a ResNet-based model, and the model architecture and the training strategy is the same as the first paper. The model consists of a ResNet 34 and a global statistic pooling layer, a linear layer that predicts the 128-dimensional speaking embedding, and finally the arc phase as the classifier predicts the speaker. So the training set is VoxLab 1 and 2. First, we train the model on the sample rate of 16 kilohertz for non-CTS data, and then we downsample the training data to 8 kilohertz and train another model for CTS data. So the Musen and the IRS corpora are also used for data augmentation. Then for the clustering model, we have two models, and one is for non-CTS and one is for CTS. So for non-CTS data, we use the attention-based model that to predict the similarity between each embedding, and the training strategy and the model architecture is similar as this paper. So first, the data is split into uniform segments during training phase. We use a length of 1.5 seconds and a shift of 0.75 seconds. During testing or inferring phase, we use a length of 1.5 seconds and a shift of 0.25 seconds. After that, we extract speak embedding for each segment and compute the similarity matrix S for each recording. To do so, we construct an input sequence MI, which consists of several speak embedding from a set of continuous segments, like from x1 to xn, and then for the ith row in the similarity matrix SS, so the Si, we can generate it by feed the sequence into the attention-based model. Here, Xi is the ith embedding, and the output is the probability that if Xi and X1 are from the same speaker for this first entry in Si. So, or you can say that this is the similarity between these two embeddings. So, then after we generate each row from Si to S1 to Sn, we can obtain the similarity matrix S. But since we construct the matrix row by row, and so this matrix S is not a symmetric matrix, so that we have to employ some post-processing like symmetrization, diffusion, and normalization to smooth the matrix. Finally, we perform spectral clustering on the matrix to get the final diarization result. And so this is the model for non-CTS data. And for CTS data, we use another system, which including the agglomerative hierarchical clustering and the target speaker voice activity detection. We will introduce the AHC first. We first employ a uniform segmentation with length of 0.5 seconds and a shift of 0.25 seconds on the speech region. Then we extract speak embedding for each segment and merge the consecutive segments if the cosine similarity of these two consecutive segments is greater than a predefined threshold, which is similar with the Microsoft system for VoxLab speaker recognition challenge last year. Since there are only two speakers in the CTS data, we can cluster all segments into two clusters, and the center of each cluster is the mean of all speaker embeddings. The stop threshold is 0.6, which is a high value, but we don't aim to get a low DER, so we just want to find the speech region without overlap for each speaker, so that we can use this cluster, use segments in this cluster as the target speaker's speech. But for comparison, we still assign the remaining segments to each cluster. But this time, the center embedding are fixed after we stop at threshold of 0.6. And an overlap ratio of 0 is employed that if the cosine distance between the speak embedding of a segment and each center embedding is lower than this overlap threshold, we consider it as an overlapping segment, and it will be assigned to each cluster. So after we obtain the target speak and target speak speech and embedding, we can use target speak VAD to obtain the diarization result. We only perform TSVAD for the CTS data. The model is very similar to the model in these two papers, the personal VAD and the TSVAD for the KIM6 challenge. But the training strategy and network architecture are slightly different. First, we only detect the speech region, which means that the task becomes a binary classification instead of a trinary classification. Another difference is that we use ResNet 34 to further extract the frame level speak identity information. And this figure shows the structure of our TSVAD model. First, ResNet with a fully connected layer extract the 120 28-dimensional frame level speak identity vector, which is the same as our speak embedding, and then the target speak embedding is concatenate to each frame of speak identity vector as the input of the BySTM. Finally, a fully connected layer with a sigmoid predict if a frame contains the target speaker. So during the fine-tuning phase, we use the first 41 recordings as the fine-tuning set, and the remaining 20 records as the validation set. Finally, for inference, some post-processing on the output are employed to get the final diarization result. First, we perform 11-tap median filtering on the output of the network. Then we find the target speech by a predefined threshold of 0.65. Note that we only perform TSVAD on the speech region, so some frames may be misclassified as non-speech because the output of each target speaker is lower than the threshold. So we choose the speaker with larger output as the target speaker for these misclassified frames. And this is a result of our system on the development set that for the non-CTS data and CTS data. So for CTS data, for non-CTS data, the DR is 16%, and for CTS data with agglomerative hierarchical clustering, the DR is 15%. And after training with TSVAD model, the DR become 10.6%, and after fine-tuning, the DR become lower than 8%. And this is the first round result. Then we extract each speaker's embedding from this first round result and feed it to our TSVAD model again to get the second round result. And it shows that the DR also decreases in the second round, but it no longer changes in later round in our experiments. This is the result of our system on the evaluation set. For track 2, we didn't submit this system, so we only present the result for the second system, and our team ranked the 4th place in both track 1 and track 2 on the full and core set. Thank you.
Sorry for the delay there, lost my cursor. If our speaker could, thank you, and bring up your slides as well. Do we have any questions? It looks like we have about 5 or 6 minutes for any questions regarding this submission. I see we've already been answering a few in the chat window.
Okay, can you see my screen?
Yes, I can see your slides.
Okay.
Right, so if there are no other questions currently, I do have a question. Did you try, in addition to having distinct models for CTS and non-CTS, trying model trained on everything that made no distinction?
We also have tried to train a TSVAD model on the non-CTS data, but it doesn't work. The reason may be that we don't know the number of speaker, and the recordings contain so many noise. So this target speak VAD model doesn't work for non-CTS data, and we also tried the attention-based model for CTS data, and the result is similar to this AHC-based result. So they are very similar. So we do not try more system on this data.
Okay, there are a number of widespan speech domains in DIHARD that almost always have exactly 2 participants. So one thing you could do would be to look at the various interview domains, the data from YouthPoint, the broadcast interview, the clinical interview domain. That might cause issues for you for other reasons, since those are children usually between 12 and 16 years of age, and some of the younger ones can have very abnormal productions, but it might still be interesting.
Yeah.
Oh, I see we have another question. So we have, can you give a few more details regarding the tricks you use to make TSVAD work with X vectors?
What guess what?
So the question verbatim is, can you give a bit more details on the TSVAD, the tricks you use to make it work with X vectors?
Okay, so we first for each recording, and let me see my paper, and then for each recording, we first we only perform TSVT on the speech region that we first use the Oracle VAD and convert it to the index array, and use this VAD index to extract only speech region, and our experiment only perform on the speech region, and we ignore the non-speech region. This is the first, and the second is that we use AHC for the target speaker speech extraction, and we believe, and for the first round, we use the target speech as the obtained by AHC as the input, and so and the learning rate, we first the second is the mixture speech is randomly select from 4 seconds and to 20 second speech as the input of ResNet 34, and this is the target speech that we believe that there is no overlap speech in this speech, and for the training parameter, hyperparameter, the learning rate is set to it's very slow, and is about 0.0001 is the learning rate, and we use SGD, and these details will be provided in our system description. Also, the loss is binary cross entropy, and for fine tuning, the learning rate is set to more lower. Yes, and this is and this is our training hyperparameter, and that's all.
This is just standard SGD.
Yes, standard SGD. And
okay. Right, we have about another minute if anybody else wants to jump in with a question. If I don't see anything in the next, say, 30 seconds, I will move to the next talk.
Okay.
Okay, well, thank you for that talk. And let me just restart my timer here. So the second presentation in this oral session is the UST-NELSLIP Systems for DIHARD 3 Challenge, which will be presented by Mireia He of University of Science and Technology of China. For everybody who is interested to see what the winning submission to DIHARD 3 was doing, this is the talk you should be watching. And if we could start, press play.
Hello, everyone. Now we are here to present the USTC-NELSLIP systems for the DIHARD 3 challenge. My name is Lei Sun. I will be with Mireia He to bring you this talk together. This page shows all the participants in our team. The submitted system represents the joint efforts of everyone presented here. Before diving into the details, we first describe our motivations here. The pain point in DIHARD can be summarized into two categories. One is about the overlapped speech, including detection and assignment. This is the largest cause for performance degradation. The other one in DIHARD is about its diverse environments, including telephone, cafe, street, and other things like speech in the wild. Such complex data put forward a high demand to the generalization ability of Diarization system. Hence, we mainly propose two ideas to address those problems, including iterative multi-stage strategy and domain-dependent processing methods. In this page, we illustrate the whole system design. For Diarization, we use three different kinds of methods to solve the problem. The first one is a traditional clustering-based system. The second one is our proposed iterative speech separation-based system. The last one is the iterative target speaker VAD-based system. We also use several auxiliary techniques like audio domain classification, speech enhancement, overlap, and some ASR-related information to further enhance the overall performance. Note that the dotted lines in the figure are used selectively, depending on the domain classification results. Next, I may introduce Mireia to show the details of each part.
This is Mireia. Let me first introduce the audio domain classification part. Here we use ResNet-based network with 17 convolutional layers to classify 11 domains. The whole development set was divided into 10 parts, 9 parts for training, and the rest for testing. During testing, we use voting strategy to get sentence-level classification results. The proposed model achieved 100% accuracy on the development set, and we directly applied it on the evaluation set. The classification results were used as prior knowledge for subsequent domain-dependent processing. We employed a progressive multi-target network-based speech enhancement model as shown in the picture. PELPS1 refers to progressively enhanced log power spectrogram and target layer 1, and the progressive increasing SNR between two adjacent targets was set to 10 dB. The enhanced speech was applied on restaurant domain with loud background noise, and it was also used for all domains of track 2 SAD. In this page, we introduce clustering-based Diarization system, which acts as a basic system for our overall framework, as shown in the picture. This system mainly based on X-vector, PLDA, AHC, and VB clustering. The results on track 1 development set are shown in the table. We can see that given Oracle VAD, the mixed value is the largest part in the whole DER, indicating that the traditional clustering-based Diarization system cannot well handle overlapping speech. To get more accurate label of overlap regions, we solve speaker Diarization via speech separation. We can see great similarities between the two tasks. Successful speech separation can yield good Diarization result. Hence, we propose a novel speech separation-based framework for the speaker diarization task. And seeing the figure, the framework simply contains two parts, separation and detection. In separation part, original waveform is separated into two single speaker channels. The existing speech part will be captured by a SAD model in detection part. After combining all SAD results along the time axis, speaker diarization results will attend where overlap region will automatically labeled. However, currently, the generalization ability of speech separation model is not guaranteed. We show two real examples here, which are taken from CTS domain. The left is an example of successful separation. Two speakers of the speech are clearly separated. The overlap regions are actually labeled, while in the right, the separated results are messy. Speakers are not correctly separated. The blue box indicates those regions which should belong to speaker 2. To improve the generalization ability, we propose a multi-stage training method. In the first stage, we added a fine-tuning procedure using speaker price, which could be drawn from the classroom-based diarization system. Though the prior data are not pure and clean, it's still enough to do fine-tuning. After it, we directly use the fine-tuned model to separate the original recordings. What's more, we also found that using better price to simulate training data can significantly improve the separation model's performance. So we use the diarization results obtained from our separation-based method to return the separation model in second stage. Such an iterative processing method can further improve the diarization performance. Here is the experiment part. In pre-trained stage, we use the library speech dataset to simulate 250 hours data and train the convertlet as our pre-training model. In fine-tuning stage, we simulated 5,000 mixed audios for each session to train session-level models. The results of iterative speech separation-based diarization are shown in the table. Compared to the traditional method, ISS-based methods significantly improve diarization results on CTS domain of development set. We also utilize the TSVD-based method. Original TSVD take MFCC and I vectors of each speaker as inputs and predicts speech probabilities for all speakers simultaneously. This makes it possible to handle overlapping speech. With the well-matched training data on CHAM6, TSVD obtained great improvement compared with classroom-based diarization system. However, original TSVD can only process sessions with a fixed number of speakers. Obviously, it cannot be directly used in scenarios where the number of speakers is changing. Besides, TSVD does not perform well in the mismatch domain, indicating its poor generalization ability to diverse environments. This slide shows our strategy for dealing with a session where the number of speakers is not fixed. We first remain the original TSVD structure and set the number of speakers output to 8. Note that the session in DIHARD 3 have no more than 8 speakers in most cases. When the number of speakers was greater than 8, we randomly select 8 speakers for training and select 8 speakers with the longest voice for decoding. When the number of speakers was less than 8, we randomly picked speakers from the training set, and then marked these selected speakers with silence for training, and discard them after decoding. In order to solve the problem of mismatch between training and testing set, we proposed an iterative strategy for TSVD called iterative TSVD. Firstly, we decode the TSVD pre-trained model with I vectors extracted from the classroom-based diarization results. Then we removed overlapping segments detected by TSVD from clustering-based results and used the remaining non-overlapping segments to simulate multiple speaker dialogue data for TSVD fine-tuning. Finally, we used the vectors extracted from the non-overlapping segments to decode the TSVD fine-tuned model and generate the iterative TSVD derivation results. Please note that we fine-tuned TSVD pre-trained model for each session. Here is the experiment details of iterative TSVD. The vector extractor was trained on voxelable 1 and 2, augmented with threefold speed perturbation. TSVD model was trained on real recording datasets, including switchboard 2, AMI meeting corpus, VoxConverse development set, and simulated multiple speaker dialogues with neighbor speech. And we also simulated about 4 hours multiple speaker dialogues for each session to fine-tune. TSVD pre-trained model only performs better than classroom-based derivation on well-matched domain like CTS and meeting corresponding to switchboard and AMI M20 set. Iterative TSVD helps improve generalization ability on most domains except web video and restaurant, mainly due to the large number of overlapping speech and noisy environments. As mentioned before, we got several derivation systems, including classroom-based derivation, iterative speech separation-based derivation, and iterative TSVD-based derivation with different priors. We first perform system fusion with the overlap of above results, and then use the results of audio domain classification. We chose the best system for each domain according to the development sets. We also detected laughter with ASR and assigned laughter segments to each neighborhood speaker. This gave a slight performance improvement. Here is the DER of each system on development and evaluation set of track 1. We achieved a huge improvement with the mentioned method, which helped us ranking first on both full and core set of track 1. For track 2, most sub-modules are the same with track 1, so we put more efforts on the SAD part. We employ 3 different networks for SAD, that is DN, CLDN, and TDN. All the 3 models were fine-tuned on enhanced development set and tested with enhanced evaluation speech. Finally, we voted from the 3 systems and got a fusion SAD results. Here is the DER of each system on evaluation of track 1 and track 2. Our system shows its effectiveness even without Oracle SAD, which helps us ranking first on both full and core sets of track 2.
Okay, in this page, on behalf of our whole team, we want to express our appreciation during our journey in speaker derivation. Thanks for people who hosting and inviting us to great JSOT workshops from 2017 to 2020. Thanks for all organizers and contributors in DIHARD Challenge series who provide a great platform. 2020 was a tough year. We wish all colleagues can stay healthy and happy in the future. Finally, we list some take-home message here. First, iterative multi-stage processing is important. Also, speech separation is an interesting and promising direction to help derivation task. Last, compared with using an unified method, domain-dependent strategy is very useful for data like DIHARD. Thanks.
Okay, we have about 5 minutes for questions. If the presenter could turn on their video and bring up their slides. I see we already have several questions in the queue.
Okay, can you hear me?
I can hear you, yes.
Yes, thanks.
Can't see you, but we can hear you.
Okay.
All right, good.
You see me? Yeah.
Yes. So if you could bring your slides up, I'll have a look at the question queue. So the first question, how is the speech selected for generating training data during the fine-tuning process for the SS-based diarization?
First, we use the price to remove overlap regions and get the speech of each speaker in the current utterance. Then we randomly select two speech segments belonging to different speaker and mix them to generate the training data of the separation model. Yes.
Okay. We have another question, which is, did you try to apply the separation on for the conditions other than conversational telephone speech?
Yeah, we have tried it on the other domains, but I found no significant improvement relative to the baseline module due to the effective loss and the number of speakers, maybe. Yes.
And that was, did you try that on the development set? Did you evaluate its effectiveness on the domains independently or just when used on all domains together?
We just tried on the development set, but found it's not worked on the other domains. Yes.
Okay. Another question we have here is regarding the use of simulation data. So does increasing the amount of simulation data during the fine-tuning process improve your model's performance?
Yes, we have tried to simulate more training data. For example, 10,000 mixed videos, voice in a fine-tuning stage. But the performance is not significantly improved. So we just use the configuration in this slide. We only use 5,000. Yeah.
Okay, so you also tried with 10,000 though, you said, but there was no improvement.
Yes.
We have another question about the TS-VAD setup. So how did you get the different priors for your iterative TS-VAD?
As mentioned here, we got the non-overlapping speaker segments by removing overlap speech from clustering-based diarization. We also tried clustering-based diarization on the detected non-overlapping segments to improve the prior accuracy. It's useful in some domains, but in most domains, it doesn't work. Besides the iterative TS-VAD outputs and the iterative speech separation results mentioned before for CTS domain, we're also talking as price for second stage TS-VAD fine-tuning. Yes. And we use this system to do the overlap.
Okay, so Shinji has a question about so are you going to make this system publicly available, either the whole pipeline or the individual components? And if so, will you release a open source tool and a recipe for replicating your results on DIHARD 3?
Yes, we plan to make it public available in the future. Yes.
Okay. Let me just clean this up. I think we have time for one or two more questions. So one last question I see in the queue. For separation, do you always train on 2-speaker mixtures, or did you also consider single speaker mixtures or mixtures of more than 2 speakers?
We only train it on the 2-speaker mixtures and never tried other situations. Yes.
Okay, so I'm going to ask, we have more questions, but I do have one. what is the time for the real-time factor for this system? So about how long would it take to process an hour of recordings?
In our pipeline, we focus on the performance. We didn't care the times. Maybe in my experience, maybe it takes 10 minutes for each session fine-tune in GSVD. But in the whole pipeline, I think it will take several hours to complete the whole decoding part. Yes, because yes.
Okay, thank you. Well, that just about wraps up our time for this talk. It's a great talk. Thank you so much, both you and Lei. And moving on to our next talk. The third talk of this session will be presented by Prachi Singh of IIS. Her talk is titled Leap Submission for the third DIHARD Diarization Challenge. And if we could press play on the video.
Hello everyone, I am Prachi Singh. I am a PhD student at Indian Institute of Science, Bangalore. I will be presenting about the systems developed and the results obtained by our LEAP team in third DIHARD challenge. This is the outline of the presentation. I will start with introduction. Then I will explain briefly about our proposed systems with block diagram, followed by experiments and results. Then I will end with the conclusion. Let's begin with the introduction. DIHARD-3 dataset has a mix of narrowband and wideband speech recordings. In the development set, there are 24% of recordings which are narrowband with 2 speakers in each recording. As the narrowband contains telephone dataset, which is a separate domain, we build a narrowband wideband classifier for separating wideband recordings from narrowband. Therefore, we use combination of models optimized for each band. On the right side, we see the overall scheme, details of which will be covered in the next section. I will discuss details of each block used in our system in this section. In the overall scheme, the first step is the band classifier. It is a 2-layer neural network with 512 dimension X vectors as input features. These are extracted every 5 seconds using segments of duration 10 seconds. Output of the network classify between 2 bands using majority voting of the segment-wise prediction. If the band classifier detects the recording as wideband, we use wideband X vector PIC system. This system is inspired by multi-stage baseline system as shown below. First, it takes input audio and divide it into short overlapping segments and then feed it into a embedding extractor, which is a time delay neural network. Output of this extractor generates features which are also called as X vectors. These are used to compute PLDA score metrics, which are used to perform clusterings. The output of the clustering generate a speaker label for each of the audio regions called as the diarization output. Here we focus on 2 important blocks in our system, which is embedding extractor and clustering. Now I will focus on the embedding extractor. In our experiments, we used 2 popular architecture. First one is the eTDNN or extended TDNN architecture, which has 30 layers. It has 22 frames temporal context. Adding extra TDNN layers before pooling layer helps to increase temporal context compared to baseline TDNN model. The second is the FTDNN or the factorized TDNN, which has 14 layers. It has total 32 frames of temporal context and it replaces the pre-pooling layers by a factorized TDNN. The FTDNN reduces the number of parameters of the network by factorizing the weight matrix of each TDNN layer into the product of two low-rank matrices. And the 12th layer affine output are the X vectors. Details of these two architectures are given in the below mentioned papers. Now after getting the X vectors, we perform PLDA score computation and then perform clustering. Next I will discuss details of clustering algorithm. We use path integral clustering or PIC. It is a graph structural based agglomerative clustering algorithm where graph encodes the structure of the embedding space. Given a set of vectors x from x1 to xn, it involves creation of directed graph G as shown on the right side, where V is the set of vertices corresponding to the samples in X, E is the set of edges connecting the vertices, and we compute a weighted graph adjacency matrix W, which is given in the slide, where Sij is the pairwise similarity between Xi and Xj. And to make the matrix sparse, we only take k nearest neighbors of Xi, which are used finally for the affinity computation. Right side shows a graph representing 5 clusters with different colors. There are connections between vertices within cluster as well as across cluster. PIC uses path integral as a structural descriptor of cluster. It is a sum of all possible paths of all possible lengths within each cluster. High path integral indicates more stable cluster. Therefore, it encourages merging of cluster towards higher stability. Like AHC, PIC also merges two clusters at each time step based on maximum affinity. Affinity between clusters CA and CB is given by the equation on the slide, where SCA is the path integral of cluster CA. SCA given CA union CB is the conditional path integral of cluster CA, which is nothing but sum of all possible paths in the CA union CB cluster such that the starting and ending vertices must be within CA. The difference between these two terms is called as incremental path integral of CA. Here is one sample example of merging process. Here we see cluster A and cluster E are represented by orange and blue color respectively, and the two terms in the affinity are represented in the two blocks. The first rectangular box shows incremental paths in cluster A highlighted by pink color. The starting and ending vertices are in cluster A. The second rectangular block highlights incremental paths in cluster B in green color. This shows that higher affinity indicates higher path integral, which thereby indicates dense connections between the two clusters to be merged. Output of the PIC system generates speaker label for each of the X vector segments. For further refinement, we introduce another block which performs VB-HMM and overlap detection. Refinement of segment boundary is done using the popular variational based hidden Markov model along with posterior scaling, which is introduced by our team in the second DIHARD challenge. We also do overlap detection using module in Keynote Audio Python toolkit. The segments identified as overlap by the detector are then used to refine the segment boundaries obtained after the VB-HMM based on the posteriors. If the band classifier detects the recording as narrowband, we use a different strategy which is based on transformer-based end-to-end system. The architecture of the model is like the self-attention EEND with the encoder-decoder based attractor calculation. Input is 23-dimensional log-mel filter banks with a context of ±7 frames. The overall block diagram is shown on the right side. It has 4 stacked transformer encoder blocks. Each block consists of 256 attention units with 4 heads. It is trained using permutation invariant loss. This completes the full description of all the systems used in our approach. In this section, I will discuss the training and evaluation procedure along with results. For embedding extractors, ETDNN and FTDNN both are trained using VoxelLab1 and VoxelLab2 datasets for speaker classification of 7,323 speakers. A separate PLD model is trained for ETDNN and FTDNN. For SAEEND, we simulate 100,000 two-speaker mixture from SpeechWord2, SpeechWord Cellular and previous NIST SRE datasets. It is trained for 100 epochs using PIT training criteria. As narrowband contains two-speaker telephone recordings, we adapted the model on call-home subset containing two-speaker files. For evaluation of wideband X-vector PIC system, for both tracks, we perform the following steps. We extract X-vector from 1.5 second segments with 0.25 second of shift. We consider cosine scores and PLD scores to compute similarity between segments. To compute the scores, we follow the same pre-processing steps as used in the baseline setup. We experiment with different clustering techniques like AHC, path integral clustering. The number of speakers is generated using the PLD-AHC by finding the best threshold on the development set. For track 2, we use the pre-trained SAD model from baseline setup to generate the speech segments. For evaluation of narrowband end-to-end system, we downsample audio to 8 kHz and pass it to model to generate frame-wise posterior. We subsample the frame level features by different factors to avoid abrupt speaker change and reduce memory competition. And we predict at least one speaker based on maximum posterior probability and then apply threshold on posterior to detect presence of more than one speaker. Finally, we remove the silence frames using the ground truth SAD for track 1 and pre-trained SAD for track 2. These are the results for the track 1 development set of the DIHARD. First table is the wideband ETDN system configuration. The first row is the PLD plus AHC approach, which gives a DER of 20%. And when we apply PIC instead of AHC along with PLDA, we get 1% absolute improvement. We also tried cosine plus PIC, which also gives slight improvement over the PLD plus AHC approach. Next row shows the baseline with PB results, which is 19.95. And when we apply our approach, which is PLDA plus PIC, along with the VB overlap, we get a significant 3% improvement over the baseline. The second table shows the narrowband system configuration. We experiment with two versions of the SAEND model. V1 is the subsampling by 10, where we obtain frame level posterior at every 10th frame, and V2 is subsampling by 5. Baseline is the baseline for only the narrowband system by forcing the number of speakers to be 2. And we see a significant improvement in the DER as well as JER for the narrowband system using the EEND model. This graph shows average domain-wise DER comparison for wideband development set. X-axis represent the 9 sources from the development set of the wideband, and the y-axis represent the average DER for each of the source. The orange color represent the PLD plus AHC output for the ETDN and X vectors, and the gray color represent PLD plus PIC output for the same architecture. We can see the performance of the PIC is better in almost all of the domain compared to the AHC approach, except 2 domains, which are RT04 and youth point. That is because for 1 or 2 files which performed very worse in these 2 domains. This table shows results of our combined systems for the full and core set for the track 1. We have 2 variations in the wideband PIC system based on the TDNN architecture. We get around 24% relative improvement over baseline for dev and eval full sets for both the approaches. Here we show results for track 2. We use the SAD model from the baseline for speech segments and use the track 1 setup to generate RTTMs. We get around 22% and 18% relative improvements for dev and eval full sets respectively. Finally, I want to conclude by saying that we proposed a combination of narrowband and wideband diarization system. The end-to-end system is found to perform better for two-speaker narrowband recordings. The baseline framework is optimized for wideband recording using better speaker space embeddings, ETDNN and FTDNN, and novel path integral clustering scheme. The ETDNN and FTDNN are found to have similar performance, and system combination at the score level improves the overall DR only marginally. Thank you. For any question, you can reach me at practicing@isc.ac.in.
Okay, thank you, Prachi, for that great talk. If we could get you to turn your video, great. And maybe bring your slides up. So do we have any questions from the audience? We have about 5 minutes for questions for this talk. Okay, so I'll ask, did you, all right, great. Did you explore any additional approaches to refinement of the outputs of your system?
Refinement after the clustering?
Yes.
So we have actually used VB-HMM itself, and we also tried a VBX approach, but like eventually when we do the combination of refinement with overlap detection, we did not find improvement by changing the refinement technique. So that's why we stick to the VB-HMM approach.
Okay.
Yeah.
And I sorry, I left the room briefly while you were presenting. I missed what data is the overlap detector trained on?
Overlap detector, actually it is a pre-trained model, and then this is a Python toolkit available, and then it is adapted on DIHARD 2 dataset.
Okay.
Yeah.
Okay, so that's probably like an AMI model or something that was adapted.
Yes. We also tried to use E&D model for the wideband setup, but because of the it was trained on the 8 kilohertz and the DIHARD was 16 kilohertz, and when we tried to simulate, it was taking a lot of time, so we could not finish the training of that properly. And also the overlap detector which we tried to use from the E&D setup was little worse, like it was worse than this Keynote audio. So that's why the final system we have not mentioned that E&D.
Okay, and we have another question, it looks like, regarding the VB overlap. So just asking what your actual detection accuracy was for the overlap detection component.
The overall detection, like I actually have the results, but it's not like I don't remember exactly, so because we have tried a lot of combinations, so
yeah.
So
well, if that was
the exact results actually.
Okay, so I'll table that for the moment. There's another question, which is how did you estimate the number of speakers for PIC clustering?
So yes, like I mentioned, just to go to that slide. So actually we have used the threshold based criteria on PLD plus AHC and find the number of speakers using those that base threshold on dev set. and then use those number of speaker for the PIC as well.
Okay. Paula asks, did you do any special treatment for the CTS data or the new clinical data that was added this year?
Special treatment, as in I didn't get the...
Yeah, Paula, I'm going to request you to unmute. Allow to talk, okay. Could you ask that question live? You should be able to unmute yourself now, Paula.
Sure. Hello. So I was just asking if you have a special treatment for the CTS, because we know that there are like different domains, and CTS is 8 kilohertz. And if you like do any special thing for it, and also for the clinical data that we know that we have a lot more this year.
Yes, actually, what we did is we have separated like our approach using this band classifier. So we have trained the band classifier on the X vectors, and then the output of this will detect like whether it is coming from telephone recordings or it is any other domain. So the CTS domain, once we classify, then we use the narrowband E&E approach for that. So we downsample the CTS once detected as narrowband and then apply it to the narrowband system.
Okay.
And it really helped, right? Oh, sorry. Sorry.
Yes, yes.
Yeah.
We found a considerable improvement, like I have put it here. So it helped a lot. Yeah.
Okay. Okay. Thank you.
So thank you for that talk. That exhausts our time for questions. So we need to move on to our final talk from this session. Thank you, Prachi.
Thank you.
So the fourth and final talk from the second oral session is being presented by Kishore Kumar of IIT. Their talk is titled Domain-Dependent Speaker Diarization for the Third DIHARD Challenge.
Hello everyone, my name is Kishore Kumar. Today I am going to deliver the presentation on the topic of domain-dependent speaker diarization for the third DIHARD challenge. This work is the submission from the team Audio and Biosignal Processing Laboratory, Indian Institute of Technology, Kharagpur, India, for the task 1 of the challenge. Generating timestamps with respect to the speaker labels from a spoken document is known as speaker diarization. In earlier studies, rich transcription researchers mainly considers audio recordings of broadcast news, telephonic conversational speech, and meeting data. With the rise in multimedia content over the years, more variety is observed in the recording environments of the spoken documents. Thus, instead of a one-size-fits-all method, a domain-dependent speaker diarization approach might cater to the diverse and challenging recording conditions in a better way. Figure below shows the difference between all-domain diarization and domain-dependent diarization approach. In our submission to track 1 of the third DIHARD challenge, we propose a simple but efficient method for acoustic domain identification using speaker embeddings. Next, we show that the domain-dependent threshold for speaker clustering helps to improve the diarization performance only when probabilistic linear discriminant analysis adaptation uses audio data from all the domains. Additionally, experimental optimization of PCA parameters in a domain-specific way further improve the diarization performance. The proposed acoustic domain identification system built upon speaker embeddings, drawn from sentence-level features, and nearest neighborhood classifier was used. These speaker embeddings are capable of capturing the background acoustic scene, recording session, and channel information, though they are principally developed for speaker characterization. In this work, we considered two frequently used speaker embeddings. One is discriminatively trained X vectors, and another one is generative I vector. The block diagram shown below illustrates the proposed acoustic domain identification system. The development set consists of 254 speech utterances from 11 domains, and the experiments were performed by randomly selecting 200 utterances for training and the remaining 54 samples used for the test. For similarity measurement between the training and test data, cosine similarity was employed. 1,000 times we repeated the experiments and obtained an average accuracy of 71.39% for X vector based system, and for I vector based system we got 90.81%. The comparison of ADI performance of the two systems shown in figure 3 shows that confirms that I vector system is substantially better than X vector system for ADI on DIHARD-3 development dataset. In the subsequent experiment, we have used this system for identifying the domains of the individual evaluation data samples. Our experimental setup is based on baseline system created by the organizers of this challenge. We have used toolkit with the same frame level acoustic features, embedding extractor, scoring method, etc. To extract utterance level embeddings for the ADI task, we used a pre-trained X vector and I vector model trained on X voxelab audio data. This figure shows the block diagram representation of the experimental setup we followed for this work. In the first experiment with the baseline system, we analyzed the diarization performance for each domain and noticed that the performance varied with the domains, as is expected. Next, the diarization experiment was separately performed with each domain. Interestingly, this degraded the performance compared to the baseline. This is more likely due to limited speaker and acoustic variability in the domain-specific subset, which is also used as in-domain target data for PLD adaptation. Hence, we propose to apply a domain-specific threshold for speaker clustering, but PLD adaptation is performed with audio data from all 11 subsets. The baseline system used recording-dependent PCA during PLDS scoring, where 30% of the total energy is preserved during dimensionality reduction. We experimentally optimized this value for all the domains separately, which further improved the diarization performance. In this slide, we have shown the results for development data considering two domains, clinical and court. The system is built on domain-dependent threshold and PLD adaptation with full data, along with domain-dependent parameters for PCA, shows a relatively good performance with comparison with the rest of the methods for both clinical and court domains. Now, in this slide, we have shown the results for entire development data for baseline and proposed M1 and M2 method, where M1 method is domain-dependent threshold and M2 method is domain-dependent threshold along with domain-dependent parameter for PCA. Here also we can see that M2 method performs better than the rest of the two methods. For the evaluation data, we performed domain-dependent diarization on the evaluation set by first predicting the domain for every utterance, followed by the grouping of the utterances according to the predicted domains. We used a domain-specific threshold for speaker clustering and the percentage of the total energy for dimensionality reduction optimized on the corresponding domain of the development set. Results summarized in Table 3 indicates substantial improvement over the baseline and the M1 based method. In this work, we explored domain-dependent speaker diarization and integrated an acoustic domain identification with the baseline system on the third DIHARD dataset. Our ADI system is based on I-vector embeddings and nearest neighborhood classifier. We selected domain-specific thresholds for speaker clustering and used domain-dependent PCA parameters for dimensionality reduction during PLDA scoring. The PLDA adaptation was performed with audio data from all the domains. For our proposed method, 10% relative improvement was observed with respect to the baseline system for both the conditions in track 1 of the challenge. The work can be extended with advanced embedding extractor based on ResNet, extended TD, NN, etc. I would be glad to answer any question now. Thank you.
Thank you, Kishore. We can get you to turn your video feed on and unmute. It looks like we have about 7 minutes for questions, if there are any questions from the audience about this wonderful talk. All right. Oh, great. There are the slides. So I'm looking at the queue. I'm not seeing any questions in the queue yet. Maybe I could start off and ask, have you done any preliminary experiments with any other speaker embeddings? You appear to, oh, I see we still don't have you. Right.
Sorry, am I audible?
Yeah, I can hear you
Yeah,
now.
yeah. We haven't applied any speaker embedding other than this one. We used the baseline itself only.
Okay. Right, and let me take a look at the slides again. Can you bring your slides? Can you share video and bring your slides up? I'm going to take a look. I have a local copy. I'll bring those up too, but.
Yeah.
All right. Yeah, so. Okay, yeah, so you retained, so basically you retained the majority of the baseline system outside of the domain specific processing. So the refinement stage, for instance, and the clustering stage are both identical and tuned identically?
Yeah.
Okay. Did you look at tuning any of the parameters for the VB HMM refinement stage? I know you don't present any, but I'm just curious if you did any other domain-dependent tuning experiments.
No, in the VB refinement, we haven't touched any parameter tuning there.
Okay.
Only PCA and the threshold method there, we tuned the threshold for clustering, and for PCA we adjusted the energy parameter.
And from your recollection, do you remember which domains the domain adaptation made the biggest difference for? I'm assuming from the development data.
Sorry, hello?
Yeah, sorry. Asking again, which domains did the domain adaptation have the biggest impact for?
Okay, for the domain identification or for the this one?
For domain-dependent adaptation.
For these two classes, that clinical and the classes that we have shown on the slides, the clinical and the court, we have seen the things.
Yes. Was it harmful for any of the other domains?
For some, like web videos and meeting, we have seen the good improvement, and for the other domains like restaurant, and we don't get a good thing. I mean, a substantial improvement.
Okay, so it is variable.
Yeah.
Oh, Paola asked a question. How do you decide on the domain-dependent threshold?
We empirically change the value of the threshold domain-wise, and then we got the better result on the development data for that particular domain, and then we selected that threshold.
Okay, so it's tuned using the development data.
Yeah.
Okay. We have time for maybe a couple more questions before we break for 10 minutes. I'll leave the floor open for maybe another minute or so, and if not, I'll break early. We've been at this for a while now, so I imagine everybody wants some time to stretch their legs, and perhaps get some coffee. Okay, in that case, I'd like to thank everybody for making it all the way through the second of our 3 oral sessions. As I said, we will be reconvening in 13 minutes for our second keynote, which is scheduled to start at 16:20 UTC. I hope everybody is able to show up for that.
Hello.
Hi, Paula. Hi.
How are you?
I'm good. How are you? Good to see you.
Yeah, good to see you too.
So, all right. So, welcome back, everyone. So, this is Sriram again from India, enjoying a cup of Indian chai. It's almost about 9:50 p.m. here in India, but certainly enjoying the sessions and feeling very good about it. So I am again honored to introduce the second keynote session. So this is talk is going to be provided by Dr. Leibny Paola Garcia Perera. I hope I got all the pronunciations at least almost right with my Indian accent. So Paola has a PhD from the University of Zaragoza, Spain in 2014. She has joined Johns Hopkins University, or we did not overlap, I believe. Certainly, I think I left much before 2014. So she joined Johns Hopkins Research, John University, after extensive research experience in academia and industry, in highly regarded labs in Ag initio, as well as in advanced communications. She has led 20 plus researchers from 4 of the best laboratories in worldwide in far-field diarization, speaker recognition, and also under the auspices of the Johns Hopkins Summer Workshop 2019 in Montreal, Canada. She has been in the past a researcher at the Tec de Monterrey, Campus Monterrey in Mexico for 10 years. She was a Madame Curie researcher for the IRIS project in 2015, exploring assistive technology for children with autism in Zaragoza, Spain. She has been a visiting scholar in the Georgia Institute of Technology in Carnegie Mellon, and she has been working on recently in the child speech, including recognition of child speech, diarization of day-long recordings, pretty much very challenging domains and interesting problems of research. He has also led and been part of the JHU Time 5, Time 6, and SRE 18 and 19 teams. Her interests include diarization, speech recognition, speaker recognition, machine learning, and language processing. And Paula, I also had a chance to briefly look at the talk and the slides that were available as recording. I'm really looking forward to it. Excellent job anyway in putting this together, this recording, and we look forward to your talk. So the organizers, could you kindly load the talk?
Hello, my name is Leibny Paola Garcia Perera. I am an assistant research scientist at Johns Hopkins University. Today, it is my very great pleasure to be presenting a talk on diarization. So let's go to it. The title of this presentation is The Yellow Brick Road of Diarization, Challenges and Other Neural Paths. First of all, I would like to thank all our collaborators. I really want to thank each one of them. You have made this work possible. From JHU, all the speech team, students and faculty. From Hitachi, Yusuke and his team. From CMU, Shinji. From NTT, Mark and Keisuke. From NTU, Susie and her team. And some other collaborators around the world. I have a disclaimer of this talk. I know that there are a lot of fascinating works that are not in this presentation. Apologies in advance. I chose the ones in which somehow I have been involved or have closely followed the research. So sorry. Technology is like a tornado. It abruptly changes our reality and takes us to different adventures. And in this case, Dorothy was the chosen one. And let's see where she got. We have arrived to the world of speech technologies with lots of devices from which we can gather data. But once we have all of it, how to make it useful is one of our goals. The first thing that comes to our mind might be that we need to categorize this data to find a way to label speakers or events or the things happening in those recordings. Labeling the recordings by speakers so that the output can serve other downstream tasks such as speech recognition or other related technologies is the main task. In this example, we have 3 speakers in a meeting having a conversation. So we should be able to label all of them. And for tagging these speakers, we need diarization. Diarization answers the question, who spoke when? Let's have an overview of what diarization does. So we have the speech signal, and the first thing to do is to get rid of the silences. For that, we use what is called a voice activity detection. After the voice activity detection, we can have a speaker type classification. We can decide whether it is a device or a real person. We can also search for the gender and classify between adult and kids. Afterwards, we can tag each of those speech segments and decide which ones belong to the same speaker. In our example, we have 3 speakers. Well, the overall process makes sense up to now. But how can we test the diarization systems? The most common metric is the diarization error rate, composed of summing up the false alarms, the misdetection, and the speaker confusion divided by the total time of speech in the recording. The false alarm is the duration of non-speech mistakenly classified as speech. The misdetection is the duration of speech incorrectly classified as non-speech, and the confusion is the duration of speakers classified as another speaker. Another metric is the Jacquard error rate. To compute the Jacquard error rate, for each reference speaker, we sum up the false alarm and the misses, divided by the union of the segments of the reference speaker and the hypothesis of that speaker. The final Jacquard error rate is the average of all the reference speakers' Jacquard error rates. Now that we know how to measure the diarization, let's take a look at some numbers. These are the diarization results for different subcorpora from the challenge. In the first graph, we have the results for the first DIHARD using an energy VAD. This was one of the first evaluations in which the corpora was heterogeneous, coming from different domains. As shown, the wildest domains got the worst results. Now let's constrain the problem and let's try to get the best results considering I have a perfect voice activity detection. Those are the results for DIHARD-2 best system and DIHARD-3 Hitachi and JHU solution. It is consistent for the 3 evaluations that the worst cases occur for the data like child-centered speech, VAST, which is YouTube videos, and restaurant scenarios. We know how to do diarization. We know the yellow brick road of diarization. This is the current pipeline that we follow. The boxes in blue are the ones that are optional, but in our brick road, it's mandatory to have the yellow ones. So we have an enhancement to denoise the speech signals. Then we have a voice activity detection to get rid of the non-speech parts. Then we have the embedding extraction to convert the speech into a mathematical representation that preserves the relevant information of the speakers. Then we have a scoring stage in which we establish similarity measures among those embeddings. Afterwards, we do the clustering where we group together segments that belong to the same speaker. As optional stages, we have the resegmentation, that is a refinement of the speaker boundary regions. And if we want to go fancy, we can apply an overlap assignment, that is to detect the regions where we have more than 2 speakers talking at the same time and assign labels to it. Finally, we can get the RTTM, which are the labels of the complete recording. Now, at super fast tornado speed, Let me go through all of them. Enhancement. There are lots of denoising techniques. Today, I just want to point out two that gave improvement on previous diehards. The first one is WP, the weighted prediction error, to mitigate the reverberation. And the second one is the progressive multi-target network-based speech enhancement with signal-to-noise ratio preselection for robust speaker recognition. As shown in the figures, this approach is able to clean the signal from very high noise. Now, let's talk about the voice activity detection. We are considering that we don't have noisy condition. The recent most successful approaches include a neural network at some of their stages. For example, the neural network voice activity detection includes a SyncNet, a couple of LSTMs, and fully connected ledgers to give an output of speech and silence. On the other hand, we also have a hidden Markov model TDNN voice activity detection that consists of TDNN ledgers and bidirectional LSTMs. The posteriors obtained from this DNN combination are then post-processed using a hidden Markov model. Treating the frame posteriors like emission probabilities, we can apply a Viterbi algorithm and obtain the most likely label sequence. Let's talk about the embeddings. It is true that the better the embedding network, the better the performance. So we can see in the left graph that the extended TDNN got good results. But if we included augmentation, we can even improve those results. And also recently, the Microsoft team supports this claim by adopting a REST-to-Net as part of their main architecture for the Box Converse challenge. The scoring. Now that we have the embedding, we need a way to score them. The most popular method is probabilistic discriminant analysis. This method combines intersection variability and scoring all together. The idea of PLDA is to obtain a similarity matrix among all possible segments. Let's jump to the clustering. After the similarity matrix, we can group the same speakers using what is called agglomerative hierarchical clustering. And then at this point, we are ready to compute the RTTMs. But wait, agglomerative hierarchical clustering was good enough until the variational-based hidden Markov model clustering arrived. You can clearly see the difference in improvement. These are the results for the DIHARD 2 with agglomerative hierarchical clustering and the BBX. So BBX arrived to change the story. Mireia already explained the BBX clustering. But just to recap, the input to this system are the X vectors. And in the figure, each hidden Markov model represents a speaker, and the state transitions correspond to speaker terms. The state distributions or emission probabilities are single Gaussians. You can also notice that each speaker has a probability of P-loop, by which the hidden Markov model ends up back in the same state. With this approach, we can easily handle X vectors or any other embedding and produce speaker labels. We use the BB algorithm to infer the speaker distributions, the number of speakers, and the speaker sequence. For the resegmentation, we use the same idea as the BBX, but in the input, we have MFCCs at frame level. We can also observe the loop probabilities, and we have a GMM for the state distributions. We use, once again, the BB algorithm to infer speaker distribution, the number of speakers, and the speaker sequence. Now let's jump to the overlap assignment. Perhaps these architectures sound already familiar. They are exactly the same as the ones used for the voice activity detection approaches. But now they are trained in a certain way that the output is overlap, non-overlap regions. Both approaches are quite competitive. And finally, the overlap assignment. Once we have the posterior probability matrix from the BB resegmentation or the BBX, and by using the output of the overlap detector, we can assign the two most probable speakers to those overlapping regions. And well, the yellow brick road seems quite useful, but it has some issues. We are still trying to handle overlapping speaker. The system is not designed to minimize the diarization error, but optimizes every module independently. So as good engineers, we look for solutions. And the first that comes to our mind is, what about a fully neural path? That means a single DNN with a single optimization stage where the input is speech, or perhaps speech features, and the output are the labels, or perhaps speaker posteriors. But what about something in between? Because at first glance, the idea seems too risky. Let's try something first. This is our first trial towards end-to-end. The region proposal network-based speaker diarization was one of the first trials. It was inspired by the region proposal network used in image processing. The main idea is to find regions of objects and tag them accordingly. For example, in the picture, there are some labels for persons, dogs, known monuments, cars, etc. And the way to do it is to extract some feature maps from the picture using a set of convolutional layers. Then predict the object boundaries. After this, on the left side of the diagram, the region proposal network iteratively selects a bunch of proposal regions with redundant information. It serves as the attention of the network. On the right side, the network computes what is called a region of interest pooling. Both information, the proposal and the region of interest, are then used by a classifier. The output is the picture with all the labels. Well, this sounds good, but is it possible to use it for diarization? The answer is yes. It is the same idea, but only in one dimension. So one neural network that outputs region proposals. Each of these region proposals contains speaker information that can be easily processed by different backends, so that in the end, we can get an RTTM. Let's tackle the region proposal network for speaker diarization. The first stage is to compute the STFT of the signal and process it using a set of convolutional networks to obtain a feature map. The feature map is then sent to two branches. The first one is the region proposal branch. In the region proposal branch, the algorithm defines a sliding window and a set of anchors. Taking each anchor as the center, the system expands n times with predefined sizes. The anchors represent possible speaker segments with various sizes at different locations. These regions are inaccurate and redundant, so there is a regression layer that can adjust the timestamps, and a classifier which can distinguish between high quality and non-high quality segments. Those ones are referred as foreground and background segments. The output is a set of curated region proposals. The other branch goes directly to an algorithm called region of interest alignment. This is a pooling stage in which we ensure that the fixed dimension features in the feature map really reflect the STFT and mitigate the effect of quantization. The output of the region of interest is passed again to a regression layer, a foreground background classifier, and we include a speaker classifier from which we can compute the embeddings. The algorithm selects the speakers with highest scores. Then a non-maximum suppression model is included to get rid of proposals of redundant speakers. In a clustering stage, we use k-means, but it can be any other clustering algorithm capable of grouping the embeddings. Finally, we merge the regions of same speaker segments and obtain the final RTTN. The way to control this huge pipeline is with the following losses. The classification loss that decides if the speech segment is foreground or background. The regression loss is a smooth L1 loss to regress the central point and the length of the speech segments. The speaker classification loss that classifies the speaker identity of the speech segments. Some results on DIHARD show that we are getting closer to the best system. Now that we feel more comfortable, let's take a look at the end-to-end approaches. The idea of neural diarization is to design a neural network that can do the job in an end-to-end manner and can replace our previous modules. This is exactly what end-to-end neural diarization is trying to do. The way to do it is to define the diarization as a multi-label classification. This multi-label approach is a predictive modeling task that involves predicting 0 or 1 or 2 classes or the classes that I need. I mean, you can assign mutually non-exclusive class labels. This is exactly what EN or end-to-end neural diarization does, transforming the problem into a multi-level classification problem. It is a single network with supervision. In the following slides, I want to highlight very briefly the evolution of this interesting approach. The first one is like a proof of concept. It focuses only on 2 speakers. During the training, the system calculates frame posteriors from a neural network and computes the binary cross-entropy loss using the frame posteriors and 2 permutations of reference labels. To prevent label ambiguity, the algorithm minimizes the permutation-free loss. That means it chooses the minimum loss computed by the binary cross-entropy. At the inference stage, the neural network computes the frame posteriors. Then a threshold is applied to obtain each speaker's activity at every frame. Finally, we can compute the speaker labels. In a second approach, a set of bidirectional LSTMs are used to obtain the frame posteriors. It is known that the middle ledgers of a neural network can extract embeddings, so the algorithm includes a training criterion based on deep clustering loss. So it can group together the embeddings that are speaker dependent, meaning speaker 1 or speaker 2, or overlap or even non-speech. The final loss function encourages same speaker embeddings to remain together in the same cluster or separate them if they are in different clusters. This approach can work for multiple speakers. The next improvement of the EN is to include self-attention. The bidirectional LSTMs depend on the past, future, hidden state, and the current feature. These bidirectional LSTMs are replaced by an attention layer that depends on all input frames. This encoder that is similar to transformer computes an all versus all frame similarity matrix. The encoder is similar to the transformer approach, but without positional encoding. As shown in the figure, the heads capture different characteristics. For this example, head 2 takes care of one speaker, and head 3 takes care of temporal dynamics. Now let's put all of them together. The first one for 2 speakers, the second one using the bidirectional LSTM with deep clustering loss, and the third one including the self-attention-based network. There is a problem with this EEN approach that it cannot handle variable number of speakers. The solution came with an encoder-decoder attractor. The starting point is a self-attention EEN from which we can compute the speaker embeddings. These embeddings are then fed into the encoder-decoder module. The LSTM encoder takes the embeddings and outputs the final hidden and sealed states that go directly to the LSTM decoder. The embeddings plus a sigmoid layer produces the posterior probabilities of every speaker, and finally the labels. Another method to solve how to deal with variable number of speakers is the speaker-wise change rule EEN. The main idea is that the activity of each speaker is estimated sequentially conditioned on the previous speaker's activity, following the change rule. It works as other sequence-to-sequence models with a stopping condition. So for the full audio, we first obtain the posterior probabilities, let's say for Dory. And that is our first condition, to obtain the posterior probabilities for Lion, and then for the Tin Man, until there are no other speaker activities. The teacher forcing with a modification is used in this approach to prevent label ambiguity. And now we have here some results on the DIHARD 3 dataset on track 1 and the Oracle set. We can see the evolution of the EEN. Surprisingly, the EEN approaches are very competitive, and even in some cases, better than the traditional systems. We are almost at the end of the slides on EEN. Let's talk a little bit about online diarization. Up to now, only a few papers deal with the online diarization. To give a result at a desired time unit is not an easy task, but a modified EEN can deal with this scenario. So let's say that we have a 10-frame chunk and we apply EEN. It can be EEN EDA or the speaker-wise EEN. Then we get some posterior probabilities for 2 speakers. We take the ones with higher probabilities because they are supposed to be of cleaner regions, and we generate a buffer. This buffer matches the probabilities and also the frames. We want to increase the number of speakers, so we append some zeros to our posterior probabilities. The second chunk comes with another 10 frames. The first stage is to append the buffer. and then apply EN. The solution again is a set of posterior probabilities for 4 speakers in this case. To prevent the label ambiguity problem among the chunks, we solve the permutation. Once again, we select the posterior probabilities buffer and match it with the frame buffer. We continue the process. As we can see in the figure, we have Dorothy as the first speaker, Tin Man as the second speaker, and Lion as the third speaker in the second chunk. And yes, more results on DIHARD 2. We have a comparison of the traditional systems and 3 options of online diarization. The proposed method is improving the offline baseline and is competitive to other methods. Another approach I want to mention is how to tackle the problem using our knowledge on source separation. In here, we have a neural network that takes care of everything. It is able to separate any number of speakers and mixtures in a recursive way. So we start with a residual mask or attention map and a spectrogram. The network pays attention to all the region and outputs a first mask. This mask corresponds to the first source. The residual mask is then injected to iteration 2, and it pays attention to the shaded areas. The same method computes a second mask corresponding to source 2. In the third iteration, the source 3 is obtained and the residual mask gets empty, finalizing the process. This procedure can be extended for different time steps, as it is the case for diarization, where we have multiple speakers talking at different times. Although the idea is the same, the method first splits the spectrum into consecutive blocks, and it includes a speaker embedding that is passed to the next block and guides the extraction of the mask of the same speaker. If the speaker does not appear at a given time step, the mask is 0, and the process continues until the residual mask is empty. The diarization error on simulated data is encouraging to continue exploring possible solutions in this direction. Now, are there ways to get the best of both worlds? Let's say part end-to-end and part embedding clustering? The answer is yes. Let's start with the EN vector clustering. This is an approach which was inspired by the EN and the clustering. Instead of just getting the posterior probabilities from the EN, we can get the embeddings. And with those embeddings, we can do clustering to prevent label ambiguity between different chunks. In the figure, let's say that we have 2 chunks and 2 speakers per chunk, although we have 3 participants. The encoder output is a modified EN, from which we can compute a diarization result. Let's choose Dorothy for the moment and obtain the posterior probabilities using a linear D1. Similar, we can compute the embeddings, linear S1, and perform a dot product between the embeddings and the posterior probabilities. We perform a time average and assign a cluster. A similar procedure happens for chunk 2, where the system chose Lion. We obtain a diarization result and the embeddings. The system performs the multiplication of the posterior probabilities and the embeddings and computes the time average. Now Lion goes to a second cluster. At the same time, the method does the same for the missing speakers. So now we get a point for a scarecrow and a new element for Dorothy. This happens iteratively until the process finalizes. The table shows an encouraging research direction using simulated data from liver speech. The proposed method with the chunking and the clustering gets better results for recordings of 5 minutes or longer when compared with the actual EN. Now let's talk about DOVERLAP. Inspired by Dover, we have DOVERLAP, a way to combine RTTMs that contain overlaps. The DOVERLAP has 2 stages, a label mapping that puts all the labels in the same space and the label voting that decides which regions get to the final RTTM. Let's say that we have 3 systems with 3 different hypotheses. We compute the tuple cost for all possible combinations. For example, this one, and then this one, and then this one, until we get a global cost tensor. Then we pick the lowest cost and assign the same label to it. And finally, we get the final mapping. For the label voting, we divide the RTTM into regions and estimate the number of the speakers in each region. We assign the highest weighted N speakers in each region and compute the final labels. There is another interesting approach that uses EN as post-processing. I cannot tell you the complete story because this is a spoiler. Let's say that we have a nice system. For example, the output of the embedding clustering coming from the BBX or the embedding clustering with agglomerative hierarchical clustering, but it contains no overlap. The main goal of the EN is to estimate those overlaps in the current sequence. The procedure is as follows. We take the 2 longest sequence of speakers, in this case, Lion and Tin Man. We apply EN that give us the overlaps. We solve for any permutation issues using our previous knowledge of the speakers. Then we get the next pair, Tin Man and Dorothy, excluding the parts already used by Lion. We apply the EN and we solve for any permutation issues. Let's go for a third round. Our pair is Dorothy and Lion. We exclude the frames that were processed before and apply EN. We solve for any permutation issues and we assign the final labels. As I told you before, this is a spoiler, but here is a kind of recipe. We get the labels from another system, can be the BBX or an agglomerative hierarchical clustering system. Well, then we apply EN. Then we solve for any permutation issue. And finally, we get new labels with overlaps. Now, more results. This is the summary of the different systems. Systems that take the best of both worlds outperform their predecessors. For example, TDNN plus BBX plus EN as post-processing outperforms TDNN, BBX plus overlap. The overlap that fuses all the previous systems gets the best of each of them. And it considers overlap as well. It gets the best performance so far. These results are very nice, but wait, what about the difficult example? What is beyond what we have known so far? What is beyond Diarization? In this slide, I'm showing you the results on 2 data sets that are focused on child-centered data. Well, the results are not very good. It can be because of the voice activity detection. It can be because of the annotations. It can be because of the overlap. But the truth is that the linguists and the cognitive science experts are waiting for all of us to really improve our error rates on these challenging scenarios. So we can see the best results with the Oracle VAD are around the 30s, and using VAD are around the 16s. So there is room for improvement. As an example, I can share with you 3 different recordings on this challenging scenario. And I remember that one expert told me, in real life, we don't have dev data. We only have eval data. So let's see. One that is not very crazy.
No, don't touch them. That is a calendar. I want to look. You want to look at the calendar?
Let's take a look at the second one, which is a little bit more challenging.
Baby, don't lick
and stuff.
That is
Stop.
You know what? I tell you, other kids touch this, and if they've got germs,
Then I say nasty.
it'll make you have some germies.
Nasty. Nasty.
And finally, one that it is super challenging.
It's here. Wait, Susan?
You will see. You will see. Here you go.
So now we can understand why the diarization error rates fall dramatically. Finally, the takeaways. There are lots of flavors of systems to choose from nowadays. We have huge improvements, but we are not yet there. Neural diarization is becoming as good as embedding clustering methods. Overlap detection is still an ongoing research. Diarization to help downstream tasks like ASR is a must. Day-long recordings, including child-centered data, cocktail party scenarios, need diarization solutions. Self-supervised learning for diarization can be a new research direction. Now let's see where the tornado brings us the next time. Thank you. Now we are ready for questions.
Excellent talk, Paula. Thank you so much for your contribution to the DIHARD workshop. We have about 15 minutes or so, quite some time for questions. So I see that you had answered some of the questions and comments. So we are certainly open for questions. If anybody wants to either raise their hands and get yourselves an audio question in, or you want to type it in, we are open for both sets of questions. So since we are waiting for the audience to ask any questions, let me use my opportunity as the host to ask you the question. So you mentioned about the, okay, so we had a couple of questions. So I'll anyway start off with my question and then get to that. So you mentioned about the region proposal network as well as the other end-to-end models. So do you have a comparison between the EE and D model style of using transformers with the image style of using the region proposal? Can you give any comparison between these two ideas?
You mean between the region proposal and the EN, right?
Yes, yes.
We have like a separate settings right now, but they can be compared. But from our experience up to now, it seems that EN is getting a little better results. Well, much better results than the region proposals. Yeah. So for the best system of our EN approach, it is around. Let me give you the exact number that I know. I'm just looking for it. But it's around 13% for this for the DIHARD 3. Yeah.
Okay.
And
So
it will take, I think, sorry, and I think it will take a little bit of time to really get the region proposal idea to work entirely on the DIHARD. The problem with the region proposal is that it cannot really tackle the different domains at the same time. So that is the main challenge for the region proposal.
So Brian McKinney is asking, I wonder how much labeled home bank data you might need for training in that domain.
Wow, that is a good question. Yeah, so right now in the systems that I have for child-centered speech, I am using around 20 to 30 hours to do the adaptation. But you know that the more data we have, the better, right? But perhaps around 50 hours of very curated data will be enough to at least have a competitive system. Yeah, I know that that the child center experts, the ones that do the annotation, are doing a very hard work trying to assess these huge data sets, because there is a lot of data. The problem sometimes are the annotations, that they have to be, that we as speech researchers are very picky sometimes, that we want them to be like single speaker, overlaps, and everything very, very, very curated. And sometimes that is not possible, at least for the child-centered data.
Paola, on that question, just how good would that have to be? Because I can tell you from experience with seedlings, trying to annotate that data to the unrealistic standards we set ourselves was like sometimes 35 times real time using a spectrogram and using 2 spectrograms at once.
Yeah. And I also think that we have to really reduce the gap between what we have and also what the linguists or the cognitive science people require. Because we know that we have the technology here, but how to really pass this technology to them, it's quite a challenge. And it has been quite a challenge for me as well. Yeah, but I totally agree with you, Neville. Thank you.
So moving on to the next question. So Omid here asks, how much is the real-time factor for the online diarization system?
I think if I remember it correctly, you can have, that's a good question. I'll tell you later, Omid, because I had the paper, but it is not bad for the online diarization. Yeah, but I don't want to tell you lies.
Okay, so I guess Paula will get back to you, Omid. So Sanjeev is asking a question. You know, he may be your neighbor there, but he's still asking through this platform. So he's asking a question. You have combined 4 systems. Have you tried to do an ablation study? Essentially, what he's trying to suggest is that you may not need all the 4 systems. You could, choose a subset of these systems, maybe get at least as good, if not even better, by combining a subset of complementary systems and not blindly combine all the things that you have.
Yeah. That's also why our team decided on this weighting modification to the overlap. So we decided to give more weight to the E-end approach and a little bit lower weight to the other systems, because we know that the E-end is better for almost all the conditions. Yeah. But yeah,
so a related question. Yeah, I had a related question. So suppose one system is pretty good at so-called finding the right number of speakers, and another system is perhaps good at getting the best DER. Maybe the systems that get the best DER not always get the best count of the number of speakers. So is there something in this overlap flavor that you can suggest, or is there further research that you can highlight, that how you can get the best of the both worlds?
Yeah, that is also possible. there are like many different ideas on how to go with the overlap. For example, as one of the proposed methods, the EEN with the post-processing, we get the best of both worlds, right? So we get the solution from the BBX or from other clustering algorithms, and then we pass this one to the EEN. And then the EEN is in charge of getting the overlaps in some sense and refining those boundaries. So in that case, you don't really need like the overlap itself, but it is like a cleaning stage, like a refinement stage on top of a very good system, right? And then using the overlap, of course, we can get the best of these different strategies just in one single result. Yeah.
So the next question moving on is in child speech scenarios, how can diarization algorithms be modified to accommodate the case of each person wearing a microphone? So I guess the question, I guess the question is that, if, in some scenarios where each speaker is also, wearing a headset or some sort of a lapel or some sort of an attached microphone, and you may perhaps be only recording the sounds channel. I mean, the question is from attendee. So if you want to rephrase your question, then
so having like multiple microphones, right?
Right.
Perhaps it's like having like multiple microphones in the same room and trying to decide, trying to do the diarization. I think that might help as well. But the challenge is to use like only a single microphone that is very close to the baby or to the toddler or to the kid. Yeah.
So how do you rate the so-called, because perhaps the most interesting is to separate the child from the rest, right? I mean, diarization full-fledged may not be the end goal, right? So I always wondered that, at the end of the day, you perhaps want only, child versus non-child.
Right.
So treating it even as a diarization problem, is it like, overcomplicating what the cognitive scientists really want at the end, or is it the right way to do it? I mean, I don't know. I'm just trying to wonder.
Yes. So for the linguists and the cognitive science people, they want both. They want the child vocalizations, and also they want the different people talking in the recording. So with this information, they can see how much interaction they have with the kid, how many different words or different vocalization the kid is having, and then they can perform other studies on language development. So that is the key idea. But they are just waiting for us to get like some good results. But it is true that if we give them results of around 30-40%, that is not good enough, right? So they will be carrying this error on all their further studies.
But the examples that you played, the child speech, spectrally, or auditorily, it feels very different from the adult speech, right? So is it the overlaps or the annotations? Where is the crux of it?
Yeah. The first one is just very good, right? You can really listen to the toddler talking at the very first, and then you can listen to the mommy. But that is not the usual case. Those ones are the first like 5 seconds. It gets like super crazy, right? And you know that you cannot. The kids, they are not collaborative. So you can have all unexpected noises in those recordings.
Yes, not only for diarization, in real life too, I can watch.
Yeah, that's true.
So Shinji here asks, it's a bit off topic. I'm curious, like the other speech processing areas, I would like to know some discussions about human versus machine. So do you have any comments? Are humans still better, or machines are approaching this?
Some discussion about human versus machines in the current stage. Do you mean like for doing the diarization stage?
Right. So I guess that's the question. So in diarization, do you think machines have caught up with humans, or humans are still better? Do we still have a chance, or no?
I think that for these challenging scenarios, humans are a little bit better. But what we are doing right now is, for example, we give the cognitive science people like a curated version of our diarization system that has some problems here and there, but that will help them to really get a better output. So our output passes through a second annotation stage to have to obtain a better labeling.
Yeah, just a related comment from our own research I can add to Shinji's comment is that we had tried a talker change detection, where there is a file where small snippets of audio, they either come from the same speaker or different speaker, and we did machine versus human, and we wrote it on a JASA paper. So what we found is that the machines are better than the worst human, but the average human results are slightly better than the machines too, just as you were saying. Yeah. So something of that nature. So any thoughts on combining multiple modalities? So I guess this is going towards newer research directions in diarization. Can we do audio video diarization?
That research direction is going to be like very, very, very interesting, and we are looking forward to it. Yeah, of course. Yeah.
So so why there is no current interest in this is actually a couple of questions around the same direction. Why there is no interest in multiple microphones or microphone arrays?
I think there is interest. So perhaps not in this DIHARD, but if we consider CHIME, the CHIME challenges, so they are focused on this multiple microphones. And the end task is speech recognition, but they usually have an initial stage that is a focus on diarization to do the task, to get rid of the non-silences, of a little bit of the to get like a curated version of the different speakers, and on top of that, then do the ASR. Of course, right now there are like different combinations as well, and there is also a very nice study that combines the diarization and ASR jointly, which is also very, very, very nice, and that can also work on multiple microphones.
So Sanjeev is following up on Shinji's question. He's saying that if we know how hard the problem is for the humans, then it may be difficult to even trust the so-called ground truth that is used for machine systems to learn on. So any evaluations become not so trustworthy if the human annotations or ground truth by itself is not so good.
Yeah. That's also
so. I mean, related to that comment, Sanjeev, we had also between Neville and ourselves for the next DIHARD challenge, we were mentioning where you can record. So surely, because the annotations by humans are getting trickier as we go into this complex acoustic environments. So in all this environment, we would need a close talking microphone for each speaker. That is the one that you give the humans for annotation, but you still want the machines to do well on the so-called far field or the remote microphone using the ground truth, so-called activations from the close talking. So in some sense, you want that superhuman sort of a feel.
Yeah. So following up on that, I've would have replied in the Q&A, but as a panelist, I can't actually reply on these without closing them, the questions. But I do actually, I think for a subset, a very small subset of seedlings, which is why I never did the analysis, have dual annotation from two people who were trained to use spectrograms. That's before we just decided the annotation was too expensive to continue with. Sort of informally, though, I think some of these tasks, specifically the child speech where it's recorded from a single far field microphone that's a wearable, it's very, very, very difficult for a human to do more than sort of gross things. Like you can kind of get an idea of how many children and how many adults are on the recording. And you can have like a general idea of where they are. But when you have 2 or 3 children whose voices are similar and background noise, and you have a single channel and they are overlapping each other, it's you have to do things that no normal person is doing to get the boundaries.
Yeah, I have some recordings where we have siblings and you cannot distinguish who is who. But also we also experience some difficulties in our diarization system when the parents are talking to the babies, because they instantaneously change the pitch. So for our diarization systems, they are actually 2 different persons. Just by changing the pitch and just addressing the baby. And it should be just like a unique person, but we are also facing that problem in our current, with our current data sets. Yeah, I think also-
So an opposite, Brian is also saying that, you could think humans can clearly detect when children are talking and overlapping. So so that, I guess the point that you are also making is that suppose there are multiple children in the given and recording, then it gets harder for humans and human annotators. So particularly they are similar in age and so forth.
That's entirely true. Yeah. So even, well, I know the mothers that they can detect their kids. Even if they are siblings, they have a very good diarization system. Yeah, but for our current diarization system, sometimes it's not that easy.
So Sanjeev is asking if there are any audience members who can vouch for human performance in speaker discrimination. They can identify themselves, and the chair will give them the floor. Surely we can, but Sanjeev, we are almost past the time for this session. Unfortunately, I really enjoyed these discussions also. So if there are, maybe one more, a question or comment from anybody who can identify and qualify Sanjeev's comment, then, if you can identify yourselves, we can give you the floor for 30 seconds or so.
Probably a good idea is to open the microphone to Brian.
Sure. Can one of the organizers get Brian's microphone on and have him?
I think I'm unmuted. I simply I simply am thinking of the case which is very common with one mother and one child. I agree that if there were 3 children, then all bets are off.
Right.
But and I mean, obviously, even the mother can't tell when there are 3 children overlapping with each other. It's just bedlam. But there is so much data that we would really like to look at in which there's one mother, maybe one father, and one child. And if we could just get that diarized, I think that would be a big advance. So I think the thing here is that there's training data is really missing. And because the children have such distinct sounds from the adults, you would think that would be easy from an intuitive human perspective. And I think the thing is that we just don't have the training data that will clearly pull these apart from the, Libra speech or all these other training sets that you've been using. That's my reaction, but I could be wrong.
No, exactly. I also totally agree with you. I mean, you feel that, even male versus female, you get, almost 100% classification by all these systems. A child versus an adult, should be, very close to 100% in classification. But, therefore, it's just the, if there is, the right amount of data, this problem of having just one child and, one adult, or at most, 2 adults of different gender should be, a problem that machines can solve.
Yeah, I'm also very sensitive to what Ryan was saying about the need for the very accurate boundary detection. And people are really not going to be able to do that very well with the, with their current sophistication, unless there were better methods and so on. I mean, they can do the best they can. And I wonder, does it have to be that accurate? maybe Ryan could explain why it has to be absolutely precise in order to make progress.
The very, very quick answer is that it doesn't. When we went into DIHARD 1, we didn't quite grasp just how difficult human annotation for the data would be, which is why we've relaxed some of those constraints over the years.
Great, great.
Okay, excellent. So on that note, we take this opportunity to thank Paula once again for the excellent session review of all the topics in diarization, and also bringing to the the fore of the discussion the the challenges in child diarization. I think this could be one of the key parts in future challenges as well. So thank you again, Paula, for the session. And as per the schedule, we'll take a thank you again. And as per the schedule, we take a quick break, about 5 to 10 minutes. I'm a little overboard in my own schedule by about 5 minutes. So if we can join back in 7 to 8 minutes for the next session, that would be great for the final oral talks. Thank you all, and see you soon.
All right. Okay, I think that's a long enough break. So I'd like to welcome everybody to the third and final oral session from this year's workshop. We have 3 presentations lined up in this final session. Thank you to everybody for sticking around. It's been a bit of a slog, I know, especially for those of you in Oceania and Asia, but just three more talks to go. The first talk in this session will be presented by Federico Landini from Brno University of Technology, who will be presenting the BUT system for the third DIHARD speech diarization challenge.
Hello, my name is Federico Landini, and I will be presenting the Brno University of Technology system for the third DIHARD challenge. So this is the system overview. As you see, there are different blocks. The first 4 here in light green are 4 different diarization systems. 3 of them are based on X vectors clustering, and then we have an end-to-end system. The outputs of these 4 systems are fused using the overlap, but since only one of them, the end-to-end, accounts for overlapped speech, then we still, after doing the fusion, apply overlap detection and overlap handling. Finally, we used a telephone channel detector in order to discriminate files that are telephone speech from the other ones. That is because the end-to-end system performed quite well on telephone speech, and for this reason, those files are only processed with this system, and the rest of the files are processed with the rest of the pipeline I just described. So let's go now into the details of each of the blocks. First, we have here BBX HT heavy tail PLDA. So this is the core of the winning system of DIHARD 2. So we released this recipe earlier and it does Markov model using those X vectors. This is named as VBX. And the difference in this system with respect to the recipe we released is that in this case, we used a heavy tail PLDA instead of a Gaussian one. Then we have VBX adapted. So again, we used VBX. The difference with respect to the system we use for box converse is that here we use the same trick we used for DIHARD 2, in which the PLDA is obtained as an interpolation of 2 different PLDAs. One of them trained on a large amount of speakers, but out of domain, which come from VoxCeleb, and then another PLDA that is trained on, let's say, in-domain speakers, but a smaller amount coming from DIHARD 2020 dev set. Then we have a spectral clustering-based system. So again, we use the ResNet 152-based X vectors, and they are clustered by means of spectral clustering with k-means. The affinity matrix in this case is based on cosine similarity, and the number of speakers is based on the largest eigencap. Then we have an end-to-end system that is based on self-attention and encoder-decoder LSTM-based attractors. This model was trained on artificially created telephone conversations, and for this reason is that the recordings are downsampled into 8 kilohertz. After that first training on lots of artificially created conversations, we still fine-tune it to real conversations coming from call home. The interesting thing of this approach is that eventually we have one output per speaker, and by using thresholds, we can determine which of the speakers are active. So for instance, if none of the speakers are active, basically we have silence, but it is also possible to have overlapped speech for 2 or even more speakers. In the way we use this system for the challenge is that we also made use of the Oracle VAD for track 1 in order to do some post-processing, so that every
time that the Oracle VAD says that there is speech, we always take the most likely speaker in the output of the system, and then we tune the threshold to find overlap, let's say to find other 2 or more active speakers in each moment. As I mentioned, the outputs of the 4 systems are fused using the overlap. The interesting thing about this approach is, well, after making a global mapping between the speaker labels across the different approaches, there is a weighted majority voting to obtain the final labels for the speakers. But the main interesting thing is that this approach can handle overlapping labels. The problem in our system is that out of the 4 systems, only 1 of them has overlapping labels. The other 3 that are based on X vectors do not have any. And for this reason is that still we wanted to apply overlap detection and overlap handling. So in this case, we used an overlap detector that uses encoder and separator of a COMTAS net. It was trained on DIHARD 3 dev set, box-converse dev set, and meeting data. Since the amount of overlap that appears naturally in these conversations is quite low, we still created some artificial overlaps using the single speech segments from these data. And after some segments are recognized as overlapped speech, we still use an heuristic that considers the closest in-time speaker to assign it as second label. Then, since the end-to-end system performed quite well on telephone speech, we still did telephone channel detection. So that was done using the average energy levels on the spectrogram. So using a certain threshold, we would classify recordings as either telephone, and in that case, we would only apply the end-to-end system, and for the rest, we would apply the whole pipeline as we described. So now that we covered all the different submodules, let's talk about results. So here we have results for track 1, the 4 systems in light green, and we have results for development core and full, and again, evaluation core and full. For the dev set, we not only have the diarization error rate, but also the 3 components, the missed speech, the false alarm speech, and the speaker error rate. And we see at first glance that the 3 X vector-based systems perform very similarly among themselves, both in core and full, and the same holds for the evaluation set. However, the end-to-end system by itself lags behind, so it performs quite worse, especially on the core condition. However, since it performs quite well on telephone speech and the full condition contains a much higher proportion of telephone conversations, then we get quite some gain with respect to the performance that we see on core, and that holds both for the dev and evaluation sets. Then when we apply the fusion, we managed to get some improvement over the best performing single system, roughly almost half a point of TR both on core and full. And we still see some gain on the evaluation set. Then when we apply the overlap detection and handling, we managed to push the performance further for the dev set. But here it's worth taking into account that part of the training data used for the overlap detection is indeed the development set. So it is possible that these results are too optimistic. In fact, when we evaluate the results on the evaluation set, we see that mainly for the evaluation core condition, the gain is very small. We still get quite some gain on the evaluation full. Finally, when we also use the telephone channel detection, we managed to improve the performance roughly by another half a point on the dev core, and roughly, well, in this case for full, it's 0.8, but it is almost 1 point on the evaluation full. And again, half a point on the evaluation core. In order to have as a reference how we performed in comparison to last year, the winning system for the challenge that used the DIHARD data, track 1 and track 2, was based on the VBX system that we proposed. And in this case, well, we used the recipe that we released earlier in 2020. So this system is not exactly the same system that won the challenge, but it performs very similarly. Although it doesn't have the overlap detection and the VB segmentation, when we released this system, it still performed quite similarly to that winning system, but we could compare it, let's say, with the first set of systems. And in this case, we get 16.9 DR on the dev core and 16.46 on the dev full. So we see that this system is slightly worse than the systems that we get this year, but still in the same ballpark. Mainly the gains that we obtain in the challenge this year come from the fusion and the overlap handling. In order to understand a bit more the results, we also analyzed the performance across the different domains. So here we have again the different systems, and here the results of DR for dev core, and then DR for the different domains that compose the DIHARD set. So as it is known in the DIHARD set, there are some domains that are clearly more difficult than others, and we see that with all our systems. Some interesting things to observe is that, for instance, the fusion with the overlap helps in, let's say, half of the domains with respect to the best single system, but in the other half kind of gets slightly worse results. However, overall, the performance is using the fusion is still better, roughly by half a point with respect to the best single system. So even though in some domains there are some gains and in some others are some worse performance, overall the fusion helps, and that can be seen in part because the different systems perform differently on the different domains. So in some way they complement each other, and using the fusion performs better. Then when using the overlap handling, the overlap detection and handling, we see basically some slight gain on most of the domains, but the largest gain is actually on the telephone data. However, the telephone data is a very particular case where the end-to-end system performs by far much better than the rest. And that is basically the reason why we wanted to use it by itself for these type of recordings, and that basically gives roughly half an extra point of improvement. And if we compare it to the performance of the other system, including fusion and overlap handling, there is still roughly 4.5 points of improvement just by using the end-to-end system. The end-to-end system also has similar performance as the other approaches in sociolinguistic lab interviews, and it also performs very similarly for the case of audiobooks. However, for the rest of the domains, it performs substantially worse. Then let's go finally to the track 2. For this track, we didn't try anything very sophisticated. Instead of using the Oracle labels, we used the baseline VID, and we didn't use the VBX Heavytail PLDA. So in this case, we have here the results for, again, the different systems and the different steps, and the comparison of the final system for track 2 against the final system for track 1. We see, for instance, that in the dev set, both core and full, we have roughly 3 DR points worse performance. However, that difference is much larger on the evaluation set. The main reason for this is that basically the baseline VID is trained on the dev set. So the results that we get here on the dev set are too optimistic. And when we evaluate this system on data that were not used for training, the performance gets largely degraded. Finally, some remarks. Well, we see that dealing with overlap using the standard approaches, that is the ones that cluster X vectors, is still very challenging. On the other hand, the end-to-end approaches naturally model overlap. However, they still fall behind in terms of the overall performance. Let's say if we compare what we saw with our system in comparison to the standard approaches that we used using the Oracle VAD. So this is it for the presentation. If you have any questions, feel free to ask them during the workshop. Thank you.
All right. Thank you, Federico. And oh, great. There you are. So if you could unmute and maybe bring the slides up. It looks like we don't have any questions from the audience yet. So we have about 5 minutes. I will start off with a question. Could you remind me what the end-to-end system was trained on?
So it was trained on artificial conversations created with the telephone, let's say the two sides of telephone conversation. And then it was fine-tuned to call home in order to have some, let's say, real data there.
So it never saw wideband audio during training?
No, not during training. We believe in part that's why it performs so well on telephone data. We did evaluate it on the whole set. So the results that we showed basically are the wideband, but downsampled to 8K so that it would fit in the input.
Okay, I was curious about that because there are a lot of two-party interactions that are similar to the conversational telephone speech in DIHARD. So I was kind of struck that, say, youth point, which is very clean interview speech, was so bad. But if it's the models are probably over-adapted to narrowband, that makes sense.
Yeah, so actually in the sociolinguistic lab conversations, there are only two speakers there, and there it performs quite well, or similar to, let's say, more standard approaches. But it's true that in some of the other ones that there are probably only two speakers, yeah, that didn't happen. So maybe the background or somehow the channel is different.
Yeah, okay. Let's see, take a look at the rest of this. All right, since we still don't have any questions from the audience, I do have another question, which is, have you evaluated this system or a version of this system on, say, AMI, on the new version of AMI that you evaluated VBX on?
So we haven't evaluated this system in particular. So as part of the paper, we had, let's say, the traditional VBX recipe based on ResNet X vectors. And we have results for that, which are the ones that Mireia shared earlier, but not this particular system.
Okay.
I believe that there will probably be not too much difference because of, let's say, what we see here in the table of the comparison of these approaches. Let's say the heavy tail PLDA uses TDNN X vectors, and here we have ResNet, and well, maybe the tuning of the PLDA and playing a bit with that actually makes more difference.
Okay. Well, do we have any other questions? Here we do. So do you have any further idea on how to combine the end-to-end system with the VBX apart from the use of Doverlap?
So the truth is we haven't really thought of that. I think actually in the keynote, Paola was commenting about approaches for that. So probably those should be good ideas to try on. We really didn't work much on that.
We have about 2 minutes left. If anybody else wants to get a question in.
I guess it's getting late in places.
It is, yes, for a lot of people. I'm finally starting to hit my stride since we're finally past noon here on the East Coast of the United States. But I know that John
maybe I can take the chance to congratulate the winning team that they did a superb performance with a large gain on top of the rest of the team. So really very good performance. And thanks again for organizing the challenge, of course, and the workshop.
Right, so I'm going to go ahead and cut this question and answer period off about a minute early and see if we can get through these next two talks and some people can get some sleep.
Sure, thank you.
So our next talk, second talk of this third oral session, is Sangeeta Kanam of Intel Corporation. We'll be presenting. I was curious throughout the challenge as to how you pronounce the team name, so I'm going to assume it's Diaboliic at DIHARD 3. Okay, I wasn't sure if it's that or Diaboliic. And I will shut up and we can run the presentation.
Hi everyone, this is Sangeeta Kanagam, and I'm here to present the work that we did as part of the third DIHARD challenge as part of the Diaboliic team. And with me today is my teammate, and I'll also let him do a quick intro.
Hi everyone, this is Wenda Chen. We are teammates for the Diaboliic team for DIHARD 3 challenge. We are here to present the preliminary version of our system.
Thank you, Wenda. So we'll start quickly with our team structure, as well as a quick summary of the approach that we took. So our team had people from many different places. So we had a team from Lyon, as well as from IRIT, both from France, and then Wenda and myself. And in summary, we had many ideas in the team, almost as many as the total number of team members, but we kind of zeroed in on the following three areas. So we looked at the approach taken for segmentation, embedding, as well as for resegmentation at the end of the pipeline. And we focused on this as three separate systems or three separate efforts, since the team is not based at the same location. And then at the end, we used an ensemble approach to combine the each system end result into a single per track result that we then went ahead and uploaded. To get started with, we will quickly add some details about the approach that the team took for segmentation. The baseline pipeline that's used as part of this particular module is based on Keynote. And for those of you who may not be aware of Keynote, essentially Keynote creates a modular approach to doing speaker diarization, where each one of the modules can be addressed as a sequence labeling task, such that the input is essentially a sequence of feature vectors, and the output is a sequence of labels, where the different type of labels actually depend on the number of classes that's applicable for that one module. And there is also a code available as part of the Keynote pipeline to train your own neural network. So the Keynote pipeline was utilized here as a starting point. And then one of our team members made changes to this particular pipeline to comprehend not a sliding window type of an audio input signal, but actually using audio segments. And the approach of using audio segments is what we found out as we ran through the different test scenarios and training was actually did provide a lot of improvement in the end result versus using a sliding window anywhere from 0.5 to about 4 seconds or so. So that is the improvement, which, as mentioned here on the slide, it definitely improved the overlapped speech detection aspect. The multitask training approach certainly helped with being able to train this on the Voxella dataset, which was key to ensure that when we ran it through the DIHARD development data, we saw good results. Now I'll pass it on to my colleague, Wenda, to talk more about the embedding approach.
Yep. Thanks, Sangeeta. So here, after we have a reasonable pre-segmentation based on the VAD speaker change and overlap detection, we want to produce the efficient embedding for those speech segments in order to support a better resegmentation at a later stage. So we used the X-vector-based speaker identification model as our initial baseline model. This X-vector structure, as shown on the right figure, use attentive pooling and TDNN networks to learn using the target speaker label by producing the speaker embedding at 256 dimensional. The learning was through adaptive margin softmax loss. And this pre-training was done on VoxLab database. And then from VoxLab to test, we used the voices database to see which model was better for the short duration segments. So we can see in this table, there's two models that perform very well for different lengths of segments. The first model performed extremely good for 1 second and 2 second type of cases. And the second model performed better for 4 seconds all the way to the full speech length. So here we are evaluating by equal error rates. So we also further test these models on the DIHARD 3 development data and evaluated the average distance of all the embeddings from the same speaker. We found that the model 1 has lower distance, cosine distance, of all the embeddings that belong to the same speaker. So this is quite expected because we observed that in the segmentation data sets, the average length of the segments are slightly less than 2 seconds. So we tested these two model on the development data of the DIHARD 3, and which evolved from the VoxLab and voices, so which make it usable from speaker ID embedding to diarization purpose. Thanks.
Thank you, Wenda. And now we'll move on to the next approach that we used, which was the resegmentation. So for this particular system, what we did was we used the baseline Keynote system. This was based on the second DIHARD submission that was done 2 years ago. And then the Keynote embeddings actually were utilized as the input into this particular system. And in this case, the embeddings were trained on a sliding window with up to a 4-second duration. And that particular flexibility in how those embeddings were created was essential because one of the key steps as part of this particular system approach was to kind of transfer or translate that particular embedding results into speech segments that can be utilized in the Kaldi ARC format. The resegmentation system was reused from the VBX, which was actually the part of the second DIHARD submission as well. That particular system utilizes a Bayesian hidden marker model where states correspond to the speakers and the transitions correspond to the actual speaker turns. Since it uses an I-vector-like model and then converts each of the speakers as well as the segments into a Gaussian mixture model type of a representation, it does a really good job at robustly identifying for a given set of embeddings what is the connection between a speaker as well as the speaker segment. So once the speech segments were actually converted into the Kaldi ARC format, we used that as the input to process that through the VBX resegmentation system. So in this case, the entire VBX resegmentation part of the pipeline was reused as is. There were a few key changes that were done in order to optimize the end result. The p-loop parameter, which helps identify the number of speakers for a given set of data, that was optimized to a certain number based on a few runs through the third DIHARD development dataset. Also, the interpolation alpha value, which in the end was influencing the PLDA result, was actually fine-tuned to 0.75, which is different than what was captured in the baseline. So these different variables allowed us to fine-tune the resegmentation approach, which could then be easily used and integrated with the Keynote embeddings. A 4% improvement in the word error rate was seen. So previously, we were seeing an end error rate of about 28. And then with the use of the resegmentation approach, it went down all the way up to 24. So even when utilized with pre-existing systems, combined with that resegmentation approach, there was definitely an improvement in the end result or the error rate that we noticed at the end. So now I would like to summarize the different systems that we did submit to both track 1 as well as track 2. The track 1 system was a combination of pipelines that utilized the voice activity detection result through the Keynote baseline pipeline, which was submitted to the second DIHARD competition. We also utilized the third DIHARD system baseline and did an ensemble of both of them to actually provide the end result, which we submitted to track 1. And this particular ensemble was created using the overlap technique. For track 2, we actually combined 3 different systems. One was the Keynote fusion, which combined the 2 approaches that you just heard about from both the segmentation as well as the embeddings. This particular Keynote pipeline was then combined with the second system, which had the resegmentation output, and then another baseline system, and in this case, the VBX baseline system, which is an updated system, was utilized. All 3 of these systems were combined using the Dover algorithm. So we used 2 slightly different ensembling techniques for both track 1 and track 2. And I believe based on the leaderboard results, we were placed on number 6 for track 2. I think this page summarizes some of the references that we utilized. I think I would like to say the third DIHARD competition gave me a good opportunity to understand how the different innovations in the speaker identification area can be brought out in the text-independent diarization area, which was a key learning for me. Also, some of the new ensembling techniques and how effective they are were very evident to me once I saw the output from the different combined systems. I would now like to pass it back on to Menda and see if he has any takeaways from the competition.
Yeah, this competition is teach us a lot on how we extend the speaker identification embeddings to the application of diarization. And also, we, as a joint team with LIUM and IRT, we managed to work together on combining the systems and produce better results. Very thankful for the organizer for this challenge.
Thank you, Wenda. Likewise, I would also like to thank our entire Diaboliic team, almost a cross-site, cross-geo team, who came together to put together these different systems and the final submissions that went into both the tracks. I would also like to thank the third DIHARD Challenge organizers who worked very hard to ensure that the entire systems, the scoring servers, etc., ran to the very last submission point, which did give us some more time to try out additional things that we wanted to. So thanks to the team and to the organizers and for this opportunity to present today. Thank you.
Thank you.
Right, thank you for that. Great talk. It looks like we have, all right, Sanjeev has a question. Oh, okay, no, this is a more comment on some of the interruptions we've had. So I guess, Sanjeev, after the workshop, we'll have to see if the cloud recording is any better. If not, maybe we can get that talk re-recorded. Also, earlier, Shinji had a question that I answered, so it no longer shows as open. Shinji was asking whether Keynote is intended to at some point support end-to-end diarization. Unfortunately, Hervé seems to have left. I don't suppose he mentioned to you whether that was in the plans for Keynote.
So the open source version of Keynote that's available today, that does support end-to-end speaker diarization. I think the updates that you saw that we did as part of this competition, I think Irv would be the right person to comment on whether that will be open sourced or not. But pipeline as it exists for the second DIHARD competition is available open sourced. And that's what I used on my end for a lot of the work that I did as a baseline embedding system.
Okay, thank you. So we have about another 5 minutes if anyone else has questions. I know people are starting to, we've seen about half the number of attendees we started with at this point. So I would ask maybe one question, which is, no, I'll save that and ask by email. It's not be too complicated for this. Well, okay. We are asking for, I have a question asking about the results, a little more information in your results, such as percentages for improvement, relative improvements, et cetera.
Sure. I did notice through the earlier presentations that there was a good summary and a table format for all the different end results that were achieved. So we can certainly update that slide deck to make sure that it includes the results for each one of those systems. I'll have to get that from the rest of the team, but we can certainly update it and submit the slide.
Okay, so as was mentioned earlier during the workshop, we will be posting the slide decks as well as the videos to the website. So there will be a chance to do that. I had to talk to John to see what the time frame is for that, presumably after he's had a nice long sleep. Right, in that case, oh yes, Paolo is asking about how you performed overlap assignment.
Oh, so there were two different approaches that the team took. One of them was as part of the efficient embeddings that were created. So this is the idea that Wenda had, in terms of being able to, actually, I can share the slides here so that you can see it. So the first part of it, as part of the fusion system, as we call it, this actually was done here with the X-vector model. There were multiple different durations that were actually used as an approach to create the embeddings themselves, trained on different data sets, and those were actually combined in the end. So that's one approach that we took. The second one that we took was as part of the resegmentation. This is where, again, I did not use the Keynote version that Herb updated. This is the original open source one that uses the sliding windows. And I utilized the output of that as an input to the VBX system. This is not the recent one, but the one before, where I was able to convert the output of the embeddings into the Khaldiak format, and then I utilized VBX as is to do the overlap assignment. So there were these two approaches that we took. So there's two different levels of overlap processing, and then they were combined using the Dover fusion in the end for track 2.
I do have a question. So the slide where you mentioned your voice activity detection. So can I see the reference slide that's for that reference? I wanted to know if that is that the domain adversarial? Okay, yeah, so it's domain adversarial version they presented this past year. Okay.
Yep.
Well, in that case, I think I will close our question period and move on to the third and final talk from this final oral session. So we could get the video. Okay, good. So the final talk of this workshop is Tae-Jin Park of USC SAIL, presenting their contribution, their submission to the third DIHARD challenge. I'm not sure if Tae-Jin was here from the very beginning, but it would have been 4 a.m. at the start in California. So if he was, I applaud him.
Hello, everyone. We are USC SAIL.
team named USTC-NELSLIP who participated in DIHARD 3 challenge. And I am presenter Taejin Park, and this work is done by myself and Raghuveer Perry, Arindam Jati, and our advisor Shrikant Narayanan. Let me introduce ourselves. We belong to University of Southern California, Electrical Engineering Department, and our research group is called SAIL, Signal Analysis and Interpretation Laboratory, and we are all supervised by Professor Shrikant Narayanan, and our lab concentrated on various different signals, the human-centered signals and information processing. And we are also focusing on speech signal processing too. So let me start with a brief recap of our last DIHARD challenge experience, which is from DIHARD 2. So in DIHARD 2 system, we used X-factor fusion technique, where we added two different affinity values from two different X-factor embedding sectors, which were X-factor Colholm and X-factor Voxelot. Then we calculated the cosine distance, and we applied spectral clustering to get the labels. And then the temporal labels are refined by V2B segmentation. So we achieved 22.89% of DER, and we placed this 9th place among 23 teams. Let me briefly introduce the few takeaways we got from last DIHARD 2 challenge. We realized that PLD and AHC does not perform better than cosine distance and spectral clustering. And we also realized that PLD adaptation sometimes doesn't help if we don't have enough development set to train a PLD model. And also we tried lots of embedding denoising techniques, but for sessions with very, very low SNR, it didn't improve the performance. So we got rid of those embedding denoising techniques. And then also we tried overlap detection, and same happened here. It performed pretty good on high SNR sessions, but pretty bad on low SNR sessions. So we did not include overlap detection for our final system. So but there were some positive takeaways. We realized that cosine similarity, very simple distance measure with binarized affinity, and the spectral clustering performs really well. And we also realized that by adding the two cosine similarities from two different embeddings, and that this method performs way better than only one embedding structure. And also we realized that V2B segmentation helps a lot for track 2, where we use system voice activity detection module. So let's talk about the DIHARD 3 module. We had a major upgrade on two different parts. First one is auto-tuning spectral clustering. So before in DIHARD 2, we used spectral clustering, but the binarization parameter P was tuned on development set. So we tuned the P value and then use it for the evaluation set. But in this time, we applied a new algorithm, which is called auto-tuning spectral clustering. So and another improvement was a domain adaptive affinity fusion. So we used a soft decision method to weigh the affinity values from three different X-factor embedding structures. So let me briefly explain what auto-tuning spectral clustering is. So spectral clustering is usually done by calculating the affinity metrics which shows the affinity values between all the segments in the given utterance. And using this affinity matrix, we calculate the Laplacian matrix, and then we calculate eigen decomposition. Using that eigenvalues and eigenvector, we perform k-means clustering, and then we obtain the final output. But we realized that if we binarize the values using the per row parameter p, which determines how many values are converted to 1 per each row. If we use this value and binarize the values like this, we realize that it performs way better because it ignores the values with small values, which is oftentimes pretty noisy. But there's still a problem of determining this value. So we had to come up with a method that estimates the best p-value. So for that, we used the relationship between eigengap and cluster clarity. So as you can see here, if eigengap is huge, you can see that clusters have better clarity, while a smaller gap shows less clarity compared to bigger eigengap. So using this, for example, if we put more, we keep more values per row and more ones per each row, the eigengap gets bigger, which means we can yield clear clusters. But there's a problem with the one values, because if we fill all the affinity values with 1, and then the whole affinity, the whole session will be clustered as one speaker. So there should be a compromise point between these two, like putting all zeros or putting all ones. So for that, we used the ratio between the p-value and the maximum eigengap value GP. So so this ratio shows, if we calculate this ratio between p over GP, we can, if we plot this p over GP, the trend follows the DER, because the maximum eigengap is usually follows the trends of how clear the cluster is. So if we find the minimum value of this p over GP value, we can find the adequate p-value, and then we can perform the clustering using that p-value. So the result is pretty interesting, because without using any depth set, which means a parameter-free clustering, the auto-tuning clustering, spectral clustering performs better than PLDHC method, while we're using exactly same embedding extractors for all these different data sets. So this method, the auto-tuning spectral clustering, appeared in CHIME 6 Track 2 challenge, the winner team STC's speaker diarization pipeline. They used this auto-tuning spectral clustering, and along with target speaker VAD, which performed way better than other participants, and they won the challenge. So if you read the author's paper, you see that they also show the superior performance over Caldi's AHC and PLD by using auto-tuning spectral clustering. So that was our clustering method, and let's talk about the domain adaptive affinity fusion method. So for this, we tested 3 different X vectors. First one is X vector Colholm, which is trained on telephonic speech, SRE dataset and switchboard. And then second one is X-Vector Voxelab, which is obviously trained on our Voxelab dataset, which is web videos. And third one is X-Vector Chime6, which is released very recently. And this is trained on a Voxelab dataset, but adaptive on Chime6 training data. So as you can see here, while in most cases Chime6 is showing the best performance, there are a few domains where column X-Vector performs better. For example, CTS, which is telephonic speech. And of course, Voxelab X-Vector performs better for web video domain, as you can expect. So different, you can see that different X-Vector performance shows different performance on different domains. So if we can estimate the domain of the input test session, then we'll be able to choose the best X-Vector for that domain. So the first thing we tried is hard decision model, where we estimate the domain and then apply the most probable, most likely best performing X-Vector. For example, if it looks like telephonic speech, we use column X-Vector. Or if it looks like web video, we use X-Vector Voxelab. And second method is soft decision. We used structure similar to CMS network, and we estimate the adequate weights adequate weights of affinity values among 3 different embedding extractors. And then we obtain one final affinity value for a pair of speech segment, and then we do the clustering. So we obtain one set of weight for each session. So for each session, this neural affinity score fusion module estimates one set of weights. So as you can see in this result, we also tested our last year's system, and we also tested the whole test data evaluation data set with X-Vector Chime6, since it showed the best performance among 3. And as you can see here, hard decision model performed better than X-Vector Chime6 only model. And then our soft decision model performed even better, while it's showing 18.19% of DER. And this is for full set track 1. And for core set, we got 19.76% of DER. So let me finalize the presentation. We tested that auto-tuning clustering method showed improved performance over regular depth set optimized binarized affinity spectral clustering method. That was the first takeaway. And second takeaway was we realized that soft decision method works better than hard decision model, where we estimate the label of the domain itself and then perform the clustering. So soft decision method worked well, and I guess the performance gap between the state-of-the-art or first place model is, I guess that's because we lack of overall detection or speech separation techniques. So thank you very much. This is the end of our presentation.
All right. Thank you, Tae-Jin, for that presentation. All right, so we do have, I see that you've been answering questions during the talk. We do have one that just popped up in the queue. Could you comment on the real-time factor of your final system?
Yeah, just as the other teams, I didn't particularly measure the time it takes to complete the diarization. But I'll say it increases dramatically as the session length goes up, because the spectral clustering and the affinity metric space method is basically n square, and the calculational complexity goes up dramatically. So to give you a ballpark estimate, if it is around like 10-minute session, it doesn't take more than a few seconds. But if it is like 30 minutes or like or more than that, it'll take 5 minutes and 10 minutes.
Yeah, so because the reliance on spectral clustering for longer recordings, that's going to dominate everything else in the system. Okay.
Yeah, he asked the follow-up question. So there must be like spectral clustering process, and then there would be auto-tuning part where we need to calculate the eigenvectors and eigenvalue. So the thing that I mentioned is about the time that I mentioned is including all the clustering and the auto-tuning process together. So to be honest, the auto-tuning part is very computationally heavy process. But
I actually have
but I guess for DIHARD challenges, since the sessions are pretty short, the spectral clustering method worked pretty well.
Yeah, it is relevant for some of these domains because, for instance, the clinical domain in DIHARD, those excerpts come from couple-hour-long recordings. They might have breaks in them, but they're very long recordings. The restaurant recordings are pretty long too, the original recordings. I actually had another question also on auto-tuning. So are you extracting all the eigenvectors and eigenvalues, or are you doing like a truncated SVD?
What do you mean by truncated SVD?
Are using, say, a randomized SVD and only computing, say, the first however many components and assuming the gap is in that first, say, 15, 20 components?
Well, the eigenvalue selection is based, I guess that's based on the where maximum gap is located. I use some kind of a sparse search method, not for eigenvalue, but for searching the p-value. So if the session is too long, or if which means the affinity metric is pretty large, then I limit the number of potential p-value for being searched to 20 values, so that we can limit it to certain numbers, so that it can be done in limited amount of time. So, for example, if we need to search from 1 to 100, it skips and search every 5 from 1 to 100, 5, 10, 15. So that's how I reduce the calculational complexity. And then the performance was almost the same if we keep that into 20 values.
Okay, we're at the very end of our question period, though I will ask one last question I really should have been asking everybody, which is, do you have any plans to release the system and or the recipes via GitHub or some other venue?
So I'll definitely upload it once I finalize the description and all that, and I'll say I'm willing to share the code, and some of the audience might know this, but auto-tuning clustering software is already on Git, and then it's already used in the previous challenge from other teams. So I just wanted to emphasize that it's already freely accessible to the public.
All right, thank you. And thanks for sticking through this. You had a very early start date on your end.
Yeah, I dozed off a little bit. It was 4 a.m.
Well, that concludes the third oral session of DIHARD Challenge, and it concludes the workshop as a whole. So I'm not sure if John had any last remarks he wanted to make that he had planned. I'll defer to him at this point.
Hello. Yeah, I put all the organizers and presenters and the best contributors in Q&A session. For example, Sanjeev and Shinji, yeah, to the panelists. So I want maybe everyone can open the camera. Yeah, we can take a picture. Yeah, thank you for all your contributions. Yeah, to the workshop. Thank you. Yeah.
Thank you very much.
Thank you. Yeah. So I think
June and NAVER, thanks, guys.
Yeah, I think 3 organizers for the JSOT 2017, 19, and 20 is here. Yeah, Mark Lieberman and I think Shinji Watanabe is collaborator with Jordan and the Paola Garcia. Yeah. So yeah. Thank you. Yeah.
Right.
Well, I'm not sure as the initial for the speaker diarization, maybe Mark can say something. Yeah, because you are the creator of the first JSOT, for the speaker diarization problem. Yeah.
Well, I have not contributed much at all to this workshop, but it's inspirational really to see the progress that has taken place in the last 3 or 4 years from a time when the technology was very poor, but there was very little focus on it, to a situation in which the technology is enormously improved. There's still some headroom and some things to do, but we have learned a lot. It's very impressive and makes me feel very good. So thank you all.
Okay, maybe Sanjeev can also say something. You also the first. Yeah.
So I will just tell a little story about when we were planning the 2017 workshop. Ken had these problems at IBM, and he was showing us recordings of how simple customer and agent dialogues were breaking down because you didn't know who was saying what. This was just 2-person telephone, and how it was important to get it right so that you could do the subsequent understanding. And we had a big group of people in the audience who said, oh, come on, speaker recognition error rates are down in the single digits, and this will be solved before the beginning of the summer. And 3 years later, we are still working on it. So I'm happy we started that group and kickstarted this whole project. And like I said, Ken and Mark were the main people who came to the planning meeting and said, hey, this problem is harder than you think. And it's really nice, like Mark said, to see the problem getting attention. By the way, we have made huge progress since 2017. I should probably go back and check our error rates on AMI at that time, and we've at least cut it down to a half, if not a third.
Yes.
So yes, there's been a lot of progress.
Thanks. Yeah, maybe Ken also say
Yeah.
something.
So can you hear me?
Yeah. Because you have the story with the IBM, right, on the speaker diarization.
Well,
you
yeah.
told me.
So the problem was actually worse than what Mark and Sanjeev said. That is,
But I mean, Sanjeev kind of gave a hint of it. That is, not only did the solutions not work, but the community believed that they had the solutions. They didn't even, I mean, it was, we were in denial. Not only the stuff wasn't working, but we weren't willing to admit that it wasn't working. And I was in an awkward situation because what happened was that we had committed to the powers that be at IBM that we would solve the problem based on all the optimism that was in the literature. And it was only after we committed to it, we had to ship something, that we realized we didn't have much to ship. And it was just very embarrassing. And we couldn't really justify the business case to do the research that needed to be done. And so the only solution I could see was how somehow to engage the research community. Now, thing, right? Obviously so, but it's sort of amazing that it was hard to make that case back in 2017. So, do you think that it's a sort of that this inertia, that this enthusiasm can be maintained, or do you think that people will go back to the complacency that we were at? That is, or is this seem like a hot area to keep working on, or does it feel a little bit tapped out?
Ken, I think that the facts that were the original impetus for you remain in place. That is, there's increasingly practical, serious, and widespread speech-to-text technology being deployed that people are being asked to pay money for, or that is being folded in with other services. And I think it remains even more true than it was back then, that as the word error rate is coming down, the diarization accuracy of the deployed systems is not really improving to the same degree, although it's probably better. And so I think the fact that the basic systems are being widely deployed in circumstances where there can be more than one speaker, for example, in the clinical situation. There are cases, of course, where you have good audio separation of the different channels and so on, but there are also plenty of cases where you don't. So my prediction is that there will continue to be impetus to work on it.
Yeah. And Ken, the impetus comes from many places. So, for example, like, my former student Arya, who's at Amazon, he still thinks that the problem of, say, figuring out who said Alexa so that you can follow what they say afterwards when many other people are talking in the background is still an important problem. It's a special flavor of diarization, but nonetheless, that's what it is. Our friends in the the language environment, language acquisition community, Brian McWinney was here. I don't know if he's still here in the audience. They still don't have a solution. They still look at us and say, what are you guys doing? You told us back in 2017 that you'd fix this. Just like you said. Right. And well, actually, all I'd hoped to do in 2017 was to get people to think about it. I didn't really expect that we would solve it. Absolutely. And there are other applications where people see some of the speech technology working well and they're starting to think big. So we have collaborators at NTU who want to understand the dynamics of classroom interactions and what makes for good education strategy. Sure. And we have some of their classroom recordings and it's hell. I mean, like, I wouldn't give it to an early graduate student because they might just leave the program. Well, you're bringing up, though, a lot of problems that I think are much harder than diarization. Yes. So let me just mention one of the things that you mentioned, which is how is the machine supposed to know when you're talking to the machine and when you're talking to somebody else? Or when, a car backfired somewhere. I mean, during some of these talks, I was hearing cars noise in the background. And it would hardly distract any of us, but, it can do horrible things to machines. Anyway, one of the problems was people want to get rid of the wake up word. I shouldn't have to say Alexa, blah, blah, right? But in order to do that, you need to have some common sense to know when we're talking to the machine, when we're talking to somebody else. And the wake up word is a simple kludge to get around the fact that the machines can't handle that. But I think understanding who you're talking to is much harder than just figuring out who's speaking when. Diarization is already plenty hard. Right. Yeah. Anyway, but I have no doubt that the people in this room or in the Zoom room are now convinced that this is hard because you've worked on DIHARD. But I worry that the larger community out there thinks you can just download something from GitHub that actually does a pretty good job on word error rate, at least in simple cases. And then you run into all these issues that we've been thinking about here. But I'm not sure, people who haven't thought about diarization, are they aware of these things now? Has this community made a difference there? So Ken, I'm thinking we may have, but I will tell you what our enemy is. And when I say what our enemy is, what I mean is what causes there to be misinformation, right? And the situation that typically is, like, you can kill almost anything with matched training data. So therefore, instead of giving me Chime 6, where I have 40 hours of training data, if you gave me Chime 6 with 4,000 hours of training data, I bet diarization would be more or less solved. So, like, that's the thing, that if you can match everything properly, if you're a Google and you can get 1 billion people doing the kinds of things that you want to recognize, then maybe there's not a whole lot of research to do. Just kill it with a bigger network. That's the sense I get from talking to people who are stakeholders in research decisions, who make decisions about, like, what to find. If they can see that one of the key challenges we have is that with diarization, there are going to be as many different test cases as there are recordings, that each one is going to pose its own problems, that we cannot kill this one with data, then that might be a bigger success than where we are. But I think we are having an impact. People are starting to see how difficult this is.
Well, anyway, it's good to see all this progress here. Yeah.
So I also think that that we are there's still a gap, as I said before, between what we have and what other fields really need, because we always trust on our dev data and then on the test data, but outside there is only about data. So that is one of the main limitations that I think we have right now. For example, on the child-centered data, the results that we are getting are not very good, and that also happens, for example, in Chime or other different domains. So I think there's still a lot of room for improvement.
If I sort of riffing on what you said, it sounded a little bit like what Sanjeev said, that in some tasks that we work on, you can hope to have samples of train, dev, and test that are kind of representative of one another. But you think for some other problems, the diversity is just so extreme that it's unreasonable to expect the different train, dev, and test to be
exactly
right. I
think for web video.
Oh, sorry, Nabil. And sometimes you even have like 2 recordings of about 10 or 15 minutes, right? That's all you have, and you have to diarize them automatically. The rest of the data set probably is private, but that's all you have, and you have to do the best you can with the systems.
Neville, what were you saying?
I was just going to say pretty much all of the found speech applications and things like web videos tend to fall into this.
if you look at the subset of VAST that we selected from for DIHARD, there's a massive diversity in just maybe a few dozen videos of what shows up. Interaction type, conditions, speaker characteristics, the environmental conditions are sometimes crazy because you can have, there's just a question even of what is a target speaker. And that changes almost recording to recording for that found speech, especially that stuff that's collected in outside.
Right. But you're saying people that work in the big firms that have, unlimited sort of inputs like, I don't know, Google and Amazon, they don't seem to share this feeling. I think they seem to think that you can hope to get reasonable samples.
Yeah, I mean, I think there's a lot of people that still...
It may be a little different from that. I mean, Sanjeev may have other experience, but the people that I have talked to at Amazon don't seem to be confident that they can separate voices with Alexa reliably, that that's a solved problem, or that they can guarantee a solution at a certain.
Well, I mean, also Amazon and Facebook AI Research both have active groups looking into pre-trained acoustic representations. So I think at least a subset of people there are not banking on having matched training data to win the day.
I see. Where you think Google gets most of its input off of a phone that has a single user? So it's very different. Google Home. No,
Google Home's a different kind of product, right?
There's, but I meant that most of the audio that hits the Google Cloud is probably not involving lots of speakers. Okay. Whereas the audio that comes in through Amazon's speakers are probably picking up what's in a room that typically has more than one person. So diarization is much more of an issue there. The problems that I was facing were, it sounded pretty simple. It was just call center stuff, but, I'd have a couple of agents as you get handed off from one agent to another. And also sometimes calls had more than one customer, but typically they didn't speak at the same time because they were using the same handsets. But even then it turned out to be quite difficult. And I remember some back and forth conversations where people were trying to hand back and forth these long, complicated serial numbers. And one person would say part of it, then the other one would confirm what they heard, and then they continue. And sometimes there would be confirmation, sometimes there'd be corrections. But if I couldn't even tell who was speaking when, it was really difficult to figure out what was new information and what was either a confirmation or a correction. And of course, another issue is what's the difference between a confirmation and a correction, right? You might say the same thing either way, but it was pretty obvious to the people listening. But when I look at the output of the ASR, all I saw was the words they said. I couldn't tell who said what and what they were, what the meaning was. Do you agree or do you disagree? Right? Anyway, that's another problem that goes beyond this thing. Yeah. But they seem incredibly simple. Yeah. What?
No, I was going to say, Ken, I think the problem you're pointing out are interesting. We have two other people who are from industry in this group right now, Shota and Sangeeta. Maybe they want to say why their companies still think this is an important problem, because I can imagine we academics, we just persuade somebody that it's an important problem. But maybe they have to, in their case, money is involved. So Sangeeta, Shota, do you want to say what your companies think is interesting about diarization, why it's important, why it's hard?
So I guess just a quick comment. So on our side, for the work that I do, we are looking at smart conferencing. And this is going beyond using a single voice assistant at home or using even one in the meeting room. What customers want to see in the future, and where we hope to be, is a place where your meetings can be transcribed. There is a way to identify speakers that's text independent, so you don't know who they are when they enter the room. but you need to know that they are different speakers. So I've seen that Microsoft has a way to do that in Teams today, where even if you are in a virtual meeting, they will transcribe it, except they don't assign speakers yet. So you do get the transcription. There is no speaker identification to it. So there's, this is certainly a hard problem. I think I have seen different efforts from the industry to solve it, but we are not there yet. And the uses of this could be very beneficial, especially as we move into a hybrid conferencing environment with half of the people being virtual and half of them being in the room post-COVID. So I think, and this is definitely very hard. We haven't seen a problem or seen a solution yet. And, we certainly are continuing to work in the space with partners and others to see what we could do. So.
Okay, so for the industry part, I think because I attend the 3 JSOT workshop on speaker diarization, I have one observation that more industry institutes involves. Maybe Shinji can give some comments, because this year's JSOT, the organizer is from Microsoft, right? You collaborate with the Microsoft guys. It seems that they are very interested in this technology to put them in their product in the future. Maybe.
Yeah, definitely. Yeah, that's a kind of a very the exciting point. I mean, diarization and also some other downstream tasks, the mostly ASR. It's having a quite great interest in the industry now. So yes, Microsoft, yes, and in our teams also NTT, also the inventing a lot of the interesting technologies for their product. And also the like our submissions, the Hitachi, they also had a lot of kind of diarization techniques. And I know a couple of them, maybe Shota will follow up, but in addition to the meeting, they also have some smart agents, sometimes even through the robot, to have some kind of agent for the human conversation. And then, diarization is actually necessary technique for them. Shota, do you have some kind of more comments about your the couple of applications of the diarization?
Diarization. In my research, I'm using diarization as a guide. If it used with the guide, for example, guided source separation, it can be used for the totally good ASR system in very bad condition like chime 6. So in terms of this, that diarization can be a good pre-processing for the transcription system in the very hard conditions.
Yeah, that's a good point. Diarization is sometimes chicken and the egg problem. The separation, if we solve the separation, we can also solve the diarization. It is a kind of straightforward the idea, but it turns out that we actually built that the opposite direction is important. If first we solve the diarization, which is slightly easier, and then we get the speaker statistics, and which is used for the separation. And then sometimes it's also going back to the diarization and so on. And which also finally improve the ASR. And I also know that the Microsoft system actually first do the ASR. So this kind of, how to say, the interesting combination of the modules are also the very the interesting direction, and it's also depend on the kind of how to say the finally what the people want. So that's a kind of the interesting trend now.
But your story about how all these problems are sort of interconnected has just got to be right. I mean, something like if you just deal with sort of say the cocktail party effect, that most people sort of approach it with a sort of bottom-up sort of processing to figure that you know, we have 2 ears, you must be able to use that to localize the speech and focus on one angle and, you know, sort of like beamforming. The problem, though, is that I think it's well known that native speakers are much better at the cocktail party than non-native speakers.
So Ken, your point is that we also have something between the 2 ears that matters?
Yeah, there's some logic going on between the 2 ears. It's not just electrical engineering, right? And somehow you need to do both of them at the same time, I think, right?
Yeah.
Yeah, and that there's no way to explain that knowing something about the language actually helps you in figuring out doing the sound separation and maybe even the diarization and so on.
I think this is very kind of the important direction in the research now. Linguistic feedback for the speech separation or speaker diarization. Tejin also has some kind of very interesting lexical the speaker diarization techniques. And speech recognition and the speech separation, speaker diarization, it's one of the parts, as I mentioned, it's that this module is kind of interactively solved now. And one of the other techniques is actually the one, just try to use a single neural network or whatever to try such kind of older problem. That is actually one of the topics that we were working in the summer, last summer, in the Jelinek workshop. And I think this is one of the very cool the direction in this kind of the trend.
But I didn't think I heard much today that involved, you know, knowledge of the language.
No, not at all. Not at all. Yeah. No, so this is, Ken, this is partly our field learning things. And that's why when the slide discussion started about human performance on this, I jumped in and so on. So I made one point about evaluation, but the other point was that when I learned about how humans process speech, I got the first order version. I got the Bohr hydrogen atom where the electron goes round and round the nucleus in an orbit. But I never had learned the Heisenberg stuff. What I mean by that is we learn about auditory processing and the cochlea and the filters and all that. But at least if you go to the next level, there are as many nerves coming down from the brain into the ear than that are going up. So basically, there's a lot of upper level information that goes all the way down to influencing perception. And I think that has to be a part of what's going on. Like, you know, we have to have some kind of higher level information feeding back into all the way into, like, you know, speech activity detection, into the speaker identification, diarization, the whole thing. So we have a long way to go in terms of just understanding the basic sources of information. Like, you know, in other words, I'm not even saying let's do it the way humans do it. I'm saying just to understand where the information is that lets people do the diarization, we're still getting to that.
Right. So let's say we were trying to design the benchmark for the next round of this meeting. And let's say we wanted to encourage people to work on some kind of top-down constraints in addition to the bottom-up stuff. What could we do differently to cause that to happen? You think it would help to collect data sets in different languages?
Yes, so that's one idea we had early on with DIHARD before we realized that we'd been off more than we could chew. About half of the video data actually is in Mandarin, but we've never tried to analyze it at that level because we already were over our heads. Another option actually might be to have kind of a task that's not necessarily all that useful for most in tasks, but might be useful for understanding. So you can do a multimodal diarization where you have text and audio. That's not the kind of multimodal diarization people are probably interested in doing because probably they are interested in getting to the text. But you could ask what having the text as an additional constraint gives you.
I guess the other item, that also comes to mind is having multilingual data set from speakers who, have are non-native to that language. Because I think this mimics a lot of the real world scenarios where you have people from different backgrounds, different language speaking abilities. I think that helps as well.
Following up on the idea of text as a possible input, if you had conversation, and of course we have many lengthy conversations, as Neville pointed out, if you had an accurate transcript, let's say, of the first half of it, which tells you quite a bit about the language model for the second half, as well as the roles that the participants are playing, you ought to be able to use that in order to improve diarization in a challenging second half, in terms of the number of speakers or the audio quality or whatever. At least that might be a thought.
Yeah, I think these are all interesting suggestions.
Yeah, I also
Well,
think that it is possible to have these bilingual data sets. For example, the Siami data set that is already there in LDC. So you have, or something similar that can have like two languages in the same recording, and usually by the same speaker. So perhaps that can also be useful. And I don't know if it's in the plans to have audiovisual data set for the diarization.
right. So let me
It's been
riff on the
discussed.
audio. On the audio-visual thing, there's getting to be more interest in lip syncing. And even to, you know, like deep fakes. I mean, some of it is detecting deep fakes, but people also want to generate them. So I'm seeing parodies on YouTube where you have these animated characters lip syncing to things that politicians said. But the lip syncing isn't terribly convincing. Anyway, if I had a video with multiple speakers going on, you would think you could do diarization by looking at the lips, and maybe vice versa. I'm not sure that would force me into the direction that we're trying to say is that I want to get people to think about top-down constraints. But there is a sort of interesting question about, say, if I was to dub a movie, could I dub a movie and change the lips to make it convincing? And that this person is speaking in another language that he doesn't speak. Anyway, yeah, so I think this is an interesting topic to be thinking about, to say, suppose that we wanted to drive the research in some particular direction, how would we collect data sets to go there? Now, one of the things that Neville mentioned is that some of the data sets we could imagine might be expensive to collect. But I could imagine, say, in the case of Mandarin, that we could probably find partners who would be quite interested and maybe more skillful at collecting some parts of it. They might actually like to join forces. So, you know, if we could think about, let's say you wanted to do something that involved both English and Mandarin, where knowledge of the language would be useful. Let's think about how we could, you know, what would be needed and what kind of resources we might have access to and how could we get there. And if you've got a fair amount of time before the next meeting, that gives us time to actually do something, to think creatively.
That's one of the many reasons for wanting to move to a 2-year schedule.
Yeah.
Right. Yeah. So Ken, what I was thinking is, like, you know, I was also thinking earlier about the utility of track 1 versus track 2. I mean, are we at the point where we can say, let's stop doing track 1 because track 2 is close enough now? You know, this is how we started. For many of the people in this group are not as old as I am, but I remember we used to do ASR evaluations where NIST gave us the segmentation. And then we went away from it because at some point we got good enough at it. But I think that we should still keep track 1 for a different reason. If we could transcribe the dev and the eval sets only, let's do track 1 where you have the transcript. You know the segment boundaries and you have a transcript. And then let's see how much that improves diarization, just knowing what was said. Maybe that's one way to think about it. Or I think maybe you suggested it, or maybe Mark, I can't remember, saying we'll give you the transcripts for the first half of the conversation or the recording and you figure out the second half by yourself. Something like that, where I'm thinking, for example, that people have very characteristic ways of back channeling, like there's just these aha alarms that we do, right? Those are some of the hardest things to diarize because you have 0.2 seconds of speech and sometimes you don't even find it, and other times it's overlapped with other speech. But if you knew there's an aha over there and you have ahas from all the speakers in the room, can you figure out whose aha it is? Like, things like that. So there are little aspects of this.
Yeah. Well, when you get to back channels, talking about back channels, one of the things that's so difficult for us to figure out, like this new technology. So with back channels, can you hear me? You can hear me? Yeah. So with back channels, one of the big hard problems with something like Zoom is I'm talking and I don't get, I don't get the body language. I don't get the, not only the back channels, I don't get the head nods that you just made, but mostly I'm not seeing it at all. And it's just very awkward. I can't tell if I'm scoring points or not. Maybe if I, spent more time on Zoom, I've already spent more than I want to, but maybe I'd figure out how to make it work for me. But right now it's just, I just feel like I'm struggling to communicate with this new technology. And I think that even with the diarization, we're probably not at all great at capturing back channels. I don't know. I mean, is that really part of the task right now?
No, I mean, when we chose to, one of the rationales for eliminating forgiveness collars was a concern over back channels, because if you have a 250 millisecond forgiveness collar, as was standard in the NIST-RT evaluations, then the back channels just disappear. Of course, the problem is eliminating the forgiveness collars runs into issues with inaccuracy in annotation, and you have to make a decision about whether or not you need a certain level of precision in the annotation, which is a whole nother area of discussion. So we did have some concern of back channels then, but we haven't done an actual evaluation of system outputs that focuses on back channels in some way. You might be able to do that with Chime, because Chime Track 2 has diarization and transcription.
Yes, that definitely has a lot of back channel included. But I particularly didn't analyze this the part. Maybe it's a very good point. Yeah, because we can easily get the diarization result and also ASR result. So yeah, I will definitely do some analysis. Yeah, that's a very great kind of discussion.
It's my understanding that back channels are extremely common in Japanese, much more than in English. Is there any truth to that?
I think the
word
that I hear is hi.
Yeah.
I'm forgetting Japanese conversation.
Okay.
I'm kidding.
Sorry, to put my engineering hat back on, right? I think that there is a way to focus on these things. So, Neville mentioned this during his introductory talk, that although we did come up with DIHARD error rate, we didn't really emphasize that BER is still the primary metric. But one thing that DIHARD error rate does is it takes away the unequal speaker time, because every speaker becomes equally important, right? So you could take that one step further and take every utterance and do the DIHARD coefficient of that utterance, and then average equally for all the utterances of the speaker, and that further equalizes long and short utterances. And then every aha is as important as my rant of 30 seconds. So I think if we did think, there are ways to think about how to make this, more a focus of the metric, and I think that will then drive us all to do research to make it better. So Neville, maybe it's worth investigating. What happens if you compute the DIHARD coefficient for every utterance, and then do a macro average of that first, and then average the speakers? So now every utterance of every speaker gets one vote.
Yeah, this is one of the reasons we'd actually, before we decided we'd had enough of running workshops after the experience with this workshop, we're toying with the idea of releasing the evaluation set labels only to people who wanted to look at alternate metrics or alternate evaluation methodologies, and not just like simply re-ranking past challenges, but actually trying to see if there are things that are just fundamentally being missed. This would be a simple one to do. I think another thing that all this discussions brings up is that we're at a point now where when we did the first DIHARD, we didn't know where we were. So that was one of the rationales for having all these different domains and making it a headache of trying to normalize the annotation and everything across domains. We just didn't know what the state was. I also was particularly interested in domain adaptation and domain generalization. So there was kind of a sort of impetus on my behalf for that. But I think now we're at a point where we really kind of need to step back and say what domains are interesting and aren't being adequately handled by other challenges or evaluations or areas of research that are being performed independently in the community. For some of them might even just be too hard. They're ones we would like to do, but I think like conversations in restaurants might just be almost too hard at the moment, and maybe that should be something that's left in the future. Something like Chime is maybe a little bit more tractable, as hard as it is, since at least it's a controlled environment. Similarly, the child language, it almost needs to be a separate challenge, because what you want to do is probably not full diarization. It's something between speech activity detection and diarization. But I think having 2 years between the next challenge gives us some time to have this discussion. We should probably arrange to have some additional discussion either offline or on a scheduled Zoom call after this to try to figure out where we want to target our time and who we might be able to pull in who has money.
Yeah. By the way, in the context of developing the resources for the next iteration of this challenge, Brian had a comment in the question QA thing, Brian McWinney, where he says he himself is looking into crowdsourcing diarization and trying to get that way, both because at this point humans are much better at the kind of data he cares about, and also this might get us a way to get data for the next challenge where it'll have a flavor of not being great because it's crowdsourced, meaning in terms of ground truth, but it'll be great in terms of there'll be multiple labels, maybe get some understanding of what human performance looks like. So there are other aspects that either Neville, you or all of us as a group can think about. And also when we go to things like Chime, we don't have to jump into the full distant microphone, quagmire. We can say, let's start with the worn microphones. We do this often in our lab, where if you want to work on AMI, we'll just sum the individual head-mounted microphones and work with that for a while. And so at least leave some of the difficult signal acquisition problems on the side for a while. Focus on the diarization issue, and once that's done, then you say, okay, now let's take it to SDM or at least to the array microphones and see what those do. So we can sort of stage these things where even within the same challenge, if you like, you could have 2 or 3 tracks where one you work on multi-party conversations but with near field recordings, and another one with far field but arrays, and a third one with far field and a single microphone. And that way you'll get the whole range, because like the internet video or whatever right now is single microphone, whatever field, near, far.
Yeah. Well, but say when I use Zoom like this, Zoom seems to know who's speaking when, because it actually knows, which we're all on separate channels. Yeah. But when you record this thing and you post the recording, is it a single, it adds together all the sources, right?
If you record in, I can't remember if it's record locally or in the cloud, but there is an option to record every single participant on a separate track.
If you record locally, you can record every participant on a separate track, and it does a pretty good job of separation.
I see. So would it be possible to collect a lot of data by some method like that, where you actually have the ground truth because you have everything on separate channels? But
we had considered,
yeah.
We'd actually considered doing something like that. After this, I keep noticing Paola keeps raising her hand, so I'd like to give her a chance to say something. I think she has something to add. But just really quickly answering your question, we did get decently far along with recording via Zoom people engaged in Dungeons and Dragons sessions. And then the problem was I sat in on a couple of the sessions and they were so socially awkward. We weren't really clear that we were getting any interesting, useful information.
Right.
So I just want to mention a few comments. So Sanjeev was mentioning before about the Jacquard error rate and the imbalance of the different recordings that we might have, that imbalance in terms of speakers. So perhaps we can have a speaker that just says, aha, in the whole recording. And is it worth it to label that specific speaker or not? So that's also one of the questions, right? And about the far field, I think it's very important to address that that direction, because we have lots of recordings out there. I know that perhaps the VAST or the Chime datasets are just very difficult, but there are some others that also contain far field. For example, the clinical data. In some cases, the patient is not very close to the microphone or is moving around or something. So
well, people may put the mask now,
yeah,
right?
yeah, exactly.
That's actually changing the acoustic characteristics a lot.
Yeah, a lot. Yeah, and I'm also pushing to include the kids into the next DIHARD, because right now all the classes, or most of the classes around the world, are by Zoom or by any other video conference technique or whatever, right? So sometimes you have like not one but two kids in the same house, and some of the people don't even know how Zoom works. So it will be useful also for them to have this diarization systems.
Paola, one thing that might help with some of these more difficult and challenging cases, including with children. So these are all these unconstrained cases where you don't really, there's really just a question as to what speakers that show up you care about, because maybe it's a background speaker, maybe it's a foreground speaker, it's just yet another annotation decision. Would be do something to run a task that's somewhere between speaker tracking and speaker diarization. So you actually give a sample of each speaker of interest. So you have to have at least enough audio for that to be relevant.
Mm-hmm.
But now the system is no longer having to make a judgment call about whether a speaker is of interest. They know which speakers are relevant. They have to produce a segmentation for each one of those speakers.
Yeah, so that last task reminded me of some demo I saw probably 30 years ago, where somebody was really proud that he had some kind of a camera that could aim at wherever the speaker was. And it did pretty well at some simple cases, but then somebody was next to a wall and the camera went right for the wall instead of any person, because the reverb off the wall. And then there was two people in a quick rapid succession, and the camera was always pointed at the person who just finished speaking, never the one who was about to speak. And somebody coughed and it went right for them. Right. When they first put the microphone array in the Murray Hill Auditorium, they had the guy in the sound booth who would see where it wanted to go, and he could decide whether to let it go there or not, because you didn't want somebody kibitzing in the auditorium to go over the house speakers. There's a whole lot of these tasks of, are you talking to me, or are you talking to somebody else, and do the rest of us want to hear it? There were some cases where there was car noise in the background of some videos, and I don't want that, sort of transcribed. I'd like to be able to delete that. But the back channels are definitely important. I want to know if the audience is agreeing with me or not.
Mm-hmm.
Yeah.
So I might suggest at this point.
No, Neville, I was going to say, I haven't heard from Mireia, Federico, what they think we should do next. Any thoughts, Dave? Or Tejin? Sorry, I tend to talk too much, so I'm just trying to check myself.
At some point they commented, I think it was Kenneth, about let's say, how the conversations work, let's say in this Zoom or whatever other system. And I would say that when you consider these back channels and so on, it's very different if it's telephone conversation where you don't see the other person, or for instance, when it's a meeting or a restaurant conversation where you actually have the other one in front of you. Yeah. So I guess these type of things would change a lot depending on the context or the domain, let's say, as in DIHARD. So I guess that is also important in terms of what you want to focus on. So deciding on what data and what type of data you want to collect, depending on the problems you want to see, of course. And I guess in that sense, as Neville was commenting, a few years ago, it was important to know where we are. And let's say DIHARD is a very good way because you can see how you are in very different contexts. But then if you want to focus on something, then it makes sense to think about the problems and particular to that domain, let's say.
Yeah. So the problem I think we were trying to do in 2017 was to convince the community that we hadn't solved the problem. And I think we've perhaps, accomplished that. But now you're saying, now that we realize there's a whole lot of unsolved problems, we probably want to focus attention on a few of them and not just frustrate everybody every time. Right? Yeah. It's well taken.
There's too many domains, and yes, the way we should attack each of them is quite different. Also, I'm also afraid that we are maybe focusing our attention in some very particular things, like we were discussing during the workshop at some point, whether we are doing Diarization precisely on the boundaries, or is that really that important, or even those very short segments, or
right.
Do we care that much about overlap speed? How much does the overlap speed weight over the whole recording, and how are we actually going to use that? So what is the further application or detecting the overlap speeds, and what is the purpose of it? So we are really putting a lot of attention into this very short, but there's much more to be solved in other domains. Like we saw in restaurants, there's something that is still because it's very hard. It's really this like speaker tracking can be very interesting for other applications, or just meetings are very complicated and so on. So I would maybe be more of what are the target applications that we want to really contribute to, rather than to these very small, annoying, but very small or parts of the Diarization system.
No, I agree completely, especially specifically the question of overlaps, which is maybe not the most important piece there, but there were issues with Diarization error rate metric where, for instance, overlaps, if you have 6 people overlapping or lots of 3-party overlaps, those are counted worse than a 2-party overlap. But you know nothing more by detecting there are 3 people. It's what you care about is there overlap speech here or not, probably, because as a human, I don't know what to do with those things either.
Right. So if we're on a Zoom call and half the people are booing and half the people are applauding, and you and you thought only a third of the people were doing something, then you get this huge error rate. I mean, an excellent point. I don't think we want to count frames. I think something more like Sanjeev was saying about turns is sort of more useful. But again, I think you're probably right. We need to be a little bit more focused about some particular application. What I noticed when I was trying to deal with just the simple telephone calls is that I just wanted to know whether the customer's talking, the agent was talking, and it wasn't subtle stuff. And it should be easy to get the ground truth if you just had a separate recording for each conversation, but that often wasn't the case for various stupid reasons.
One thing I just wanted to say is that this has been great to have this sort of roundtable discussion finally. It'd been nice if everybody were in the same time zone and able to be similar degree of being awake. But maybe what we should do, since we're not going to solve all of this in the next 20 minutes, much less few hours, is just decide to have some offline discussion, starting maybe with just everybody who was on this discussion, to figure out what a good venue would be for discussing this, maybe some combination of offline and online. And then maybe in a few months, we can come to a bit more clarity.
Yeah, that's a very good idea.
Do you think it's worth scheduling sort of regular meetings and maybe alternating the hours so that it's bad for different people at different times?
I thought maybe John and I would start just by having an email with everybody and then see what people's pain threshold is.
Okay, sure.
Yeah. So Neville, what has worked for me in these settings is either go for 7 a.m. or 7 p.m. And somewhere like, those 2 times are either equally good or equally bad for everybody in the world, or most people in the world.
Okay, well, maybe John and I just can quickly wish everybody, to thank everybody for showing up, everybody participating in the challenge, everybody who attended the workshop, especially for the almost 20 attendees who have been watching us talk for the last a while. And to wish everybody a good rest of their weekend. Some of you, I think, are probably going to want to go have a very long sleep.
Take care.
All right. Bye.
Thank you.
Bye.
Thank you, everyone.
Thank you. Bye-bye.
Thank you. Bye.
Thank you, Nabil and June. Thank you.
Bye. Thank you. Bye.